Congratulations on making it through the entire material for Unit 5. I hope that at this stage you're beginning to feel a much deeper understanding for why is it that economists think that markets are a very good way of solving allocation problems in many circumstances. And this is based on the key result of the course, which is this first welfare theorem that we have covered. Now, you should also have gained an understanding of what are the key assumptions underlying competitive markets that make the first theorem hold, and a little bit of a glimpse of what we're going to cover later, which is what happens with those assumptions like perfect competition or no externalities get violated. The other thing that you should have gained during this unit is a beginning understanding, a beginning set of insights about what are the tools that we can use to really measure the effects of government policy, and some initial insights about the impacts on taxation on the economy. Now, so far clearly in this unit, we have only focused on efficiency, which is a very desirable feature for evaluating the performance of markets of government policy, but not the only thing that we care about. In particular, we also care about distribution. Next unit, we're gonna take a very deep insight into what happens with respect to distribution. In other words, what are the distributional properties of market outcomes and of different government policies. As always, let me highlight a few concepts that I think are useful committing to long-term memory. The first one is this idea of Pareto optimality, which is the way economists think about efficiency. And the idea is that a feasible allocation, alpha, is Pareto optimal if there doesn't exist another allocation, another feasible allocation beta that has the following properties: ui of beta I is greater than ui of alpha I for some I, and ui of beta I is greater or equal than ui of alpha I for all I. In other words, the move from alpha to beta makes somebody strictly better off, at least one person, without hurting anyone. Now, the other thing that we saw is that with respect to Pareto optimality is that Pareto optimality is basically equivalent to maximizing the social surplus over allocations over alpha feasible. So if you ever need to compute a Pareto optimal allocation and you forget the conditions that we study, for example, you can solve the problem this way. The second, and I'm going to put it in red and highlight it in a box, and I wish I could sing a good song to it to commit it to your memory, is the first welfare theorem. And the idea here is that the allocations generated by competitive markets are Pareto optimal. And the third thing is a first insight about taxes, which we saw that lump sum taxes redistribute without introducing inefficiencies, and non-lump sum taxes are distortionary, i.e. they have a deadweight loss greater than 0. In this video, I'm going to teach you about something called the first welfare theorem, that most economists would probably argue is the most important single result in economics. So I want you to pay special attention to this material because it's going to teach us something very, very important. So let's look at in detail why this result is true. Now, the logic of the result is if an allocation is a market equilibrium, it is Pareto optimal. I'm going to prove it with you using the contrapositive, with the idea is going to show you that if alpha is a market allocation, a competitive market allocation, a competitive market equilibrium, and is not Pareto optimal, then there is a contradiction. There is something wrong. That makes no sense. That's the logic that I'm going to use. Okay? So let's suppose that we have an allocation alpha star and a price P star that are a competitive market equilibrium. They are actually a competitive market equilibrium. Now, I claim that we know that P star must be greater than 0. How do I know that P star has to be greater than 0? Because if P star is greater than 0, given that the marginal benefit for individuals, for every consumer, is greater than 0, they would want to buy an infinite amount of good Q, which would not be an equilibrium. Now, suppose that alpha star is not Pareto optimal. Okay? Let's see what happens. Then there exists another feasible beta, allocation beta, which is Pareto improving. And this implies two important things. This implies, first, that for some I, for at least one I, one consumer I, U of what he gets at allocation I is greater than what he gets at the allocation in the market. But this also implies on itself that, this is a critical step, P star QCI of what he gets at the new allocation plus MIC of what he gets at the new allocation. Notice that this is just the cost of what he gets at the new allocation beta has to be greater than P star of QIZ alpha star plus MCI of alpha star. Notice that this term on the right is what the consumer gets. Sorry, what is the cost of buying the bundle Q and M that he consumes at the equilibrium allocation? Now, this is critical, and you need to understand this to understand the logic of the proof. Why is it that for the individual who's strictly better off, the new allocation has to cost more? Because if it didn't, the consumer could have bought it at the same cost as he did before or less, and he would have gotten higher utility, which means that the consumer could not have been maximizing at alpha star. In other words, if this is not true, we get a violation of individual utility maximization for this individual I. Now, the fact that there is beta that is Pareto improving, it also implies too that for everyone, for every consumer J, U of J of beta J is greater or equal than U of J of alpha J star. We know that a movement to a Pareto improvement allocation cannot hurt anyone. Hear this. Now, but this implies, for a very similar logic, that P star of QCJ at beta plus MCJ at beta, that's how much it costs to buy the allocation at beta, at prices P star, has to be greater or equal than P star QC J of alpha star plus MC J of alpha star. Now, why does this have to be the case? Because if this condition was violated, the individual would also not be maximizing at the allocation alpha star that we are arguing is a competitive equilibrium. So as long as alpha star is a competitive equilibrium, these implications follow. Now, I'm going to continue the proof here. This together implies adding across subjects that the sum over I of P star QCI of beta plus the sum over I of MCI of beta has to be greater, strictly greater than the sum over I of P star Q IC at the market allocation plus the sum of I MIC at the market allocation. Notice that all I'm doing is adding the left-hand side and this right-hand side of these inequalities for every consumer, and we get this. Now, we have that this has to be equal, and this has to be equal by feasibility to the following. We're just going to substitute the feasibility constraint for M, and we're going to get that this is going to be equal to the sum over I of P star QIC beta plus the sum of the endowments minus the sum over all the firms of the cost for firm J of producing whatever it is required to produce at beta. And this is equal, I'm going to write it down here because I don't have enough space, to the sum of P star of QCI of alpha star plus the sum of WI minus the sum over J of CJ QJF at alpha star, whatever the firm is required to produce at alpha star. Notice that all I'm doing is unpacking this term into this and this term into this using the feasibility constraint. But notice what happens. This term and this term cancels because these are just constants on both sides, and not what we get. This term is just the profits, the sum of the profits of the firms at allocation beta, and this is sum of the profits of the firm at allocation alpha. So this implies that the sum over all firms J of the profits, pi of J at beta, remember these are profits, is greater than the sum over J of the profits of all firms at alpha star. But this is a contradiction. This contradicts profit maximization at alpha star, which imply alpha star not a competitive market equilibrium. And that concludes the proof. Think about the logic of the proof. What we have shown is that if something is a competitive market equilibrium, but it is the case that is not Pareto optimal, then we can derive an implication that shows that the firms were not maximizing profits at alpha star, which of course cannot be a competitive market equilibrium. Therefore, we get a contradiction. Therefore, the supposition that alpha star is not Pareto optimal has to be false, and we establish the result. Now, I'm going to give you two separate intuitions about why the first welfare theorem is true that look very different from the proof, and hopefully will give you an enormous amount of economic intuition. So the first is going to be an intuition that I call the invisible hand of the market. And if you are a reader or a connoisseur of Adam Smith, you will recognize this reference. So the idea is the following. Let's compare what market forces do with what are the properties, the necessary properties for Pareto optimality. Okay? Now what do we know? We know that the market forces do. We know that market is gonna settle at a P star and alpha star price and allocation that has the following properties. With first, the allocation is feasible, and we know this from market clearing. The market needs to clear at P star, and that means that the allocation is feasible. But more interesting, we know that at P star, the following is true. The marginal benefit for any consumer is equal to P star is equal to the marginal cost for any firm. Notice that I'm going to do this intuition only for interior allocations. It's an intuition, so I don't want to worry about complicating things with the general case. We know that the following property is going to satisfy for every pair of consumers I and firm J. And this is very important. Now, where does this come from? We know that this is given by the utility maximization motive of the consumers. When in the process of maximizing utility, they don't care about prices, don't care about anyone else, but they end up choosing a level of consumption at which this is true. Similarly, firms don't care about anything else but their profits, but in the process of doing that, while they taking the price P star as given and engaging in profit maximization, they end up setting out a quantity that solves that equation. Okay, so we know that the market does that. But now, as the guy from the Big Bang Theory would say, Kazinga, we have the result. Because let's see why. What does property 1 require? Property 1 requires that the marginal cost be equal among any two firms that produce a positive amount. But notice what's going to happen. Take any two firms. Firm 1 is going to set, let's say, firm J, its marginal cost equal to P star. Firm 2 is going to sell its marginal cost equal to P star. So In the process of carrying the utility maximization, they are equalizing the marginal cost, which is what is necessary for Pareto optimality. Please let me emphasize, and I'm going to come back to this, this is very important, very, very important. The firms couldn't care less about each other. All they are doing is maximizing profits, but in the process of maximizing, this guy sets this to this guy sets this to this, and therefore they equate the marginal cost. Now, this market condition also implies property 2. Why? Take any two consumers. Consumer 1, let's say, is going to equate its marginal benefit to its price star. Consumer 2 is going to equate its price star to its marginal benefit. And again, indirectly, in the process of engaging in utility maximization that generate this equation and this equation, they end up equating the marginal benefits. What about property 3, the one about overall production efficiency? Well, that just follows, is written here. Take any consumer I is going to equate this by utility maximization. Any firm is going to equate this by profit maximization, and indirectly we are equating all of this by the visible head of the market. I want to emphasize one thing, that this is, I know I've repeated like 4 times in the last 2 minutes, but it's very, very important. The fact that all of these Pareto optimality conditions, like equation of marginal cost, marginal benefits, and across marginal benefits and marginal cost, follows from the visible hand of the market. Everybody's trying to do whatever they want, maximize utility or whatever, maximize profits to do as well off for themselves as they can while ignoring everyone else. And indirectly, at the market equilibrium, it just happens that they end up picking an allocation through this market process of coordination that satisfies the Pareto optimal condition. So the invisible hand of the market, this invisible hand of the market that economists have referred to for about 2 centuries, generates a Pareto optimal allocation, and now you know exactly why that is the case. Let me give you another intuition that is emphasized in basic books and is often very useful for working out problems. So let me start with a result, which is that social surplus is maximized over feasible allocations at a competitive market equilibrium allocation alpha star. In other words, whenever you compute an allocation that is a competitive market equilibrium, you're also computing an allocation that maximizes social surplus over all feasible allocations. Now, why is this the case? The proof with everything that you know so far is trivial. Step 1 is we know that the first welfare theorem implies that alpha star is Pareto optimal. And the second thing is we know from earlier that Pareto optimality implies or is equivalent to the maximization over gamma feasible of social surplus of gamma. We've shown this before. So therefore we know that a competitive market equilibrium must maximize social surplus. But beyond the statement, there is a graph that I want to do for you that has a lot of economic intuition. So this is the amount consumed in the market. This is dollars per unit. And I'm going to draw the aggregate demand function and the aggregate supply function. And remember, this is from this perspective, looking at the quantity demand as a function of prices, and we get the total quantity produced in the market, Q star, and we get the market price. Okay? So far, nothing new from last unit, but now notice the following. Remember from our theory of the consumer and our theory of the producer and what we have done before, that this locus of points is also the aggregate marginal cost curve as a function of total production, and that's when we look at the locus as a function of Q, and that this one is the aggregate marginal benefit as a function of Q. Okay? And we saw the interpretation that was the marginal cost of producing another unit for the group and the marginal benefit of producing of giving another unit to the individual with the highest marginal benefit. Okay? Now, from this, we know that intuitively the allocation that maximizes social surplus is going to be the one at which these two cross curve. Why? Because social surplus, it cannot be down here because, let's see, at this point, the aggregate marginal benefit exceeds the aggregate marginal cost, so you should socially, you could increase total well-being by increasing production of another unit. So what we know is that this point is also the point at which is socially optimum, call it that, in the sense of maximizing social surplus. And we know that this price is the point at which the aggregate marginal benefit and aggregate marginal cost cross. So this price is also going to be equal to the aggregate marginal social benefit, marginal cost at the optimum, and is equal also to the aggregate marginal benefit at the optimum. These two things have to be equal at the optimum, but it also happens to be equal to the market price. So notice one beautiful thing, that not only is the market, the invisible hand of the market, leading total quantity at the point that maximizes social surplus, but the price itself is telling you something beautiful, which is what is the aggregate marginal cost of another unit or the aggregate marginal benefit of another unit at the optimum. So you learn something about the marginal social cost and marginal social benefits. I want to discuss several implications of the first welfare theorem that you should be aware of. The first remark is that the first welfare theorem underlies the economist's widespread belief in using free markets. So there is a joke around a stereotype that if you ask an economist how to solve any social problem, any education problem, they would just tell you, create a market and let people trade. The environment, create a market and let people trade. Dating, create a market and let people trade. Research and development, create the right market and let people trade. That's a little bit of a caricature, but it's true that the economist's intuition about the power of the market is informed by the first welfare theorem, and in particularly on the idea that as long as it satisfies the assumptions that lead to the first welfare theorem that we're going to go through in detail in a second, there is no role for intervening in the market, for government policy, just for the purposes of improving efficiency. Since the market already generates Pareto optimal allocations, there may be other reasons for intervening in the market, but it cannot be an efficiency motive. Second remark about the first welfare theorem that to me is extremely important is that the first welfare theorem shows that competitive markets lead to Pareto optimal allocations, and this is a key, at very low informational demands. Not only does the market, in other words, generates Pareto optimal allocations when it satisfies the assumptions of the competitive model, but it does so at very low informational demands. Let's think about this in detail. What is the information required by the market? The only information that is required is that each consumer needs to know its own U, its own utility function and P, and the market price. And producers only need to know their own cost function or technology and P star. That's it. Given that everybody can optimize, and market forces will find a competitive equilibrium. So in other words, think about how beautiful this is. The market forces, when everybody's being selfish and maximizing the utility or the profits, the market forces lead to an allocation that is Pareto optimal, even though nobody knows the whole problem. Nobody really can sit back and compute what is the Pareto optimal allocation. The market forces, through the invisible hand of the market, lead you there. And that's amazing. To see why that is so amazing, suppose that instead you wanted to write this as a dictator. Require info for a dictator, as sometimes economists call dictators, a centralized social planner if they are benevolent and want to maximize some sort of social well-being. But imagine you have a central government agency that wanted to compute a Pareto optimal allocation. What would they need to know? They will need to know not only their own U, but all U's, all the utility function. They will need to know all cost functions. And by the way, as a parenthesis, they will have to compute a very hard optimization problem. So compare. If you use the market, very low information requirements. If you try to have a central government agency like the old Soviet Union used to have their quinquennial plans every 5 years about what to produce and how distributed, you need to know an enormous amount of information and solve a very hard computer science problem. That puts in light how remarkable is the market. Not only does it generate Pareto optimal allocations, it does so with very low and very realistic informational demands. One of the reasons that economists believe that these centralized economies fail is because this is not feasible. And it's not feasible for two reasons. It requires a lot of information that is almost impossible to gather because people will lie to you. They have incentives to lie to you. So you construct allocations that are better for them. And also it requires a very hard optimization problem that we don't quite know how to solve in real time. I want to conclude this video by highlighting what are the key assumptions behind the first welfare theorem and what happens when they break down. So let's do a table in which on the left-hand side we have what are the key assumptions. And the second is what are its consequences, what happens if they break down. So one key assumption is optimal decision making by firms and consumers. So we are assuming in the standard model that everybody is maximizing its true utility or its true production function. And what happens when that breaks out is that the first welfare theorem fails due to decision-making mistakes. So for example, if individuals are making decisions in a consistent way, but maximizing a decision utility function that is different from their true experience utility function, the allocation will no longer be Pareto optimal. And we have seen, for example, that this may be important to understand issues like marketing or myopia, low savings and things like that. And that's studied in a lot more detail in more advanced courses in economics, especially in behavioral economics. The other key assumption is that every actor, whether a consumer or a firm, is a price taker. Now we have discussed this before, that this is a good assumption when every actor is a very small fraction of the market, so they really don't believe that they can influence prices. What happens when this fails? When this fails, you get something called imperfect competition, in which actors, especially firms, take actions with the knowledge that they can affect prices. This leads to situations like monopoly, oligopoly, or branding. It also leads to a first welfare theorem failure, but for different reasons. And in later units of the course, we're going to study what are the outcomes generated by markets in those cases. Another assumption is that there are no externalities. Now, an externality is when somebody's action enters directly in your utility function, even if you didn't trade with them. So for example, if you're sitting in your dorm and the person next door starts playing really loud music, that caused you harm and you didn't buy that from them. They just did it and it affected you. In contrast, when people trade to the market, the actions of someone else, let's say the butcher, only affect you through the act of trading with them. In the basic model, there are no externalities, there are no direct impact of the action of one consumer or one firm on another, and that generates to the first welfare theorem. When that fails, we're in a situation in which it's called public goods and externalities, in which the first welfare theorem fails again. And as we're going to see in the last unit of the course, this is very important for problems like environmental policy, environmental issues, or research and development, funding of universities, etc. The final critical assumption is that there is perfect information about the goods that are being traded. So in other words, for example, when you go to buy a car, you know exactly what its properties and quality are, and neither the seller nor the buyer know more than the other party. That's very important because when it breaks down, you have a situation called asymmetric information. in which people trade with the knowledge that one of them has more information than the other, and that makes the market fail, or the first welfare theorem fails again. Now, understanding this is very important for domains like insurance, used car markets, contracts, like for example the contract with somebody who's renovating your house, etc. Okay? Now, in this course, we're going to look more at this and at this later on. We're not going to go in much more further detail into these two things. This is covered in areas like behavioral economics, and increasingly in an area called industrial organization. So if you want to learn more, you can look at these areas. And this is covered a lot in areas called information economics and contract theory. Now, in order to study these things in detail, we'll have to go into models and mathematics that are well beyond the scope of this course. But I hope that the basic lesson is clear, which is that the model of the competitive market that we have developed has these 4 key assumptions. Every time they fail, the first welfare theorem fails. And therefore, in those cases, we need to understand what exactly that does to the properties of and the efficiency of the allocation generated in those markets. In this unit, we're going to spend a lot of time thinking about whether or not the market generates desirable allocations and whether or not government policies can help in inducing such allocations. It is actually useful to begin with a big picture of the problem. So the idea is the following. Think of what's happening in a market, or in fact in any economy. You have a bunch of exogenous variables, which are who are the consumers, or consumer identity, which are 1, that remember we have been labeled them as 1 to C, and each of them comes with a utility function and the amount of wealth that they have, that they bring to the market, that they start with. There are also a bunch of firms that I'm going to note by firms identity, with their names being 1 up to F, and each of them arrives to the market, to the problem, with a cost function, Cj, that tells how many units of the M good it requires to produce different amounts of the output good. And notice that this cost function may include semi-fixed costs, fixed costs, whatever it is. But the key idea is that we know who are the firms, who are the consumers, and their exogenous parameters. All of this is fed into some sort of institution. And what I mean by institution is the set of rules and practices that is going to determine what is the actual allocation that is going to be what is the outcome of the economy. And there are many types of institutions. For example, right now, so far, we have been interested in pure markets, but you could imagine that later on in this unit, we're going to look at markets and government policies. You could imagine other more draconian policies like dictatorship, there is a single person who determines the outcome, etc. This is just what are the rules and practices that determine what is the allocation. And just to remind you, the institution can only generate a feasible allocation. It cannot generate things that are not feasible. We discuss in detail in Unit 4 what feasible allocations were. So here I'm just reminding you to warm you up for this unit of some key notation. A feasible allocation was going to be described by the level of output for each firm. So the superscript that knows that these are firms, the subscript that notes who is the firm, so how much each firm produces, and then for the consumers, how much each consumer consumes of the two goods. We saw that in the first video of Unit 4. Here I'm just reminding you. And remember, the feasibility allocations just require these two constraints, that the sum over I, or the amount consumed by the sum of good Q consumed by all consumers has to be equal to the sum of good Q produced by all firms. This is an F. And the second thing has to be that the sum of all good M consumed by consumers plus the sum of all good M used by firms to produce, which is this, has to be equal to the amount of the good that was available in the beginning. This part is just a reminder to bring to the forefront of your memory the notion of feasible allocation. Now here comes the big question. So, big question that I want to investigate in this unit is the allocation, let me call this feasible allocation alpha, desirable? So what we want to do is we want to try to learn how to answer this question. If you have a market that generates a particular allocation, is that a good or a bad allocation? And if it's a bad one, what can government policy do? That's what we're going to start in this unit in a nutshell. One small remark before we move forward. Notice that I have phrased the problem as investigating whether the allocation alpha is desirable for any institution that may generate it. And the reason we want to study that in a little bit more general perspective than just pure markets is because we may want to be interested in looking at other institutions. For example, are the allocations generated by a market with a certain set of government policies desirable or not? So we need to be able to determine whether the allocation is desirable in a more general context than only a pure market. There are three general classes of notions of desirability that are used in economics to judge whether an allocation is desirable. The first class are notions of efficiency. The second class are notions of distributive justice. And the third are notions of procedural justice. Let me tell you a little bit about each one of them. Efficiency is just something that measures, it's a notion that measures a lack of waste in either production or consumption. And let me give you an example. If there are two technologies that can be used to produce whatever it gets produced and consumed, and one is more efficient than the other in the sense of requiring less cost to produce the same amount, then an efficient allocation requires that you use the more efficient technology. Distributive justice measures the extent to which the distribution of resources is fair. It just basically cares about fairness in distribution. And let me give you an example. One very famous notion of distributive justice is something called maximin, which basically says that the social distributive justice at an allocation alpha, which we're going to denote by a measure W of alpha, is given by the minimum over all consumers I of the utility that they get at the allocation, at what the allocation gives them, basically. So you compute the utility for every individual, you compute the minimal utility, and that will be the measure of distributive justice according to this maximin criteria. It's just measuring, if you think about it intuitively, whether or not the amount of resources and given how they map to utility is distributed in an egalitarian way across people, basically weighting the well-being of the worlds of person very heavily. Finally, there are notions of procedural justice which basically measure or focus on measuring the extent to which the process used to reach the allocation is fair, is just, is fair. Please notice a very important distinction between the first two and the last theory. The last measure of justice actually cares about the process, whereas the first two don't care at all. It only cares about the final allocation. In philosophical language, these are consequentialist notions, whereas this one is a procedural notion. One example of this, for a potential notion of procedural justice, is equal treatment. Is everybody being treated the same by whatever process is determined is used to determine the allocation? And the answer, the extent to which that is the case, will be a measure of procedural justice according to an equal treatment measure. Now, let me emphasize two things. First, economists have used all of these notions to measure the desirability of allocations, but the ones that are used most commonly are 1 and 2. 3 is used a lot less common, it's a lot more complicated to study. So in this course, we're only going to study notions 1 and 2, and we're going to ignore 3. If you're interested, take more courses in economics. The other thing that I want to emphasize is that both of them are important because these are orthogonal concepts, and you can have an institution-generated allocations, outcomes that are good in one dimension without being good in the other, and vice versa. So we really need to look at both of them. And what we're going to do in this unit is first focus on efficiency and then look more carefully at distributive justice. Economists have a very precise way of defining what efficiency of or lack of waste mean, and I want to teach you what that notion looks like in this video. The notion, which by the way is called in economics Pareto optimality, is built around the notion of a Pareto improvement test. So let me describe first what this means. So definition: a feasible allocation alpha 1, let me put that as a superscript. Pareto improves over a feasible allocation alpha 0 if the following two things are true. First, the utility of I at the new allocation is strictly greater than the utility of I at the allocation 0 for at least one person I, one I. And second, these utilities at the new allocation are greater or equal than at the other allocation for all I. Let's think a little bit about what this means. It means that if you start an allocation alpha 0, you can Pareto improve it with using alpha 1. Basically, if you can make at least one person better off, strictly better off, maybe more, without hurting anyone. So if you want to see this graphically, for example, imagine that you have a plot in which you plot the utilities of everybody at the first allocation, and here you plot the utilities of everybody at the new allocation, and here you have the 45-degree line. For alpha 1 to improve in alpha 0, it has to be that nobody is below in this quadrant. So an allocation, for example, that has a bunch of people there and only one, let's say, here, strictly better off, that is a Pareto improvement. But if you have an allocation, for example, that has almost everybody better off, but one person worse off, that is not Pareto improving. Let me make several remarks about this notion. Remark number 1, you should think of this as a test for a detector of inefficiency. And the idea is that we start with an allocation alpha 0. We want to check whether it is efficient, so we run this Pareto improvement test with other allocations to see if we can detect an inefficiency. Clearly, if the allocation alpha 1 Pareto improves alpha 0, that is a detection of an inefficiency. Second remark that is very important, notice that the notion of waste is defined around the utilities. It doesn't really matter how people are consuming, exactly what they're consuming. We care about their utilities because that's what they care about. And the third thing is, notice that the definition of a Pareto improvement test uses the notion of a feasible allocation. That is critical because I can always improve on any allocation by imagining non-feasible allocations in which more and more and more resources are present. So really, for saying that something is inefficient, it better be the case that you find a Pareto improvement with another feasible, i.e. realistic allocation. Now we're ready to define the notion of Pareto optimality. So definition, a feasible allocation alpha is Pareto optimal, and we will sometimes abbreviate this as PO, if there doesn't exist another allocation, feasible allocation, another feasible allocation alpha hat that Pareto improves over alpha. It's a little bit of a weird notion if you're not familiar, so let me describe it graphically with some intuition. So we have an allocation alpha, is feasible, and we want to check, is it efficient? And what we have to do is look at the set, the back of all possible feasible allocations, all other feasible allocations. And for each one of them at a time, we're going to apply the Pareto improvement test. So we say, if we move from here to here, can we Pareto improve? No. If we move from here to here, can we Pareto improve? No. Now, if this is no for everything, then we can conclude that alpha is Pareto optimal. Why? Because there is no waste in the sense that it's not possible to move to another allocation that makes at least one person better off without hurting someone. On the other hand, if at some point when we are doing the checks, we find that the Pareto improvement test can be passed by moving from alpha to another, let's say alpha hat allocation, then we have to conclude that alpha is not Pareto optimal. Why? Because it didn't pass negatively in some sense the Pareto improvement test. There is possible to move to another allocation that makes at least one person better off without hurting anyone. That is clearly wasteful from a social point of view. In other words, is not efficient. I want to show you a couple of examples that illustrate the notion of Pareto optimality and some properties or some interesting aspects of it. Let me emphasize that these examples are not particularly realistic. They are really designed to make you think about the notion of Pareto optimality. So the first example, think of an economy with two consumers. So there are two consumers, and both of them have preferences U of Q, M is equal to M. They only care about how much of the good M consumes. They have endowments WI. They come to the economy with endowments WI of good M. And there is no production. It's just what we have been calling, in other examples, a pure exchange economy. Okay? So, what is a feasible allocation here? What is a set of feasible allocations? I hope it's easy to see that we can plot it in a line. This line has a length equal to the total endowment of good M, and an allocation is going to be a point that basically tells me how much consumer 1 gets and how much consumer 2 gets. And any point in this line is a feasible allocation. I hope that's obvious to you. What may not be as obvious, and it's going to illustrate a beautiful point about Pareto optimality, is what is the set of Pareto optimal allocations. Well, in this very simple world, is going to be the same. Why? Any point in the set of feasible allocations have the property that if we move to another allocation, hurts one of the people. Let's say start here, move to the right. That makes person 2 worse off because they get less of good 2, and that's the only thing that they care about, and vice versa if we move to M1. So this is a case in which every possible feasible allocation is also a Pareto optimal allocation, and it should be very easy to see for this point a key feature of Pareto optimality, that it has nothing to do with equality. This person getting everything is Pareto optimal, this person getting everything is Pareto optimal. In fact, any possible distribution is Pareto optimal. Here is another extreme example designed to illustrate another aspect of the notion of Pareto optimality. So consider a very extreme and unrealistic case in which there is only one consumer and only one firm. So the number of consumers is equal to the number of firms is equal to 1. And let's start by plotting what is the set of feasible allocations. So I'm going to draw a diagram here that has the amount M consumed by the consumer and the amount Q consumed by the consumer. Now, clearly, the point at which he consumes no Q and W, is feasible. But you can imagine also using the film technology to produce something and say, getting a curve of feasible consumption like this. Now, how do we think about this? Any point in this curve has coordinates like this, which are Q and the W minus the cost of producing Q. That is feasible because basically all of the endowment is used to producing Q, and then the rest is consumed by the consumer. That satisfies the feasibility constraint. So any point with those properties and this line extends down is a feasible allocation. Now we can think of this jump here as the semi-fixed cost that the firm needs to pay. This is an example, by the way, with no fixed costs. Otherwise, we will need to change the details a tiny bit. You can play with it if you want. Now, what is the set of feasible allocations? It is this point, or it is basically this line. All of these are feasible allocations that can be achieved in this market. Now, the question is, what are the Pareto optimal allocations? And I'm going to plot those in red. So actually, just for reminder, let me call black equal feasible allocations. Now, the first thing I'm going to do is draw the preferences of the consumer, the utility function of the consumer in this space. Let's say something like this. These are the indifference scores, the levels combination of Q and M that gives the same level of utility to the consumer. Now, I claim that this point is not Pareto optimal. Well, it should be obvious to you that that point, let me call it alpha, is not Pareto optimal because any alpha hat in this set improves on alpha. So that cannot possibly be Pareto optimal. In fact, if you are following the logic, you should be able to see that the only Pareto optimal point here is going to be this point that I'm going to draw in red, at which the utility indifference curves just touch this feasible set. That is the Pareto optimal allocation here in this particular example. So in red I'm plotting the Pareto optimal. Now, why is that the only one? Well, because it's the only point that doesn't have this feature that I can find another allocation that is feasible and makes the consumer better off. Now, 2 comments. In this particular example, we can still worry about Pareto optimality even if there is only one consumer. And the key trade-off here is Pareto optimality also tells you something about what is the optimal level of production. The second thing is, please do not infer from this example that in general the Pareto optimal allocation need be unique. In economics, in general, as illustrated in part by the previous example, there can be many Pareto optimal allocations. So don't think that is, even though many of our models will have that property, don't think that is a general property of economic models. The goal of this video is to derive what are the properties that a Pareto optimal allocation needs to satisfy. In order to do this, both in the context of the exercise and in future applications like problem sets, we need to derive a couple of results that are going to be extremely useful. So the result states the following. The first one, let alpha be a feasible allocation. Then the following 2 statements are equivalent. Alpha is Pareto optimal is equivalent to saying that alpha maximizes the sum over I of ui gamma I over all gamma feasible. In other words, saying that an allocation is Pareto optimal when it's feasible is equivalent to saying that it maximizes the sum over all individuals of the utility granted for any possible feasible allocation. Okay? That result is going to be very useful, as you will see in a second. Let me emphasize that as many of the results that we derive in this course, this requires, or it's going to be true only under the assumptions of quasi-linear preferences or utility, and the good M, the amount of M that can be consumed, is unbounded bounded below. In other words, consumption of M can go negative as much as necessary. This is going to be required. Now, let's see why this result is true. Let me prove it for you. So why? Now, the proof is going to have two parts. To prove that something is equivalent, we can prove that this, the left-hand side implies the right-hand side, and the right-hand side implies the left-hand side. In this case, it's useful to do something that is logically equivalent. On this side, we're going to prove that if alpha is not Pareto optimal, then implies it doesn't maximize the sum of the U's. And in this side, that will prove that if this is not true, this is not true. So therefore, this is necessary for this to be true. And if something not maximizes the sum of the U's, this implies it's not Pareto optimal. In other words, if this is not true, this is not true, which means that this is also necessary for this to be true. And that proves the equivalence. Okay? So let me start with this case. Suppose that alpha is not Pareto optimal. What does this imply? This implies that there exists I with the utility of, this implies that there exists another allocation, there exists feasible beta, remember by the definition of Pareto optimality, that makes one person better off and at least one person worse off. So when we are across subject, there exists a feasible beta at which the sum over all consumers of the utility of I at beta I is greater than the sum of the overall consumers of the utility I at alpha I. Now, why is this true? Remember, let me emphasize and repeat, because if alpha is not Pareto optimal, we can find another beta that makes one consumer strictly better off and nobody worse off. So when we are across consumers, we get this inequality. But clearly, this implies that alpha is not maximizing the sum of the UIs over feasible allocations. So that proves this direction. Let's look about the other one. So suppose that alpha is not maximizing the sum of the UIs. This implies that there exists an allocation beta, feasible beta, for which the sum of the UIs over beta I is greater than the sum of the UIs over alpha I. But then I claim that this implies that there exists a feasible allocation gamma with the sum of the UIs over gamma I, there exists a feasible allocation gamma with the property that UI gamma I is strictly greater than UI alpha I for all I. In other words, I claim that if this is true, then there exists another allocation gamma that makes everybody strictly better off. Which, if this is true, and I have to show it to you in a second, this would imply that alpha is not Pareto optimal because it violates the Pareto improvement test at the allocation gamma. So to conclude the proof, I have to show you how to construct the allocation gamma out of the allocation beta. It's actually quite intuitive. So gamma is given like as follows. In terms of production, we have that every firm produces the same thing at gamma and at beta. So that has not changed. And the same thing is for consumption of good Q for the consumers. That has not changed. The key thing that has changed is the consumption of good M. And in particular, we are going to have that the amount of good M is going to, at allocation gamma for any consumer, is what it got at allocation beta plus the sum of two terms. The first term is the UI of alpha I minus the UI of beta I. In other words, we add or take from what it got of good M at B this number that can be positive or negative, and then we add the sum of UI beta I minus the sum of UI alpha I divided by C. Now notice the following, and this is the important part for the intuition. What we're doing is reshuffling the good M from the allocation beta to the allocation gamma. How do we know that? Because the sum of this term, the sum over I, is equal to 0. That means it's just a reshuffling, just do the addition. Notice one more thing that is critical for the intuition. If we only had this term, if the only reshuffling that we did was this, then what we have is that all I would have, for all I, the utility I at gamma I will be equal to the utility I of alpha I. In other words, what we're doing with the first term is adding or subtracting the good M such that the consumer is equally well off at allocation gamma than allocation alpha. But what is the final part that you need to notice is that this term is positive, is greater than 0. That means that we're starting with a point in which everybody was indifferent and throwing a little bit extra, which implies that at gamma everybody is strictly better off than at the initial allocation. Don't be overwhelmed by the details, it's actually very simple. What we do is we construct gamma from beta, but not changing Q, but reshuffling the amount of good M in a feasible way to make sure that everybody is strictly better off. Now we get to our second result, which is going to be even more useful in practice. And the result says the following: claim let alpha be a feasible allocation as before. Then we have that the two things are equivalent. Alpha is Pareto optimal, is equivalent to saying that alpha maximizes social surplus at alpha, at gamma, let's say, over all gamma feasible allocations. In other words, Pareto optimality is equivalent to maximization of social surplus over feasible allocations. And as before, let me emphasize that this requires, or this assumes, quasi-linearity of utility and M unbounded below. We're going to use that in the Prof. Now, how do we establish this result? How do we know that this is true? Well, we know that alpha Pareto optimal is equivalent to alpha maximizes over gamma feasible the sum of the utilities. We just proved that. But we also know that this is equivalent to maximizing the over feasible allocations social surplus over gamma plus a constant. And see, the constant do not matter for maximization, we have established the result. Now the key question is, how do we know that? This was proven in Unit 4. Now the result that we have proven have two important implications that I want to highlight. So the first implication is that the properties of a Pareto optimal allocation do not depend on the distribution of M's. In other words, if you think about what we just found, is that to characterize a Pareto optimal allocation, we need to solve the maximization over feasible allocations of the social surplus, and social surplus does not depend on who gets what M. So this proves in a very tight way that Pareto optimal is orthogonal to a distribution or equity. These are different concepts. The second thing is that now we get a formula for how to characterize the Pareto optimal allocation, which is how to find Pareto optimal allocations. You have to solve this. Maximize over Q1 of the consumer, so basically how much does every consumer consumes, how much does every firm produces of the social surplus, and I'm going to spell it out here, the sum of I of BI QIC minus the sum of other firms of CJ QJF. Subject to feasibility, which means that the sum of the QIC is equal to the sum of the QJC. Now, strictly speaking, you need to use a Lagrange multiplier to deal with the constraint, but go back to your knowledge of Unit 1. You can simplify this by basically substituting the value of one of the Q's using the equality constraint, plugging it back here, and then solving the maximization problem with respect to that. Okay, I'm very aware that this is a multivariate maximization problem. I'm not going to be asking you to solve them explicitly. I'm actually going to solve it for you and give you some formulas that you can just apply. And this coming in a second. If you take the first order conditions of the maximization problem that I just gave you, you get necessary conditions for Pareto optimality. In other words, these are conditions that any Pareto optimal allocation needs to satisfy. And this can be organized into the following three types that are very useful. So property 1 is called efficient allocation of production to firms. And what this says is the following is, for any firms, let me call them J, H, and K, with, let's say, QF of J greater than 0, QF of H greater than 0, and QF of K equals 0. In other words, take three firms, any three firms, two of which have a positive production and one of which has zero production. It has to be the case that the marginal cost of firm J at that point is equal to the marginal cost of firm H at that point, and that has to be less than the marginal cost of firm K at its level of production. Okay, so these are properties that the level of production have to satisfy at our Pareto optimal allocation. Second property, which is analogous for consumption, efficient allocation of consumption to firms, to consumers, or efficient allocation of consumption. And it says for any consumers I, J, and K, with the two consumers I and J consumer something positive and consumer K consuming 0, it has to be the case that the marginal benefit for I at what it consumes has to be equal to the marginal benefit for J at what it consumes, and has to be greater than the marginal benefit for K at 0, which is what it gets at the allocation. And finally, it has to be a third property that we're going to call overall production efficiency. And this just says that for any consumer I and firm J with the amount consumed greater than 0 and the amount produced by that firm greater than 0, we need to have that BI prima of QIZ has to be equal to C prima of J of QFJ. Okay? Think of this as three classes of tests that any Pareto optimal allocation needs to satisfy. If they are violated, the allocation is not Pareto optimal. Let me explain the intuition for each of the properties, starting with property 1, efficient allocation of production to firms, that I have rewritten for your convenience here. The basic intuition is that we want to allocate production to firms to minimize the total cost of production. And if this condition that I've written here is violated, then we are not producing what we need to produce at the cheapest possible cost. Let's see why not. So for example, suppose that the condition is violated, so C prima of J of QFJ is greater than C prima of H of QFH. Then we cannot be producing efficiently, because if we decrease, for example, production in firm in firm J by a tiny bit. So we said we bring this down by an amount dqj down by a marginal amount, and what we do is we increase this by a amount dqj by the same amount. Total production has not changed, but notice what happens to cost. So total production unchanged, but cost changed as follows. We have that total cost, or the sum over cost, or overall cost, change as follows. We have that C prima of j qf of j dqj, and this is a negative term, plus C prima of h qfh times dqj, and this is a positive term because this was a negative decrease and this was an increase, and this overall is less than 0 because this term was bigger than this term, so that decreases total cost. In other words, if this condition is not satisfied, we can reshuffle production around on the margin to decrease total cost of production. Now let's see the intuition for why the second property, which is the efficient allocation of consumption, has to hold. So I have, for your convenience, rewritten the condition again, and let's see why. So for example, suppose that we have a situation in which this is violated. Say the derivative or the marginal benefit for consumer I at what it gets is less than the derivative of consumer J for what it gets at an interior allocation. So suppose that is the case. So I claim that we can produce a Pareto improvement. How? What we do is we take a marginal amount of units of Q dQ from this guy with the low marginal benefit, and we give it to the guy with the high marginal benefit. So we move things in this direction. And then we also change the M in the other direction by an amount given by dQ times the difference in the marginal benefits just by the amount of the marginal benefit of the low guy. Okay? So I'm proposing a trait that defines a new allocation that I claim is Pareto improvement. Why is that? Well, notice the impact on the welfare of person I. We're taking this much out, so its total impact of welfare is minus dq times this, but we're compensating him with exactly the same amount in cash. So person I is indifferent. Now what about person J? It gains dq times this much, and it only loses dq times this much. But since bj prima is greater than bi prima, we have that J is strictly better off, which implies the trade is Pareto improving. In other words, if we violate these conditions, and we can play with different cases, but I hope this gives you the intuition, that means that it's possible to construct a Pareto improvement. Now consider the intuition for the third property, called overall production efficiency, that again I have rewritten for you here for your convenience. Suppose that is not the case, to see why. So suppose, for example, that bi prima, the marginal benefit of I at this interior allocation consumption level, is greater than the marginal cost of this firm J that is producing a positive amount. Then I claim that this cannot be a Pareto optimal allocation because it's possible to generate a Pareto improvement. How do we generate the Pareto improvement? We get the firm to increase production by dQ and give this marginal amount dQ to the consumer, and we get the consumer to cover the cost of the firm by decreasing dm by minus dq times cj prima qcj. Now that makes the production of the firm efficient because the extra costs are covered by decreasing the amount of M that the consumer gets, so feasibility is maintained. But notice what happens to the consumer is utility go up, so the change in utility for I is equal to dq times bi prima of qic minus dq cj prima that qcj, which is greater than 0. In other words, if the marginal benefit is greater than the marginal cost, we can improve utility in the economy by taking the cost of production from person I and increasing the amount that it gets produced and therefore consumed by person I by a tiny bit. The conditions for or properties for Pareto optimality that we have just derived are necessary conditions. In other words, if an allocation does not satisfy them, that means the allocation is not Pareto optimal. But what about sufficient conditions? Can we find a set of conditions that guarantee that if the allocation satisfies those properties, it is Pareto optimal for sure? Now, finding general sufficient conditions is a difficult problem in general, especially in the presence of semi-fixed cost or fixed cost, but under some conditions that will largely apply to many of the models that we will study, it's easy to find such conditions. And in particular, if we have that the marginal benefit function is greater than 0 and decreasing, and we have that the cost function is so satisfies decreasing returns to scale, then we have that the first order conditions for Pareto optimality are also sufficient. And remember, these first order conditions are the properties 1, 2, and 3 that we have just identified. Let's revisit the example that we saw before with one firm, one consumer, and let's assume that the cost function has the properties that it is decreasing returns to scale and that there are no fixed costs. So the fixed cost and the semi-fixed cost are equal to 0. I want to show you how the properties, the formulas that we have just derived, apply in this case. So now let's do the drawing that we did before. I'm just repeating it very quickly with these assumptions on the cost function. This is the amount of Q that the consumer consumes. This is the amount of M. And the feasible set is going to be given by this curve. Okay. And the way to generate it is the consumer can choose, we can give the consumer, a 0Q and the endowment in M, or then we can trace this line, and any point that has an amount Q also means that we have to take away from the consumer C of Q, which means that he only gets to consume this much of good M. And all of these points, including things down here, are feasible. Notice, just for your intuition, that the fact that the cost function is decreasing returns to scale means that this is bending in just this precise way. Every additional unit of Q that we want to give the individual is going to cost more and more M. So we need to, for another way of saying that is for every unit of M that we go down, the individual get progressively less and less additional Q. And that explains the bend. Notice that since this has equation, this line has an equation W minus CQ, the slope here, the slope of the line is minus C prima of Q. That is the slope of this feasible set line. Now let's look for a second at the preferences, and we're going to look at these indifference sets, and this is going to be the point that we said before was the Pareto optimal. Remember, these are indifference sets, so these are combinations of Q and M with constant utility. So, utility. Ay, the Spanglish. What does that mean? That at any point, if we want to calculate the slope, let's say, what is the dm associated with any dq, we can do it by taking by doing the following, which we say, what is starting at a point, what happens if we increment by delta q, we're going to get the change of the utility increased by b prima dq. What happens if in addition we do a change delta m, then it's going to increase just by dm, because remember the utility function is bq plus m, and we want this to be equal to 0, so we can stay in the indifference curves, but this implies that dm divided by dq is equal to minus b prime of q. So the slope at any point is minus bq. Now let's look at the conditions for Pareto optimality. Let's look at here at Pareto optimal allocations. I hope you can see easily that conditions P1 and P2 do not bite because there is only one consumer and one firm. So there is no issue about how to allocate production or consumption across firms. But the one that does bite is this condition of optimal production, which for an interior allocation in this case says that B prima at the quantity given to the consumer, I'm ignoring the subscripts since there is only one consumer and one firm, has to be equal to C prima at the amount produced by the firm. That's what we need. And that's exactly the condition that we identified graphically in this case. So the purpose of the example was just to show you how the graphic intuition we derived before is exactly the same thing that is captured by the formula, in this particular case by property number 3. I want to emphasize that in the same previous example, it's possible to have corner Pareto optimal allocations, and that's a case that would look like this. We have the amount of M, the amount of Q, the feasible point 0W, and then suppose that you have that the feasible set looks like this. So it's a feasible set. And that the indifference curves here basically are flatter. So let's say they look like this. So they don't cross here, that's the key. So in this particular case, this is the unique Pareto optimal allocation. Now let's look at what are the first order conditions here. What we have is that this is a steeper, the feasible set, so we have that minus C prima of what the firm produces, which is 0, has to be less, is steeper, so it's more negative than B prima, which is also going to be negative of 0, which is equivalent, of course, to a case in which the marginal cost of the first unit is greater than the marginal benefit of the first unit, for this case of one consumer, one producer. So that's a situation in which the Pareto optimal thing is just to produce no good Q. And the intuition should be obvious. If the consumer is here, you cannot improve his well-being by increasing production of Q, because the marginal cost is going to exceed the marginal benefit. The purpose of this example is to show you how to compute the set of Pareto optimal allocations in a more interesting economy. So suppose that we have 10 consumers and all of them have preferences of the form UI of QM equals to alpha I, where alpha is some positive coefficient, logarithm of Q plus M, again with alpha I greater than 0, and then have wealth W, I. And also suppose that there are 10 firms, just for the sake of example, and each firm has a cost function of Q, beta J Q squared. That's it, with again, beta J greater than 0. Now, let's characterize the set of Pareto optimal allocations. So the first thing that we need to do is derive the implications of the three properties. Property 1 says that we want to look at the difference in marginal cost across firms. Now notice here that the marginal cost for firm J is equal to 2BJQ. That means, because the marginal cost at 0 is 0, that we're going to have interior solutions for any positive level of production. So this implies first interior solutions, and then we know that at interior solutions the marginal cost has to be the same by property 1. So we know that 2BJQ is going to be equal to 2BK, so there's a J there, QK, the marginal cost of firms J and K has to be the same, which implies that QJ, let me put an F here so we don't distinguish with the notation for consumers, QJF divided by QKF has to be equal to the ratio of BK over BJ. So this is the first property that needs to be satisfied of the application of P1 for any pair of firms J and K. Notice what this means, that the ratio of the output of Q of firm J to firm K is inversely proportional to the ratio of their parameter that affects the marginal cost. That makes a lot of sense. The higher this marginal cost parameter for J with respect to K, the lower that ratio becomes. Now let's look at the implication from property 2, which has to be is the analogous with respect to the marginal benefits. Now notice that the marginal benefit for any consumer here is just alpha I divided by Q. And that marginal benefit is infinity, when Q goes to 0. So that implies again that we're going to get interior solutions. And second, that this alpha I over QIZ has to be equal to alpha J over QJZ. That's just the formula of marginal benefit for consumers I and J, which implies that in this case the ratios QIZ divided by QJZ has to be equal to alpha I over alpha J. In other words, the ratios are proportional to the ratios of this parameter that affects the marginal benefit of consuming the good Q. Now, the third property is going to tell us, we know that we are an interior allocation, so that marginal benefit of I has to be equal to marginal cost of J for all I and J. And if we substitute, we can do it for any I and J, but for example, let's do it for firm 1. Well, let's do it for any firm J. Alpha I divided by QIC has to be equal to 2 beta J QFJ. That is going to hold for any pair of consumers and firms. So now we have derived the properties that have to be satisfied, but we are not quite done computing what exactly is the Pareto optimal allocation. We need to do that next. And the key is to remember feasibility. I'm going to put a line here. We know that the allocation is feasible, so look at the feasibility constraint. Implies that the sum over the amount consumed by consumers has to be equal to the sum over of the amount produced by firms for good J. Now, I'm going to expand this with algebra by noticing in this formula, using this formula with K equals 1 for every consumer. So this is equal to the sum over consumers of alpha I divided by alpha 1 Q1C, and this is equal to the sum over firms using the same trick of beta 1 over beta J Q1F. Now I'm going to call, these are just a sum of constants that are parameters of the problem, so let me call this alpha and let me call this beta. Okay, and now what do we have? We have two equations with two unknowns. So it implies that equations are this A Q1C equals B Q1F. That's one equation that we have. And the other equation that we have is this one for the case of the first firm and the first consumer. So it's alpha 1 divided over QC1 is equal over 2 beta 1 for the first firm. Now we have two equations with two unknowns, the production for the first firm and the first consumer. Once we know this, we know how to back out the production for any other firm or any other consumer from this equation. So if we solve this, we have solved the entire allocation. And if you do a little bit of algebra, you're going to get that Q1F is equal to square root of A alpha 1 divided over 2 B beta 1, and that Q1C is equal to square root of B over 2A alpha 1 over beta 1. And again, from that, you can back out all of the quantities. So you have a complete description of what gets produced in good Q and what gets produced in good M. You may be wondering yourself, what about good M? Well, we know that distributions of good M do not matter. Okay? And we also know that they don't, the amount of W that we have doesn't show up in the formula of Pareto optimality. We showed that when we derived the formulas last time. The amount of endowment of good M in the economy doesn't really matter. And let me emphasize that this is because in this model we're assuming that M can become negative. So therefore we're never binding on how much good M we have in the economy to determine what's the optimal amount to produce. If we were to make the model more complex by removing that aspect of it, we would have to do a lot more math tricks to characterize the Pareto optimal allocation. No economics will change, but we'll have to do a lot more algebra. Here is a simple practice problem designed to get you some practice in how to compute Pareto optimal allocations. So consider a simple economy with two consumers, and both of them have preferences of the form utility of I over Q and M is alpha I of Q plus M. Notice the linearity here, with alpha 1 greater than alpha 2 greater than 0. And suppose that there is only one firm in the economy that has a cost function given by mu Q squared. Question: what is the amount consumed by consumer 1 and consumer 2 at a Pareto optimal allocation? This problem is quite easy if you recognize the basic logic of what's going on. Notice that the marginal benefit for consumer 1 is a constant and equal to alpha 1, that the marginal benefit for consumer 2 is also constant and equal to alpha 2, and that the marginal benefit for consumer 1 is greater than the one for consumer 2. This implies that at any Pareto optimal allocation, the amount given to consumer 2 is 0. Why? Because that same unit generates a higher marginal benefit of consumer 1, therefore it cannot be given to consumer 2. Now the next thing to notice is that since the marginal cost for the firm at 0 is equal to 0, this implies that we're going to be at an interior allocation, so the quantity 1 at PO is going to be equal to the quantity consumed by the firm is going to be greater by 0. Sorry, produced by the firm is going to be greater by 0. And this implies that by the condition of Pareto optimality, this Q1 PO is given by solution to marginal benefit of Q for person 1 is equal to marginal cost of Q. This is just alpha 1. This is equal to 2 mu Q. And of course, this implies that Q is equal to alpha 1 over 2 mu. That's it. This problem is designed in a sneaky way to force you to think carefully about the basic idea and the basic properties of Pareto optimality to make sure that you understand the concept. So consider an economy that has n consumers. All of them have quasi-linear preferences or quasi-linear utility of the form ui of q comma m equals bi of q plus m. I'm indexing the utility function by I and the benefit function because they need not be the same. Suppose that the marginal benefit is positive and decreasing for every consumer. Now, suppose there is one firm, only one firm in the economy that has a production function or a cost function that has the following properties. It has decreasing returns to scale and no fixed costs and no semi-fixed cost. Here is the question. This is all of the data that you have. Question: is it the case that every consumer gets a positive amount of Q at the Pareto optimal allocation? And I want you to think of the following categories: yes, no, yes, or it depends on the use only, or it depends on the shape of the cost function only, or it depends on both the use and the cost function. Okay? The answer to the problem is that it's going to depend on both the shape of the utility and the shape of the cost functions. And here is a very easy way of seeing why this is the case. So suppose that you have two individuals that I'm going to plot side to side, two consumers, 1 and 2. And let's see that this one has a marginal benefit function that looks like this. Sorry, let me just, it keeps going to 0, but it starts high. And this one starts low and goes to 0 at a flatter rate. And now let's look at the aggregate marginal benefit function that is going to look, let's say, something like this. This is the marginal benefit for 1, the marginal benefit for 2. And now let's plot the, let's assume, for example, that we have a cost function that looks like this. Mu of q squared. So that means that the aggregate cost function is going to be a line like this. This is the aggregate marginal cost curve. Now, if this line is very steep, let's say here, so if the line happens to be very steep, we have that the quantity star is here, and at that marginal cost at the optimal quantity, only individual one gets a positive amount. However, in contrast, suppose that this line of production is very flat. So we are in a point like this. So this is the quantity optimal in that particular case when the AMC is there. Then at that particular case, the marginal benefit and cost at the optimum is this. And in this particular case, both get positive amounts. Now, clearly that shows that the cost function matters. What about the benefit function? Well, it's obvious that the example really depends on this marginal benefit curve being much below the 1-for-1. If we were to shift this one or make it the same, then both of them will always get, for these examples, in equilibrium. So it depends on both, at the Pareto optimum, sorry. So it really depends on both. Consider an economy that has an aggregate demand function in the absence of taxation given by this. It's a very simple one. And an aggregate supply function given by this. Now, compare two policies. Policy 1 is a sales tax on consumers, in which the sales tax is $200 per unit. And the second policy is a sales tax, but this time paid by producers, by firms, of the same amount. Question: what is, or compute, the difference in the equilibrium prices given by the price in the case of the town consumers minus the price in the town producers, and the difference in equilibrium quantities for, again, the case of the tax on the consumer minus the case of the tax in the producer. Now, hint, because this is a frequent source of mistakes in these types of problems, make sure to remember that P star is the equilibrium price, and that depending on the tax, that is not the total cost or the total revenue either for the producer or the consumer. The equilibrium price means the money per unit that gets exchanged between producers and consumers. Consider an economy that has an aggregate demand function given by the following, and in which there are 200 firms. 100 firms have a cost function given by q squared, and another 100 firms each has a cost function given by 2q squared. Let me emphasize that this is a cost function for each of the two types of firms. I want you to compare two policies. One is a $40 per unit sales tax paid by producers, and another one is a $40 per unit subsidy on producers. In other words, in this second policy, every time they sell one unit, they produce and they sell one unit, they get $40 from the government. Question: which of the two policies leads to a bigger deadweight loss. Let's solve the problem. Let me divide the screen into 3 regions. You will see why in a second. The first thing that we need to do, since we're going to compute a deadweight loss, is to compute the market equilibrium without a tax or subsidy. In that particular case, the first thing we need to do is we know the aggregate demand, which is just 10,000 minus 125p, but we don't know the aggregate supply. So let's compute it. We have 100 firms with a cost function equals Q squared. Is easy by all of the methods that we have shown to show that their supply function of these firms is given by P over 2. For the other 100 firms with the cost function equals to 2Q squared, you should almost in your head be able to compute that their supply function is equal to P over 4. Adding horizontally, we are going to get that the aggregate supply for the market is equal to 75p. 100 of this plus 100 of that gives us this. Now what's the market equilibrium? It's going to be given by aggregate demand equals aggregate supply, which implies at equilibrium 10,000 minus 125p equals 75p, and this implies that P star without policy is equal to 50 and Q star is equal to 3750. Okay, so we have the benchmark. Now let's look at the case of a subsidy. Since both policies are on the producer, we know that the demand for the subsidy case is equal to the demand when there is nothing. Now what happens to the producer? We know that for the producer, it's going to respond to the subsidy by shifting its supply down. In this particular case, it's going to be equal to the supply of what it was willing to do plus the amount of the subsidy, that is 40. Why is that? Well, what the producer is very simple to what we saw in the previous practice problem. What the producer cares about is the net or total price that it gets. And since it's getting the 40, is willing to supply at a lower price than before because the 40 kind of makes up the difference. That's why the supply curve shifts down. Now, this implies that in equilibrium, we're going to have that 10,000 minus 125p is equal to 75p plus 40. And if you solve this, this is going to imply that P star with subsidy is equal to 35 and Q star with subsidy is equal to 5,625. Now to compute the deadweight loss, note the following. If you do the graph of this situation, we have the aggregate supply and the aggregate demand before the policy. Then what happens is that the supply curve is going to shift down by 40 and the quantity demanded, so the quantity produced is going to go up, and the deadweight loss is this triangle. Okay? Now what is the area of that triangle? Is 1/2 times this distance, which is the distance between the amount in the market equilibrium and this other amount, so 56025 minus 3750 times this height. But that height is exactly the size of the subsidy, so this times 40. And this is basically equal to 1875 times 20. Now let's do the case of the tax. In this case, again, the demand with the tax is equal to the demand without, and the supply with the tax is equal to the supply shifted upwards. So it looks like this. Implies at equilibrium, we're going to have that 10,000 minus 125 is equal to 75 times P minus 40. And if you compute the equilibrium, you get that P star with the tax is equal to 65 and a quantity star with the tax is equal to 1875. Now we're in a situation in which the deadweight loss look like this. You have X demand, X supply. The supply has shifted like this, so quantity has gone down and the deadweight loss is this. Okay? And it's very easy to compute that in this case the deadweight loss is going to be equal to 1/2 is again the area of a triangle times the difference between the optimal quantity and the quantity produced, which is again 1875, times the gap, this gap, which is equal exactly to the shift, the amount by which the supply curve has shifted, which is 40. So we get that again is 1875 times 20, and we get that the two deadweight losses are the same. Please don't conclude from this beautiful example that this equivalence is always there. This really depends on the case of linearity, but to the extent that things are locally linear and the introduced subsidy and tax are not too large, this is not a bad insight. They will be approximately the same. What we have done so far is shown that the free market, under the assumptions of the competitive model, generates Pareto optimal allocations, which means that there is no role for the government to intervene just to maximize efficiency. Nevertheless, for reasons that we're going to see later in the course, the government needs to intervene in the market sometimes, for example, by introducing taxes or trade restrictions. What I want to do in the last section of this unit is to give you tools to analyze what is the size of the inefficiency that is introduced by different government policies. In order to do that, we need to define this concept or tool called deadweight loss, which we are going to denote by DWL. And in order to do that, let me just remind you of a concept. We're going to denote by SS optimal and alpha optimal the solution to the surplus or social surplus maximization problem over all feasible allocations. In other words, alpha opt is the allocation that generates the maximum social surplus over all feasible allocations, and SS optimal is the value of the social surplus at such an allocation. We know, by the way, by the first welfare theorem, that the free market, without any restrictions, we generate an allocation that leads to that social surplus. That's what the first welfare theorem basically tells us. Now, given that, now I can define the deadweight loss at any allocation alpha is just equal by the social surplus at the optimal allocation minus the social surplus at the allocation alpha. And let's think of different ways of understanding what this deadweight loss is. One is a measure of inefficiency, or what is the inefficiency at alpha measured in dollars. Notice that SS optimum is the maximum possible social surplus that an allocation can have, a feasible allocation. So necessarily this number is a positive number that only takes a value of 0, its minimum possible value, when the allocation alpha is efficient itself. The other way of thinking about this, if we go back to a result that we proved last unit, is that this is going to be the sum, or a measure of the sum of the utilities over all consumers at the optimal allocation, whatever they get at an optimal allocation, minus the sum over all consumers at the allocation alpha. And if you remember the results from last section, we can also rewrite this as the difference between two terms, the sum over all benefits of whatever the consumers get at the optimum allocation minus the sum of the cost of producing whatever is produced by every firm at an optimal allocation, and that subtracted minus the same thing, this difference between total benefits and total cost at the allocation alpha, that we're going to denote by this. So these are different ways of thinking about what the deadweight loss means. But in essence, the key thing to keep in mind is that it's a measure of inefficiency. Now, the previous formulas can be applied to compute the deadweight loss in any situation that you may find yourself in. But it turns out that under some circumstances that are actually quite common in applications, the deadweight loss has a nice graphical characterization that makes the computations much easier. And in particular, suppose that, or assume that for any aggregate quantity Q that is produced is allocated efficiently among producers and consumers. What I mean by that is that whatever the level of units that are produced by the market, the production is allocated across firms, so it's produced in the cheapest possible way, and allocated across consumers, so the consumers with the largest marginal benefit for those units get the units. In that case, there is a very nice graphical interpretation for the deadweight loss that I'm about to show you. So this is our standard diagram. This is the aggregate marginal cost curve as a function of Q that we studied in the previous unit. This is the aggregate marginal benefit curve in the Q unit. And remember, for any Q, this curve is telling you what is the benefit of an additional unit for the group, and here is what is the benefit of what is the cost of producing an additional unit in the cheapest possible social way. So we know in this diagram that Q star is here, and we know that the social surplus at Q star is this, which will be the optimum. Sorry, just to be consistent with the notation, let me call that optimum. Now, what happens if we produce a quantity, let's say like this one, that is less than Q star? Well, in that case, the social surplus is only this trapezoid and what do we have? That the deadweight loss at that allocation will be this. Okay? Now we can do a similar analysis for what happens if we produce a level Q greater than Q star. In that particular case, let me bring this line up, the total social cost is going to be the area under this aggregate marginal curve. The marginal benefit is going to be, the sum of the benefits is going to be the area under this curve. So what we're going to have is the deadweight loss is going to be this area. Let me call this Q high up, and let me call this one Q low. Note for purposes of intuition an interesting difference between the deadweight loss on the left and the deadweight loss on the right. In this case, there is a deadweight loss because there are units that could have been produced for which the marginal benefits exceed the marginal cost. In contrast, in this region, there is a deadweight loss because the last few units that get produced have a marginal cost that exceeds their marginal benefit. So here, there is too little production, and here is too much production, excess production in some sense. One interesting property of the deadweight loss that I want you to observe is that it increases non-linearly and often approximately with the square of deviations between Q and Q optimal. Okay, this should be optimal there. Let's see why that is the case. So compare the following situations. We have our aggregate marginal benefit curve, our aggregate marginal cost curve. This is the optimal amount. And I'm going to do another diagram here that basically measures the size of the deadweight loss as a function of what gets produced. Okay? And compare the following situations. A situation in which there is a little bit of underproduction, or a lot of underproduction, or a little bit of overproduction. or a lot of overproduction. Okay, so in this case, the deadweight loss is this. It's the deadweight loss of a little bit under production, and this is the deadweight loss of a lot of underproduction. Notice that the deadweight loss is the area of a triangle, and therefore it's going to increase with the square of this distance. So if you were to draw how that increases, it increases something like this. It's initially very small marginal increases, but then progressively every additional unit of deviation from the optimality increases at ever larger rates. And for the same reason, the same thing is true here. So we have this nonlinear increase. In other words, if you're going to deviate from optimality, the first tiny deviation is not very costly, but once you are deviating a lot and you're sitting on a sizable deadweight loss, further and further marginal deviations from optimality become progressively more costly. Taxes come in many shapes or forms. But from a point of view of understanding their economic effects, there is a very basic taxonomy that is very useful, which is a division into two types of taxes. Taxes that are lump sum and taxes that are non-lump sum. And let me explain what we mean by that. A lump sum tax specifies a fixed amount to be paid by each consumer or firm, and this is a key, independently of their actions. It just says John Smith pays $1,000, Pedro Lopez pays $5,000, independent of what they do. And by the way, we're going to denote positive amounts as taxes, as negative amounts as transfers to the consumer or firm. In contrast, in a lump sum tax regime, the tax bill or the tax owed depends on the consumer or firm actions. And there are many types of non-lump sum taxes, as we're going to see repeatedly in examples and exercises, but just to give you one example of something we have encountered so far is a per unit sales tax by consumers. So the tax may specify, for example, that every time you buy a package of cigarettes, you need to pay $1 in taxes. Now, in this section, we want to study what is the effect of taxes on economic efficiency in isolation. Just what is the effect of introducing the tax per se? And in order to do that, what economists do is we're going to consider what are called revenue neutral tax policies. In other words, we're going to consider policies in which the revenue is returned to consumers. They're revenue neutral in that sense. That is very important. If you really want to isolate the effect of the tax policy, you want to return the revenue, because otherwise you don't know if the effects of the tax are due to the fact that you're taking revenue away of the economy or to the introduction of the tax. By making the tax policy revenue neutral, you really isolate the efficiency effects of the tax. Now, lump sum taxes have a very special property that is not shared by any other tax, which is that they do not lead to inefficiencies. Let's see why that is the case. So think of a tax policy that I'm going to note by capital T as a vector that specifies the lump sum tax or transfer paid by every consumer and by every firm. Okay? And we're going to assume that, to make it revenue neutral, that the sum of our consumers plus the sum of our firms of these lump sum taxes is 0, so it's revenue neutral again. Now claim the deadweight loss of the allocation generated by this tax policy is 0. In other words, there are no inefficiencies. Now let's see why that is the case, why we get this beautiful result. So we want to look first at the consumers. So look at the consumers. Look at the consumer problem. They're going to have to maximize over a quantity greater than 0 how much they want to consume, plus their wealth minus the tax, let's say this is person I, that they need to pay, minus PQ. Now the tax is a constant, it doesn't depend on Q, and therefore we can take it, but that implies that their demand, and in general aggregate demand, with the tax is just the demand that they had without the tax. Okay? The introduction of the tax doesn't affect the consumer problem, and therefore it doesn't affect aggregate demand. Now let's look at firms. They want to maximize over Q greater or equal than 0 the revenue minus their cost minus this tax that they have to pay. Let's say this is firm J. Again, this is a constant. It doesn't affect the maximization problem of the firm, and therefore the supply curve also remains unchanged for the firms. But if the supply and the demand remain unchanged, this implies that the competitive market equilibrium is unchanged too, and therefore the quantity produced with the tax is equal to the quantity in equilibrium produced without the tax, which is the optimal quantity by the first welfare theorem, and this implies that the deadweight loss at the allocation generated by the tax is 0. In other words, and again let me emphasize, it's a very unique property of lump sum taxes, they do not lead to inefficiencies. Now, if you're someone who likes government policy or is curious about it, let me just give you a preview of something. You're going to be wondering, why are lump taxes used more since they are inefficient? And what we're going to see next unit is that they have some very important limitations. So they have this nice property, but in practice they cannot be used because other limitations that we're going to study. So hold on that thought. As I mentioned before, there are many types of non-lump sum taxes with very different properties, and therefore, especially with the limited tools that we have in this introductory course, it's very hard to provide a general characterization of their properties. So what we're going to do instead is study a concrete and very common tax, which is a tax per unit purchased by consumers. So let tau be the per unit sales tax on consumers. And this is in dollars. And remember, it's going to be revenue neutral. So this implies there's going to be a transfer tau equals minus sign because it's a transfer. Whatever is raised by the tax, this is the equilibrium price given the tax, this is the amount of quantity purchased. So I apologize, there's a typo here. This should be this. This is the equilibrium quantity. This is the amount of the tax, which is the total revenue raised, divided by the number of consumers. That is the lump sum transfer that everybody receives back to make the tax revenue neutral. Now let's investigate what is the effect of the tax on producers and consumers. For producers, the tax has no effect. It doesn't affect the profit maximization problem, so we know that the supply with the tax is equal to the aggregate supply without the tax. Now let's look at the consumers. For a typical consumer, the maximization problem becomes maximized over Q greater or equal than 0 of its benefits plus its wealth plus the transfer that it gets minus the quantity that it buys times the price that it has to pay plus the tax. Now this is critical. When the consumer is facing this problem, we're going to assume that the number of consumers is so large that its own actions cannot affect the total revenue and therefore the transfer that it gets. So it takes this as fixed, as a constant. And that means that we can drop these two things out of the maximization problem. The maximization problem reduces what is in blue. And what we have, and this is critical, is that from the point of view of the consumer, the problem that it faces when the tax is there is equivalent to the problem that it faced without the tax when the market price was P plus tau instead of just P. That implies that the demand with the tax at any price P, and this is the market price. It's not the net price paid by the consumer, it's just the market price, is equal to what it wanted to buy, or the demand, before the tax, when the prices were P plus tau. Now, given what you have just derived, the effects of the tax on the equilibria and on the deadweight loss are very easily described graphically. So this is going to be price in dollars per unit. This is going to be the total quantity. And that would be the demand, for example, the supply without the tax, and the demand without the tax. We have that this is the equilibrium quantity without the tax, and the equilibrium price without the tax. Now, what happens after the tax is introduced? Nothing happens to the supply, so this remains the supply with the tax. But what happens to the demand is that it shifts down. It shifts down parallel by an amount tau. Okay? And the intuition is very simple for why it shifts down. The consumer now faces a price that is the market price plus tau, so it has to shift down so that it's willing to buy the same amount that it was before the tax, at the same total price that it has to pay. Now, this means that the quantity with the tax shifts to the left, and the equilibrium price with the tax shifts down also. Now, what is the deadweight loss? Well, it's going to be this triangle. It's a triangle, given that we are below, between the aggregate supply and the aggregate demand before the tax, without the introduction of the tax. This is the deadweight loss. Now, if you're curious why is that triangle, remember that the aggregate supply without the tax, when seen from the right perspective, is also the aggregate marginal cost curve. And this locus without the tax is also the aggregate marginal benefit curve. And what we need is the area between those two curves and the quantities with the quantities produced with the tax and without the tax. Now, we can use the same tools of comparative statistics that we developed before to study what is the marginal effect on the equilibrium of a marginal change in the taxes. How do we do that? We know that at equilibrium, the following relationship has to hold, which is the amount demand, and this is the demand curve without the tax, at whatever the equilibrium price happens to be. So this is P star of tau, is the equilibrium price as a function of tau, plus the tau. That's the amount demanded by consumers, has to be equal to X supply times P star of tau. That's the amount that firms want to supply. Again, this is with no tax. Now, we can take derivatives on both sides with respect to T, with respect to tau, the tax, and we get that the derivative of the demand with respect to tau, with respect to the price, the function of the price, times the derivative of what is inside here with respect to the tau, which is the derivative of P star with respect to tau plus 1, has to be equal to the derivative of the supply, Knox tau, with respect to P, times the derivative of P star with respect to tau. Now, this gives us a formula for what is the marginal effect in the equilibrium price of a change in the tax, which is going to be equal to the derivative of the demand with respect to no tau dp, wherever it was, times the derivative of x of the supply, again no tau with respect to the price, minus the derivative of the demand with respect to no tau with respect to the price. Now, notice that this is negative, because demand decreases with prices. This is negative. This is positive, and therefore, together, this is negative. Now, we know the sign. The question is, what is very interesting is what is the magnitude, and this formula is telling us that it's going to depend particularly a lot. It's going to be proportional to what is the sensitivity of the demand curve to respect to price. So, for example, if we are in a situation, let's say start at tau equals 0, in which the demand curve, let's say something like this, okay? And let's say that the initial equilibrium is here. Now, at this particular point, the demand is not very sensitive to the price. You kind of tend to demand the same thing at any local price. So for example, in this particular case, the change in the equilibrium price with respect to a marginal change in tau is going to be approximately 0. That's what the formula is telling you. Whereas, for example, if you're in a situation like this, let's say this was the supply, this was the initial equilibrium, in which now the amount demanded is very sensitive to changes in prices. In this particular case, the introduction of the tax is going to give you a large change in the equilibrium price. Congratulations, you've made it through Unit 6, and you are almost done with 2/3 of the course. I want you to know that the material that we have covered in this unit is quite advanced and not normally taught in introductory courses, especially this argument about the optimal labor-income tax that requires some work and a couple of video lectures to develop is something that is not covered in even most undergraduate courses. But given all of the tools that we have developed in the past for units, we were able to really attack the problem and solve a simple version of it. I hope that you have found that rewarding. I certainly have enjoyed a lot teaching this material to you. There have been a lot of technical details, but there are 3 big ideas that we have covered in this unit that I want to highlight so you remember it for the long term. First one is that the optimal tax problem needs to resolve a conflict or trade-off between redistribution and inefficiency or distortions. Because of the inequality, you want to redistribute, but as you increase the tax, you also introduce inefficiencies, which reduces the size of the pie, and the optimal tax balances these 2 motives. The second point is that price controls, in general, this type of price control policies, have 2 properties. One is they lead to sizable deadweight losses, but can improve either consumer surplus or producer surplus through the redistribution of social surplus between consumers to firms or firms to consumers. And the third is that legal incidence is different from economic incidence. Let me emphasize this. From now on, whenever somebody describes a policy to you, before you judge whether it's a good or a bad idea, you have to work out what is the equilibrium to really tease out what the economic incidence is, because we have seen that it's often very different from the legal incidence. Where are we in the big picture of the course? Unit 6 concludes our systematic study of competitive markets. In the next 2 units, we're going to study what happens in markets when there is imperfect competition, when the firms are not price takers. And in the last unit of the course, we're going to study what happens in markets that fail the first welfare theorem. They fail to produce Pareto optimal allocations because there are externalities. Consider the following scenario. The government is going to introduce a tax per unit of good Q of size tau greater than 0. That he knows going to do, but there is a debate of how to split or who pays the tax, how to split it between consumers and firms. So there's a debate about which fraction should be paid by consumers and which fraction should be paid by firms. Now, the politics of this type of tax debate generates a lot of passion. And to be precise, let me define a class of policies. So we can define a class of policies indexed by A, which is a number greater than 0, greater or equal to 0 and less than 1. that has the following property. A is basically the tax spread. So A is the fraction of the tax paid by the consumers. So that we have tau F is equal to A tau, so tau consumers, and the tau of the firms is equal to 1 minus A tau. And you can have any possible split. Now, this question about whether it matters who pays the tax is a question of incidence. And in particular, in economics, there is a distinction between legal incidence and economic incidence. The legal incidence is who sends a check to the government. Literally, who has the obligation to pay the tax by sending a check or pay the tax at the type of sale to the government. The other one is an economic evidence, which is who bears the cost of the tax. And the reason that these battles make economists laugh sometimes is because people get very invested on fights about the legal incidents that have no impact on economic incidence. In fact, these two things are normally or typically different. And people should fight about economic incidence, but not about legal incidence. And in particular, I'm about to show you that it doesn't really matter who pays the tax in this case. So there should be no debate about it. Claim the equilibrium allocation is independent of A, and therefore it doesn't matter who pays the tax. Now let's see why that is the case. Now the first thing to notice here, we have to be careful, is about what price is what. So notice that P is the market price, which is literally the amount of cash per unit bought exchanged between buyers and sellers. However, given the tax, we have this P plus A tau is the total cost per unit to consumers, which is different than the market price. And also, given the tax system, P minus 1 minus A tau is the total revenue per unit to firms. Okay? Now, notice that the consumers are going to react to the tax at any market price P for a tax given by A by basically trying to shift the tax, as we have been seeing repeatedly, by demanding the same amount that they demand without tax at P plus A tau. This is for A equals 0, which is the case of no tax on consumers. And the firms are going to do a similar thing at any price for any level of the split A. They're going to want to supply the same thing that they supplied at the price shifted down by the tax when they faced no tax, when there was no tax, which for the case is let me write this differently to avoid confusion. I'm just not going to put an A, so this is a case of no tax. Actually, let me just say here, no tax, no tax. Okay? Now, market equilibrium is going to require, it's going to be a P star as a function of A that has the property that the demand with no tax at P star of A plus A tau is equal to the supply with no tax at P star of A minus 1 minus A tau, because that is the level that equates aggregate demand and aggregate supply when the tax is there. One more thing is let P star be the equilibrium price P star of tau, I'm going to write like that, be equal to the equilibrium price when A is equal to 1. In other words, all tax paid by consumers. I'm sorry, when A is equal to 0, all tax is paid by firms. Okay, but then notice that the following, this implies that P star of A equals to P star of tau minus A tau clears the market in all cases. Why? Because if you substitute here, you see that this implies that the demand for P given A is going to be equal, substituting the demand with no tax at P star of tau, and the supply at P of A, again substituting, is going to be equal to the supply with no tax at P star of tau minus tau. But these are exactly, these have to be equal by the definition of P star of tau. Remember that when all of the tax is paid by firms, this is the demand, this is the supply, and in equilibrium these are equal. So we have that the market clears for every case. And not only that, since this is always equal to P star of tau, and this is always equal to P star of tau minus tau, and is independent of A, this implies that the equilibrium allocation is independent of A. In other words, the tax, how the tax is split between consumers and firms does not matter. The following graph should provide you with a nice, simple graphical intuition for what is going on. So this is going to be the demand when tax is 0, when there is no tax, and the supply when there is no tax. Okay, now what happens in the case in which all of the tax is paid by the producer? That is a case in which A is equal to 0, and what we have is that this is equal, the demand doesn't change, but the supply shifts up by tau. And this becomes the new equilibrium price. So this is P star of A equals 0. Okay, now let's see what happens in the opposite case when all of the tax is paid by the consumer, so A is equals 1. In this particular case, the supply doesn't change, but the tax, the demand function shifts down by the size of the tax, also by tau. So this is going to be tau greater than 0, A equals 1. And what we have is a price here at A equals 1, and this distance is exactly tau, that you can see here, since the equilibrium quantity doesn't change. X star with tau greater than 0, A equals 1, is equal to X star with tau greater than 0, A equals 0. A big goal of this section is to study what are the desirability of the allocations produced by the market from a point of view of equity or income distribution, and whether there is a role for government policy to improve such outcomes. Now, in order to study these questions, we need to build a simple model in which there is endogenous inequality that arises in an interesting way. And that is the first thing that we're going to do in this video. I want to start the description of the model by describing to you its basic structure. So as before, the model is going to have firms and consumers. Now, what is going to be different is that now there are going to be two markets and two goods. In particular, the consumers are going to sell labor to the firms, and in exchange, they are going to receive wages. And importantly, these wages are going to be their only source of income. The firms are then going to take this labor and are going to use it to produce good Q that they're going to sell to the consumers, just as before. And in exchange, the consumers are going to pay firms, and those payments are going to be the revenue of the firm. So the key difference is that now we need to look at a model with two markets, a market for good K and a labor market. But otherwise, as you will see in a second, things are pretty similar. Note that in this model, we're going to have to keep track of two prices, P, which is the price of good Q, just as before, W, which is the wage rate, or measured in dollars per unit of labor. And notice that L is the amount of labor sold, so we can put L there. Now let's begin to study the details of the model, first by looking at the consumer side of the economy. Before I do so, let me emphasize one thing, which is that the problems that we're going to study are actually quite complex, and the models can get very difficult. So to make things tractable, I'm going to develop an extremely simple version of the model with some strong assumptions. All of the results that I will create for you, I will derive for you, are going to be quite robust, and I will mention comments about that as we go along. But the model is going to be a very simple one, and the reason is mathematical tractability at this introductory level. Needless to say, more advanced courses in economics covers these kinds of questions in more generality. Okay, so let's look at the model of the consumer. The basic idea is that there are going to be C, consumers. This is the number of consumers. Every consumer has now exogenous wealth equal to 0. Because as mentioned in the previous part of the video, now wealth is going to be, or income is going to be endogenous. Okay? Now, the key thing is that they're going to have a utility function. This is the utility of I defined over three things. Q, the amount that they consume of Q. L, the number of hours that they work, and the amount of M that they consume. So let me emphasize that this is number of hours worked, or units of labor provided. If you want to use another scale, it's not that important what exactly units we use. We're going to assume that this is equal to Q, this linear on Q, minus L squared over 2 theta I. Theta is a parameter that depends on the individual, plus M. Okay, and let's think about this parameter theta for a second. If you notice, this is a utility function increasing Q and M, but decreases in L. There is what is called disutility of labor. So we can think of 1 over theta I, which is going to be a positive number, as a measure of I's disutility of labor. Another way of thinking about it is as a cost of effort. And notice one thing, as theta I increases, so if we plot theta I, here is low disutility of labor, and here is very high disutility of labor. In other words, people with higher theta I have lower disutility of labor. Now, What is the maximization problem that a consumer like this needs to solve? It's gonna, or what is consumer problem? It has to maximize, importantly now over two decisions, how much Q to buy and how much L to buy, greater or equal than 0 of Q minus L squared 2 theta plus, notice there is no exogenous wealth, but this consumer gets labor income LW, and then it has to pay PQ to buy the good. Now, how do we solve this problem? Now we're going to maximize over two dimensions, but things are going to be very similar to before. All you have to do is, when you do the maximization problem, is treat, when you're maximizing over Q, treat L as a constant, and when you're maximizing over L, treat Q as a constant. So let's look at the solution. First, let's look at the conditions for Q. The marginal benefit of Q is equal to 1. The marginal cost is equal to P. And that implies, it's very easy to see, that the demand for any consumer at price P is going to be equal to 0 if P is greater than 1, anything if P is equal to 1, because then this doesn't affect the utility, so he's willing to buy anything, or infinity if P is less than 1. Okay? If you're curious what that demand function like that looks like, I'm going to plot it here for you. It basically is 0 up to 1, and then it's just like this. We've seen this type of demand functions before. Now, notice that when we are horizontally, this is also the shape of the demand for the market at P, for good Q. Now let's look at good L. The marginal benefit of supplying labor is going to be W, and the marginal cost is going to be equal to L divided by theta. Since the marginal cost at 0 is 0, and the marginal benefit is greater than 0, we're going to get an integral solution, and in which these two things are equal. Doing the algebra implies that the labor supply of any person I at a wage W is equal to theta W. And adding horizontally, this is going to imply also that the labor supply of the market at wage W is equal to W times the sum over I, sorry, there should be an I there, theta I, and this is equal to W C theta bar, which I'm going to highlight here, that this is the mean or average theta. Let's check the intuition of these equations to make sure that they make sense. First, the marginal utility of consuming Q is linear, the marginal cost is linear, therefore there is going to be a precise solution. The consumer is going to have a strict preference for what level of Q it consumes only when P is different than 1. And that's why we get this, kind of this continuous shape. Now, the other thing to emphasize that is more interesting is that labor supply is theta I W. In other words, individuals who have a higher coefficient of theta, i.e. have less this utility of labor, end up supplying more hours, and notice that their income, that we're going to denote by I, this is income of I, is going to increase linearly with the square of the wage. Because why we say theta I W squared? Because it's the number of hours supplied times the wage per hour, which is W, gives you this. Now let's look at the firms on the other side of the market. We're going to assume that there are F firms and that they are identical, and all of them have a production function in which F of L is equal to gamma L. In other words, and where gamma is a positive constant, every unit of labor gets transformed into gamma L units of Q. Okay. Now, what is the maximization problem for a typical firm? Is maximize over L greater or equal than 0, P gamma L. Notice that gamma L is the output as a function of the level of input that it uses, so this is revenue. minus WL, and these are costs. The firms are competitive, they take the wages as given. What is the solution of this problem? Well, notice that the marginal benefit of L is P gamma and the marginal cost is W. So this implies that the labor demand by firm J, any typical firm, is going to depend on both the wage and the price, and it's going to take the following shape. 0 if the wage exceeds P times gamma. Anything if the wage equals P times gamma, and infinity if the wage is less than P times gamma. Let's see why that is the case intuitively. The cost of 1 unit of labor is W. The revenue is P gamma. So there's basically linearity in both cost and revenue, which means that the firm is going to be infinity, because if the wage is less than P gamma, because if it makes a profit in the first unit, it makes a profit in every unit, and it can make infinite profits. The opposite is true when W is greater than P gamma, and when W is exactly equal to P gamma, it's indifferent and it doesn't care what it produces. If we add horizontally the labor demand for the market, we get that it's the same thing, for the same reasons we saw before. Now, what is the supply of a typical firm J? Well, it's just going to be lambda times the labor that it buys by the nature of the production function. Now let's add both things together to compute the competitive market equilibrium of the market or the economies. We need to extend the definition of competitive market equilibrium, given that there are two markets, and in this case it's going to be a P star, a wage star, and an allocation star. And by the way, the allocation is to describe what the people get in Q, L, and M goods, such that, not surprisingly, first, consumers optimize over QL given P star and W star. Second, firms optimize over QL given P star and W star. And third, there is market clearing in both markets. Now, let's see what this implies for prices and quantities. Let's see what we can derive. So I'm going to draw here the labor market, and I'm going to draw here the Q good market. And let's do things one at a time. So we know that the demand of the consumer looks like this. Okay, and it's here a price of 1. We also know that the demand of firms is there at a price of W equals P times gamma, and that the supply of labor is, as a function of the wage, is CW theta min. Okay, now what do we know about the supply function of the firm? We know that it's also, I'm going to draw it in gray so it's clear, the supply function is also going to be something like this. If the price very low, is very small, is like this, and then it becomes like this. Okay, we saw that before. Now this is the price of PW, this is as a function of P, as we just saw. And this is as a function of PW. Now here is the key to see how the equilibrium is. Now, for an equilibrium to exist, clearly these two chords need to cross. And there are only two options. Either they cross like this, and there is the quantity producing equilibrium is 0, which means that the amount supply in equilibrium has to be 0, which means that this cannot be an equilibrium since the labor supply at 0 the wage at 0 has to be 0, which means that the price has to be 0, which kind of doesn't hold altogether. So what you see is that in equilibrium, it has to be the case, and I'm going to erase this here to highlight it for you. It has to be the case that the supply also lies here on top of this, and that we have P star equals 1, W star equals gamma. Any quantity can be an equilibrium, and then that L star, which is going to be this, is given by C theta bar or theta mean gamma. That is the only set of prices that clears this market. Now, this may be counterintuitive at the first place. The key thing to notice, if you are missing the intuition in the first pass, is that there are only two possibilities for equilibrium, because there has to be equilibrium in the market Q, which is that this gray curve cuts like this, like above, in which case the quantity has to be 0, but that cannot be an equilibrium in this market given all of the other restrictions. So that means that this has to be like this, and if you check with these prices and quantities, this is an equilibrium. Now, if you think about it, this is very intuitive. The price in equilibrium of good Q is equal to its marginal benefit that it generates for the consumers equals 1, and the wage is the one that makes the firms indifferent about producing anything, because the profits are 0 at that marginal revenue and marginal cost, which has to be the case given that they have constant returns to scale production. Otherwise, an equilibrium would not exist. We have seen those things before. Now, if you're asking yourself, this example is really contrived, and I agree, it's a very special case that I have done for you, in order, as you will see, to be able to really derive a set of beautiful results over the next two videos. The key feature of this example, if this is bothering you, is that the equilibrium prices are pinned down and are going to be independent of any policy that we introduce, of any tax policy of the type that we're going to consider. If that was not the case, in more general models, we have to worry about what are called general equilibrium effects. General equilibrium effects, in which the taxes change some properties of the equilibrium, and that also needs to be taken into account, but it complicates the math. Now that we have characterized equilibrium, we can look at the level of inequality either in terms of income, what is the income distribution that the model generates, or in terms of utility. Okay? And I'm going to remind you that we have found that in equilibrium, W star is equal to gamma. That's equilibrium wage. Okay? To simplify the notation below, I'm just going to call that, I'm going to take out the star, otherwise it's going to become a handful. Now, what is the income, as we saw before, of the individual in equilibrium? It's going to be equal to theta I times the wage, which is substituting theta I gamma square. Now, a good measure of inequality is something like the variance. So what we get is that the variance in income, which remember is a measure of inequality, and it's a measure of inequality, just to remind you of the intuition for the variance if you haven't used it in a while, because it measures how it's spread out around the mean income is the distribution of income, is going to be equal to gamma to the fourth times the variance of the theta I. So this is a nice formula because it's telling us intuitively that the variance of income can be traced back to two parameters, this productivity of labor and the variance in the underlying kind of utility for effort. Remember, 1 over theta was the utility, so theta can be think of some sort of utility for employing effort. So the more variance there is in this fundamental or deep parameter of the model, and the higher the marginal product of labor, the higher the inequality. Now we can also think of this in terms of utility, and remember that we can write the utility of I in equilibrium as a minus L squared, the labor that they supply, divided by 2 theta, plus LW. We also have plus Q minus PQ, but this is equal to 0 because P is equal to 1. So we can ignore that. And now if we substitute the equilibrium values, this is giving us that this is equal to minus theta I W square, both of them, divided by 2 theta I plus theta I W square, which is just equal to theta I W square divided by 2. And again, if you want to think of a measure of inequality in the utilities, what we get is the variance of the UIs is going to be equal to W4, W to the 4, but again, W is just gamma, so it's gamma to the 4th divided by 4 times the variance of the theta I. Okay? This is a measure of inequality in income. Let me put it here. In income, inequality in utility. Notice that the formulas are very simple, not surprising, given that both income and utility in this simple model are linear in theta I. Okay? And very closely resemble each other, since this is gamma squared. So just to recap, what have we done so far? We have built a slightly more complicated model of the economy, in which there are two markets, a market for labor and a market for the quantity for this good Q, in which income of the people are endogenous, and it can be traced back to these fundamental parameters, which has to do with what is the marginal product of labor and what is the disutility of labor that people have that affects how much labor they're willing to provide. And what we find is what is shown in this slide, that in equilibrium, the inequality, either in terms of utility or in terms of income, can be traced back to both, or increases in both, the marginal product of labor and the underlying variance in this disutility of labor parameter. The more unequal people are with respect to that disutility, the higher its variance, the more inequality in income and in utility that we will see. Now consider the introduction of a labor income tax of size tau greater than 0. And the basic idea is that for every dollar that the consumer earns in labor income, it has to pay $2 to the government, and assume for the policy exercise that the revenue is returned to consumers using an identical, and this word is critical, everybody gets the same lump sum transfer tau. Okay, so notice in particular that tau is going to be equal to revenue raised divided by C, the number of consumers. Okay, now question, let's look what happens to the problem of the consumer in equilibrium. So the problem of the consumer becomes maximize over Q comma L greater or equal than 0 of Q minus L squared over 2 theta I plus whatever labor is supplied times 1 minus tau W, because now it doesn't get back all of the revenue, minus PQ, there's no impact, plus tau. Sorry, plus T, the lump sum transfer. And key, this is key, this is assume fixed when maximizing. The idea is that when the consumer is choosing its labor, it doesn't assume that it can affect the lump sum transfer that it gets back, because the number of consumers is so large and its size is so relatively small that it's basically a constant. Okay? Now, notice several things. I'm not going to solve the model again in detail. There is just some obvious things. There is no change in equilibrium price. Sorry. There is no change in the Q market. Why is that? Well, look at the problem of the consumer for Q has not changed. The problem of the firm has not changed. So this implies that nothing has changed in that market. And in particular, that P star is going to be equal to 1. Now, what about the labor market? There is no change in Firm's problem. And we knew that from the previous arguments, what pins down the equilibrium wage was the labor demand by the firm. So this implies that W star is equals to gamma. Okay, and this is going to be very useful. It's what I was referring to before. There is no change in the equilibrium prices. Now the question is, what happens to the labor supply? So we know that the marginal benefit is L over theta I. We know that the marginal benefit, I apologize, is 1 minus tau W. The marginal cost is L over theta I. The solution has to be interior, and this implies that, write it here, this implies that the labor supply of any individual at wages W is going to now be 1 minus tau W theta I. In other words, they respond as if instead of the wage being W is wage times 1 minus tau, which is very intuitive since this is the take-home pay per hour worked. And this implies adding up horizontally that the labor supply for the market at W is going to be equal to 1 minus tau W, the sum of the theta i's, but this is just capital Z times the average theta. Remember, this is mean theta. Now, let's look at how taxes, the size of the tax tau impacts the revenue of the tax, raised by the tax. So we have that total revenue as a function of tau is equal to tau times total labor income. But what do we have? Labor income is going to be equal to the labor supply of the market at the equilibrium wage, which is W star equals gamma. If we substitute, we get that this is equal to tau, from the formulas we derived in the previous slide, 1 minus tau W C mean theta. So basically, notice that total revenue varies with tau as a function of this tau times 1 minus tau times a constant. Remember also that, that the wage is gamma. Now, if you plot that, you get a curve that looks like this. So this is tau 0, 1, 1/2. And basically that curve in this simple model takes a maximum at 1/2. This is total revenue. This is very intuitive. If you don't tax anything, you don't get any revenue. If you tax everything, people are not going to work because they dislike working and they don't get any wages, so you get zero revenue. The sweet spot is somewhere in the middle. A curve of this type is called a Laffer curve in economics, and it's basically based on the idea that when you start increasing taxes from zero, total tax revenue increases for a while and then eventually decreases. So if the taxes are very high in particular, you may be better off reducing the size of the tax rate, which introduces less distortions, less deadweight loss, and on top of that raises more revenue. Now, the exact point of where the top of the Laffer curve is going to depend on the details of the model. This is a very simple model. We get a Laffer curve peaking at 1/2. In other models, it's below. And in other models, it can be at other points. So don't take the precise shape of the Laffer curve very seriously, but take the idea of the Laffer curve very seriously because it's a very important one. By the way, a quick link with current policy debates in the United States. We are in the midst of an ongoing budget stalemate, and a lot of the debate can be traced back to beliefs about where this Laffer curve is. There are many people in the Republican Party which believe, correctly or incorrectly, that we are to the right-hand side of the Laffer curve and that we'll be better off if we cut revenues. The argument by many economists and the Democrats is that that is not the case, that we are actually to the left. This is an empirical question well beyond the scope of this course, but I hope that the results that we're going to be developing are going to give you an insight of what are the key empirical parameters that will allow you to answer this question and make up your mind when you vote on the upcoming elections in the US or in your own country. One very easy way of seeing what is the redistributive impact of the taxes is to write the net tax that a person of type theta I pays. And notice the following: this person gets a transfer equal to tau, 1 minus tau, gamma square C theta bar divided by C. So this cancelled. The top was the total revenue we just calculated. And it also pays taxes minus tau, of rate tau, on its labor income, which is going to be 1 minus tau gamma square theta I. We also calculated these things before. So if we do the algebra, we get that this is equal to tau 1 minus tau gamma square of theta bar minus theta I, which implies that this is greater than 0 if and only if theta I is less than theta bar. In other words, when you introduce the policy, everybody with a theta I below the mean theta gets a net transfer, and everybody above, let me grab this for you, so if this is theta bar, people here get a net transfer from the policy, and people here get a net tax. Now let's investigate the impact on the taxes on inequality. As before, we're going to do it on the left-hand side for income and on the right-hand side for utility. Let's begin with the case of income. Now we know that the total income of the consumer after the policy is going to be equal to 1 minus tau square, W square, which in equilibrium is gamma square, theta I. But he's also going to get a transfer. So this is the post-tax income, wage income. But he also gets a transfer equal to tau, 1 minus tau, gamma square, theta bar. Okay? And this is just the transfer. So notice one thing: if we plot this income as a function of theta I, what we get is the following: that now even if theta I is 0, it doesn't start at 0, it starts at tau, 1 minus tau gamma square theta bar, and then it increases with a slope. This is the income, 1 minus tau square gamma square. Okay? That slope is positive as long as tau is less than 1. Notice for comparison what happens with tau is equal to 0. In this particular case, the income starts at 0 and increases like this with a slope gamma square. So this allows you to see very quickly and intuitively what the tax is doing. Is reducing the inequality and by increasing the minimum guaranteed income and flattening it out. And in fact, if you compute the variance of this, what you're going to get is that the variance of income I is going to be equal to the variance of this plus the variance of a constant. So it's the variance of this, and then we can take out the constants from the basic formulas of variance, and what we get is 1 minus tau to the 4th gamma to the 4th variance of theta I. And as we saw before, when tau is equal to 0, we get the previous case as it should be, the case of no taxes, and then the variance goes to 0, and income is fully equalized only when the tax rate is 100%, which is pretty intuitive. Now let's do the case of utility. Substituting from what we have derived so far, the utility of person I as a function of tau is going to be equal to minus 1 minus tau square gamma square theta I square over 2 theta I. That is the effort, or this utility of L, plus 1 minus tau square gamma square theta I. That is going to be the labor income, post-tax income. and we're going to have another term for the tax, for the transfer, just as before, tau 1 minus tau w squared theta plus, and this is just the transfer. And remember, from the utility, the Q minus PQ drop out because of the equilibrium price equals to 1 that we just saw before, so we don't have to keep track of that. Now, if we do the algebra, this is going to be equal to 1 minus tau squared w squared theta I divided by 2 plus 1 minus tau I'm sorry, the gamma is gamma square average theta. Notice that if we compare the total utility with the I, there is this factor. It's the same except for this factor of 2 in which things are divided. And there is an important intuition for why that is there in the utility, is because when you get income, you also have to pay the cost for it, and that has the net utility that the income gives you. When you just keep track of the income, that factor of 2 is not there. Now, if we do a little bit more algebra, so with more algebra, this is going to be equal to 1/2 w squared 1 minus tau of this term theta I plus tau 2 theta bar minus theta I. Now, if you can compute the variance of the UIs induced by the tax very easily from this middle expression, since the right hand side is a constant and this is almost the same thing as this. What you're going to get is 1 minus tau to the 4th gamma to the 4th divided by 4 the variance of theta I. So as before, the variance in income and the variance in UI are extremely closely related, except for this factor of 1/4. Now, what's the bottom line of what we have found in this video is that if you introduce taxes, you can reduce inequality, point number 1. But point number 2, you cannot fully decrease inequality, because to do so, as you can see in these formulas, you will have to bring the tax to 100%. But in that case, people will react, as we saw in the Laffer curve, by not working at all, which will be self-defeating. So there is a behavioral response to the tax that really introduces a limitation to your ability, or the government's ability, to redistribute. And point number 3, I hope that this is obvious to everyone, there is an inefficiency. Because of the behavioral response to the tax, again, individuals are cutting their supply of labor from what would be optimal, because they only get a fraction of their wages. Now we are going to ask, what is the optimal labor income tax that the government could enact? Now, the first question you should be asking is optimal with respect to whom? And when economists specify this problem, they normally introduce a motive, a goal, a function measuring how good the social outcomes are. And what we're going to do is we're going to assume the following. We're going to assume that people, suppose that is the case that people have preferences, and I'm going to denote now these preferences by B of I, not by U, of Q, L, and M, just as before, but also over the distribution of income. They care about this distribution of income, that take the following form, is equal, just as before, as Q minus L squared over 2 theta I plus M. And then they have this term that is going to be minus sigma square root of the variance of the income distribution. Let me use a different I so it's not confusing. So it's the variance over the i's, where sigma is a constant greater or equal than 0. And here we can call this the basic utility, the UI term, and this is the inequality preference. Let me highlight the intuition of these preferences. If sigma is equal to 0, these are just as before. What we have done is that in addition, when sigma is greater than 0, people derive this utility, they are worse off if there is an unequal distribution, and the higher the inequality, the higher the utility penalty that they get from them. Now, based on them, now we can write, notice also, sorry, that this depends on the type of the individual, the theta I, but this term we have assumed just for simplicity that is the same for every individual. Nothing that we're going to derive really depends on that. Now, the optimal tax problem can be written as maximize over tau greater or equal than 0, the sum over I of the BI's, this big utility function, as a function of tau. So we've seen before that as we change tau, we change the allocation, we change the incomes, we can plug this in every BI, and we want to maximize the sum, the total utility in society, as a function of the tax. And also to give you a high level intuition, notice that this term is very important because it's introducing an explicit motive for redistribution. And we're going to see more specifically how that matters soon. Now, in this problem, notation can get unwieldy very quickly. So to keep things simple, I'm going to use the following notation that I'm going to write here in a box. UI of tau and BI of tau are just basically the utilities as a function of the tax. How do we know the function is the one that we derived in the previous video? I'm going to write by n of tau, the number of theta, the number of consumers with type theta. It could be 0, it could be a positive integer. And then I'm going to write by I theta of tau, what is the income after tax, or the total income after tax, of a type theta, as a function of the tax. This is really going to simplify the notation in a second. Now, the big picture, what we're going to do next is to rewrite the objective function of the optimal tax problem, trying to simplify it, where a lot of the inputs are going to come from what we learned in the last video. So let's start here. We know that the sum of the BI's as a function of tau is basically going to be equal, by definition, to the sum of the UI's as a function of tau minus C sigma square root of the variance of this I theta of tau. Okay. Now, where does this term come from? This is just add the first term of the utility functions. This is the second term of the utility functions. That is C times the basic term, because everybody's preferences are the same. Now, we can rewrite this as follows. And remember, this is just recall, that the income of theta as a function of tau, we proved that last video, is 1 minus tau square w square theta I plus tau 1 minus tau w square theta bar, and we also know that w is equal gamma in equilibrium. Okay, so let's rewrite what these utility functions are. We proved last time that that was equal to, for an individual of type theta, it will be equal to w square 1 minus tau square theta divided by 2 plus tau 1 minus tau w square, the mean theta. This first component was the after-tax income minus the effort for an individual of type theta. This is the transfer. And we have to add over consumers, but instead of adding over I, we're going to add over theta. And we're going to count however many individuals of type theta there are, and we are adding. And that is equal to this term. And then what we're going to do is we're going to do some algebra there. And we're going to say this is equal to minus C sigma, the square root of the following. let's substitute what the variance of I theta is. That is just basically the sum over n theta I theta of tau minus the mean over all of this square. Please let me emphasize this term is the mean I theta tau value, and this has to be divided by C. Okay. Please notice that the reason we divide by C is because this thing within the square root sign is just follows directly from the definition of the variance. Now let's look at this term for a second here on a side. What is I theta of tau minus I theta tau mean? If you go up there, what you see and you do the algebra is that this is just equal to 1 minus tau square w square theta I minus theta mean. But this implies that this term in the top, the sum of n theta I theta tau minus I mean theta tau square, is just equal to 1 minus tau to the fourth, w to the fourth, the sum of n theta theta I minus theta bar square. Okay? And if we divide this by z, and if we multiply this by c and divide it by c, then we get that this is equal to 1 minus tau to the fourth w fourth, the variance of theta times c. Okay? Now we can go back and replug and do some simplification. This is going to be equal to, first let me do some algebra here, w square 1 minus tau square theta, divided by 2 times the sum of theta and theta. This is just this first term. But think about what this is. This is just equal to C times theta bar, the mean theta times the number of subjects, of consumers, plus tau 1 minus tau w square theta bar times sum of m theta. But let's think about what that is. That term is just equal to z, the number of consumers. And then we can finally substitute that term for that, and we get minus c sigma, this fourth has to be outside, 1 minus tau square w square standard deviation of theta. Remember, the standard deviation is just the square of the variance, and it's also a measure of dispersion in the distribution. Now this is going to be linearly proportional to, doing a tiny bit of algebra, w square c theta mean that multiplies 1 minus tau square plus 2 tau 1 minus. I know that the algebra is a little bit messy, but there is no way around it. You need to do it on your own piece of paper to check it. Here I'm just highlighting the key steps. Sigma, standard deviation of theta divided by theta mean. Notice that this statistic is still a measure of dispersion. Now, the maximization problem is not gonna, is a solution to this is gonna be equal to the solution to this, and we can take this out, and this is gonna be for the equivalent to the solution to, with doing a little bit of algebra, the maximization problem of maximizing 1 minus tau square minus 2 1 minus tau square sigma SD theta divided by theta mean. So now we have simplified the objective function into something really tractable, and we're ready to solve the problem. So given all of the really boring algebra, but very useful, that we have done, we can rewrite the problem as maximize over tau greater or equal than 0 the following objective function that we just derive as a simplification. Now notice that we saw before by the Laffer curve that this problem, it was going to have a unique maximum, so we can just take the first order conditions, which are going to be necessary and sufficient, and we're going to get that they are minus 2 tau plus 2 1 minus tau sigma SD theta divided by theta mean equal to 0, and we get that the optimal tax is equal to sigma of SD theta divided by theta bar over 1 plus sigma SD theta divided by theta bar. Now we have a precise formula for the optimal tax. And not only that, we have a formula that is quite intuitive, and let's see why. Let's check our intuition. What happens when the individuals do not care, so check intuition, at all about redistribution? That is, when sigma is equal to 0, they don't care about inequality. This formula tells us that tau optimal should be equal to 0. Similarly, when there is no inequality because the standard deviation among the thetas is equal to 0, which also kind of makes sense intuitively. Now what happens as sigma goes to infinity? Well, as sigma goes to infinity, this tax goes to 1. There is full redistribution, and the idea there, even though by the Laffer curve it's becoming really, really wasteful, and the idea there is that if sigma is very, very large, the payoff of the individuals place so much weight or so much utility on inequality that they are willing to tolerate a lot of efficiency losses. Let me emphasize this point because it is important to really get in the intuition of the solution. As we move from tau 0 to 1, passing through 1/2, we saw that we got a Laffer curve that kind of peaked at 1/2. This is the Laffer curve. Okay. Now we also know that inequality decreases throughout the tax range. Okay, we saw that. So this is inequality, which is variance in income. So what happens is that when sigma gets very large, intuitively makes no sense to move in this direction because you start raising less revenue that you can use to redistribute. But if sigma is very, very large, if the dislike of the inequality of income is very large, the optimal tax problem may push you in this regime, even though it's costing you a ton. I mean, this is so inefficient that you're raising less revenue than you could. You keep pushing this way because you want to reduce the inequality that you really dislike. That's the intuition. Let me conclude with several remarks. The first one is kind of a high-level overview or a big picture that I want you to see. This has been a complicated exercise spanning, or that we have derived spanning 2 videos, perhaps the longest chain of reasoning in the course, and I want you to make sure that you don't lose track of the big picture. So the nature of the exercise is this: you're going to maximize over tax greater or equal than 0 some of these BIs of tau, okay? And these BIs of tau, let me write them down, is the sum or the individual utilities plus this measure minus this measure for the state for inequality of income that we assume maybe what people care about. So we're maximizing total utility given that. Now, when you are maximizing the problem, there is a fundamental trade-off that needs to be balanced, which is, on the one hand, you want to increase tax to reduce inequality, and that pushes you to increase the tax. On the other hand, you want to avoid inefficiencies, deadweight losses, that this push you to a lower tax. And you need to balance these two things in this fundamental trade-off. Notice that the formulation of the problem that we have done solves this trade-off. How? When we are solving the problem, we use the formulas for the income as a function of the tax and the utility as a function of the tax. In other words, we are taking into account how the tax is distorting the behavior, introducing inefficiencies, and maximizing the optimal total social utility given how people care about inequality. That balances that trade-off. So this formulation of the problem is tackling this precisely and head on. The second is a comment about robustness. Are the fundamental insights robust? The answer is yes, although the details change. So if you write a more complicated model in which there are what are called general equilibrium effects, the tax can affect the prices, etc., the details of the formula are going to change, but the basic logic of the problem is very similar. And the third thing that I want to highlight is that solution depends on objective function in the optimal tax problem. In particular, I want you to notice that we have specified here, we are maximizing sum of total utility given that people have a very particular form of what are called social preferences. They do not care about others' utility, for example. They care about the level of inequality in society. Somehow they dislike unequal societies, and that led to the formula we have seen. In problem set 6.1, I'm going to ask you to derive the optimal tax formula under a slightly different objective function of the social preference, and you will see what happens. So the solution critically depends on the objective function, and one naturally source of argument is going to be what is the objective function that should be used to derive the optimal solution. And the fourth thing I want to highlight some key empirical parameters that if you wanted to bring this to the data, you would need to worry about. One is these measures of inequality, which in our model was given by the standard deviation of theta divided by theta bar. How much is something that's telling you how much are the fundamentals that are generating the income inequality spread. The other one is this sigma, which basically think of it as a strength of the social preferences that are, in this case, leading to the redistribution. And in more general models, what are the general equilibrium effects of taxation? In other words, how sensitive are some aspect of the deadweight loss and the factor prices and good prices to the introduction of theta. This is not in our model, but it's going to be important. When thoughtful economists on the left and on the right disagree about optimal tax policy, they tend to disagree not because of this, because the data here is very straightforward. No, so it's not about distribution of income, but about what is the underlying model of the economy that best describes the economy, what are the true equilibrium effects, or what is the objective function that should be used. Some people, for example, extreme libertarians, will think that social preferences should not be there. Others, which will tend to lead them to very low tax rates for redistribution purposes. People in the opposite of the spectrum will have a sigma, for example, in this formulation of the problem that is very large, we would push the optimal tax high. I hope that you have enjoyed this section on the optimal labor income tax, not because I think it's the most important topic in economics, although I think it's an important one and a beautiful one, but because it should really give you a feeling of the power of economics to answer complicated questions like what should be the optimal tax rate, and also of the amazing progress that you have made over the last few weeks from nothing to the ability to really understand how economists can, and the power of the method of economics can be used to formulate these questions, come up with a precise answer, and an answer, more importantly, that links to empirical parameters. There is another very important result in the basic theory of markets called the second welfare theorem that you need to know about because it's really related to the problem of redistribution. It's called the second welfare theorem, and it says the following: let alpha be a Pareto optimal allocation, any Pareto optimal allocation in the model, then there exists, or there is, a list of lump sum M good transfers with their sum t equals 0, such that alpha is a competitive market equilibrium given those taxes. Okay? So in other words, and this is very striking, you can make any Pareto optimal allocation the result of the market if the government, before it lets people trade, just implements a particularly chosen vector of lump sum transfers. Now, this result is very general, much more general certainly than our model, our quasi-linear model, but I want to explain it to you here using the quasi-linear model. So let me give you the intuition here. And the intuition has two parts. First is, notice that in our model, the lump sum taxes transfers do not affect the Q good market. We have seen before that as you implement those transfers, the equilibrium level of Q produce and consume, and the equilibrium price is not affected. What is affected is the consumption of good M. And a way of thinking about what happens is the second part of the intuition is like this. Let's look at a case in which there are only two consumers. Okay? And I'm going to plot here the utility of the first person and here the utility of the second person. And suppose that we are first at a no trade allocation like this one. So this is the no trade allocation. Let's say in which person 1 gets a lot less welfare than person 2. Let's say this is the 45-degree line. Okay? Now what happens when people trade without taxes is that they're going to move, let's say, to an allocation like this, which is the competitive market equilibrium with no lump sum transfers. Okay? They're going to move to something like this that tends to make everybody better off, but still, because maybe where they started, one of the people is much better off. Now, by the way, in this graph, we can define, if we draw a 45 minus 45-degree line, this set is going to be the set of Pareto optimal allocations. Because if you think how this set is generated, is you take the optimal allocation generated by the trade, and then you can reach any one of this by implementing a tax that looks like this. Let's say in this particular case you tax individual 2, a lump sum tax, and then you give person 1 the opposite. They are up to 0 and they move to a point like this. You can implement another one like this, you can redistribute in the other place like this. So as you change the tax for person 2, positive or negative, and a continuous amount, you expand the entire frontier. The total utility in society has not changed. So total sum of the UIs is constant, but you're changing the distribution. So what this second welfare theorem is telling you is that all you have to do for implementing in our model any of these allocations that you may be interested in, let's say the full equality, let's say you're interested on that, is find the tax policy that gets you there, implement it, and then let them trade. And basically what they're going to do is First, the tax policy is going to move them there, and then they're going to move to the frontier. It's very, very intuitive and very simple in our world. Now, it's very important that we think carefully about what are the implications of the second welfare theorem for the role of government policy in mitigating the inequalities that the market may generate. There is a naive interpretation or reading of the theorem that unfortunately is not completely uncommon, although it should be, that says that second welfare theorem implies no need for distortionary labor income taxes. All you have to do is use lump sum tax or transfer policy to redistribute, which implies no deadweight loss. In other words, if taken literally, it says, yes, this is fantastic. You want any Pareto optimal allocation within a particular kind of distribution, find it and just implement the associated vector of lump sum taxes and transfers, and it will get you there. The reason I call this a naive interpretation is that there is a problem here that has to do with the fact that the lump sum tax policy in the second welfare theorem has or involves unreasonable informational demands. Notice that in particular, the government needs to choose a specific tax transfer TI for all I. And to choose it, it needs to know the fundamental parameters of the individual. So for example, it knows who has high utility of labor or low utility of labor, so it can choose the tax appropriately. That is unrealistic. The reason in practice we have to use these policy instruments like labor income taxes is that we don't really know who has high utility of labor or low utility of labor. We only know what we observe in the market, and the policy has to operate with that low level of information. The labor income tax policy regime that we have studied, with all its imperfections, has realistic informational demands. This view of the second welfare theorem that says you can just solve the inequality problem by picking the lump sum tax policy is fine in theory, but it doesn't work in practice. In this problem, I want you to revisit some of the ideas that we have covered in the section on labor income taxation. And in particular, I want you to consider the model that we laid down in section 1.2 of the notes. Now, in that model, I want you to answer the following question. What is the preferred labor income tax of a person with a disutility of labor given by a parameter theta I? Well, the problem of person I is going to be to maximize over tau greater or equal than 0 the utility that it gets at that tax. But from the equation star in the previous video that I highlighted, we know that this is going to be equivalent to maximizing over tau greater or equal than 0 1/2 of W squared, which of course we know is gamma squared. Sorry, I keep forgetting that. Gamma squared 1 minus tau times theta I plus tau 2 theta mean minus theta I. And remember, as in any maximization problem, we can drop the constants and just look at that. Also, remember from the shape of the Laffer curve that this is going to be a concave problem. So we only need to look at the first order conditions. if you plot, in other words, if this is not obvious to you, just plot something, an objective function that looks like this as a function of tau between tau 0 and 1, and you're going to get that it has this shape. So you can just take the first order conditions and it will give you the best tax. So the first order conditions are going to be given by 1 minus tau 2 theta bar minus ti equals to theta I plus tau 2 theta bar minus theta I. And if you solve for that, you get that the optimal theta for person I, its favorite has this ratio. Okay. Notice the properties of this. This is going to always be a number for people. Actually, let me plot it for you. It's going to be easier to see. So if this is theta I and this is the mean theta, when theta I is equal 0, the tax is at 1/2. I'll plot that in red. And then it decreases to 0, and then it stays at 0 for any theta greater theta I. In other words, people who have a tax greater than theta mean would like a subsidy, but that's not allowed in the problem. That's why we stay at the boundary. That is how the policy changes. Now, one thing that as a function, the optimal policy changes as a function of theta I. One thing that is interesting about this is the following. If you have an income distribution, so a right skewed income distribution, basically something that looks like this, that the tails on the right are big, are heavy, it's biased towards the right, you're going to have that theta bar, the theta mean is going to be greater than median theta. So the median person, the person right at the 50th percentile of the income distribution is going to be here, and that person is going to want a positive tax. Okay. I wanted to highlight this to give you a link or a preview of what you may learn in future economic courses that cover something called political economy, which is trying to understand how different political systems select different policies. And one very robust result is that when you have policy choices by the electorate in democracies with this unidimensional policy, like let's say a tax rate, the policy that tends to be enacted across many institutions is the policy favored by the median person. That's intuitive. There are some important details, but intuitively that's a very robust result. So what I wanted to show you here is that in these kinds of tax problems, the median person, when you have a right skewed income distribution, favors positive redistribution. And that may give you an insight when you study more economics, together what you have learned in this course, for why such policies are so common in the world. Question: derive the equation for the Laffer curve in the same economic setting under the following assumption if individuals do not adjust their labor supply in response to the tax on their labor income. Now, the goal of this problem is to get you to think about what is the role of that behavioral response on the Laffer curve. You may wonder, this is totally ridiculous. How can it possibly be the case that people don't adjust their labor supply? Well, if you need a motivation, imagine that the government has enough information that it knows what the labor supply of every individual is in the absence of taxes, and introduce a very large penalty if people supply any other amount of labor. That will give you this kind of policy setting. Okay? As we saw in the video lectures, without the tax, or with a tax of 0, we know that the labor supply of an individual as a function of the wage is just W times TI. But this implies, under the policy assumptions, that the labor supply of individual I at wage W given a tax rate than 0 is still going to be this, the same, because they do not respond by decreasing the labor supply. This implies that total revenue is going to be equal to the tax times the sum over individuals of their labor supply times the wage, and this is going to be equal to tau W square C theta bar. This is the mean theta, and C is the number of consumers. So basically what you get is that if this is tau and this is 0 to 1, the Laffer curve is linear on tau. And in this particular case, full redistribution is possible, okay, without really decreasing the size of the pie, because total revenue keeps increasing. Now, the goal of this practice problem is to first get you to practice your tools of deadweight loss and the analysis of control policies, but also to get you to understand what a difference the details of a policy make. So consider a market in which aggregate demand is given by 1,000 minus P, and aggregate supply is just P. Very simple expressions. And now consider a policy that has the following features. There is a price floor with a minimum price of $7.50. The government buys all excess supply at the equilibrium price. Purchases are financed with a lump sum tax identical on consumers. And here comes the key. The government surprises, there is a surprise return of purchase units to highest value users. Now, the fact that it's a surprise is very important, because this means that it does not affect the consumer's decisions. Let me emphasize. First, the consumers buy what they want, and the government is telling they're going to purchase the units and destroy them. Think about it this way. And then after the consumers have purchased, the government surprises them and gives the units that it's bought to the highest value users. Question: compute the deadweight loss for this policy. So let's analyze the policy using the same technique that we have been doing in the video lectures. Let's plot the market here, and this is a market that looks like this, very symmetric. The demand is 1,000 minus P, the supply is P. Notice that the equilibrium price before is 500, and then let me around this plot two interesting prices, P mean, which is 750, and then this 250. And then what I'm going to do is draw these lines out here, and I'm going to define some areas for us. Okay, it's going to be A, B, C, D, E, F, G, H, I, and J. Now we know that the price, see the equilibrium price is 500, the price floor is going to be binding. And we also know that this is the quantity, which is 250, bought by consumers. And this is 750, which is the produced quantity. Okay, So now we're also, to analyze the deadweight loss of the policy, we're going to do our usual table, which has consumer surplus and producer surplus and social surplus at free trade, at the minimum policy, and the difference. Now, the free trade has not changed. It's A plus B plus, well, in this case, E, C plus D plus F, and the social surplus is A plus all the way plus F. So that is the same. Now let's look at the policy effect, which is more interesting than before. First, let's look at the consumer. So the consumer gets the first 250 units at a price of $7.50, so therefore they get A as consumer surplus. But notice that they also need to pay as taxes before all of this rectangle, which is minus E plus F plus G plus H plus I plus J, but they get the units, so they get a benefit of E plus F plus G plus J. So this cancels, this cancels, this cancels, and this cancels. Okay. Now let's look at the producer surplus. The producer surplus, the producers is just as before in the video. They get to sell all of these units at that price, and these are the production costs. So they get B plus C plus D plus E plus F plus I. If you add these things, you get A plus B plus C plus D plus E plus F plus I minus H. So it's A plus all the way plus F minus H, sorry. So that means when you do the difference, that the deadweight loss is only minus H. It's only this in this case. And it's very easy to compute that this is equal to $62,500. Just the area of that triangle. Let me emphasize, in case it was not obvious to you, why it's so important that the return of the policies to the highest value users, to all of these users, is a surprise. It's because otherwise the consumer would have caught the purchases up here and the analysis would have been different. So the fact that it's a surprise is key to getting this much lower deadweight loss. Now, this practice problem is designed to get you to think further about the difference between legal and economic incidents. So consider a very simple pure exchange economy that we have encountered before. And here is a twist in the economy. There are 2 C consumers and no firms. Now, of these 2 C consumers, half of them, so C of them, are buyers, are what we call buyers. And what I mean by that is that they have preferences U over Q and M equals to B of Q plus M, and they have no endowment of Q. The other half of the consumers are sellers. Their preferences are given by simply M. They don't care about the bar Q, but they have an endowment of good Q given by Q of E. This is the endowment per seller. Now, the question that I want to ask you to answer is the following question. What is the difference in consumer surplus for sellers between these 2 policies? Policy 1 is a tax tau greater than 0 per unit sold paid by the sellers is the key, and the second one is the same tax, but this is paid by the buyers. So compute what is the consumer surplus in policy 1 minus the consumer surplus in policy 2. Okay, let's solve the problem. I'm going to divide the screen in three parts. This is the without tax, or before the introduction of the tax. This is the tax on the seller, and this is the tax on the buyer. So before the tax, let P star be the equilibrium price. And what is very easy to see is that graphically, that particular case looks as follows. The supply of the sellers is just equal to CQE, because basically they want to sell every unit, they don't care about the good. And the demand is going to be something downward increasing like this. Oops. It's a function of P related to the horizontal demand of the marginal benefit function, and we're going to have that P star is this, whatever that number is, it doesn't really matter for the problem, and X star is CQE. Now, let's see what happens when there is a tax imposed in the seller. Well, that's not good news for the seller, but the seller still wants to sell, so its supply at P has not changed. It's going to sell everything because it doesn't want to consume the good Q. The demand has not changed, so this is with the tax for the seller. The demand has also not changed because the tax is on the seller side, so this is going to be the demand without the subject, without the tax at P. So since the demand and supply are not affected, this implies that P star, when the tax is on the seller, is just P star. And clearly, since the supply is vertical, X star, when the tax is on the seller, is also CQE. Now let's see what happens when the tax is on the buyer. Again, the sellers just want to sell everything. And the key question is what happens to the buyers? Well, the buyers are going to react. The tax is on the buyer, but the demand is on the buyer side, basically by trying to demand the same amount that they bought before, but at a higher price that incorporates the tax that they have to pay. We have seen this several times before, so it should be very familiar. But this implies that this equilibrium price clears the market with this quantity. So in all of these cases, this clears the market. Now, the case of the T buyer, I'm going to draw in red here. Basically what happens is that the buyers react by shifting by tau their demand with the tax on the buyer, and that shifts the equilibrium price P star to P star minus tau. Okay. Now notice the following. What is going to be the consumer surplus of the sellers in this case? Well, it's going to be the amount of units that they sell, CQU, Q superscript E, times the price at which they sell it minus the tax that they have to pay. So this is when the tax is in the seller. What is the consumer surplus here? Is C times QE. In this case, they don't pay a tax, but the equilibrium price has gone down to P star minus tau. So these are the same, and the consumer surplus is the same. There is no difference. Notice the intuition, that economic intuition here that is nice, is that when the supply is unresponsive to prices, the sellers end up bearing the full tax. The prices adjust one-to-one to the introduction of the tax on the consumers, so that is shifted back to the sellers. There are many goods that have this property, by the way, as long as they are unresponsive. A typical example is art or land. We're going to switch gears now and consider another class of policies that are widely used by the government to alter the outcomes generated by the market, and those are price control policies. And let me start by giving you a very high-level taxonomy of what these price control policies look like, and they can be categorized along two dimensions. First is whether it's a price ceiling the policy involves a price ceiling or a price floor. In the case of a price ceiling, basically what it says is that the price has to be less or equal than a price max. And the price max is the ceiling specified by the government. The price floor is a policy that says sellers can never sell or trades can never take place below a certain price. Okay? So the name is self-explanatory. The other is whether the policy involves a simple intervention or a complex one. In a simple intervention, what the government do is just impose the price restriction, and that's it. So just the price restriction. In a complex one, it does a price restriction plus necessary actions to clear the market. This is going to make a lot more sense what exactly a complex policy involves when I explain what happens in a simple policy. These simple policies are very common. An example of price ceiling are rent control for apartments. I suspect that many of you live in cities and may have even grown up in households that whose house were subject to rent control. They didn't pay a full market price. These price floors, especially with this complex restriction, is very common in agricultural policy. For example, the government may not want the price of some crop to fall below a certain level, and it imposes a price restriction and takes actions to guarantee that that is the case. These are just some examples. There are examples here too, but I'm going to skip them for now. In this video, we're going to focus on studying simple price restrictions. In the next video, we're going to look at the complex ones. So let's think for concreteness about the case. What is the case of a simple price ceiling? Now, there are going to be two potential cases, and what I'm going to draw in this here is a case where the policy binds. So the policy is not binding. You will see in a second what I mean. And here is where policy binds. So in both cases, I'm going to draw exactly the same supply and demand diagrams. So this is the demand in the market as a function of price. And let's say this is the supply as a function of price. It doesn't matter what the details really are, but I'm just drawing it like this. The key right now is that they are the same. Okay, and now suppose that we consider the introduction of a price ceiling. Sorry, in both cases, the equilibrium is this quantity and this price, which is the same. Now consider the introduction of a price ceiling, and one potential case in which is this is with the price ceiling P max is greater or equal than P. In that particular case, the policy does not bind. It doesn't affect the equilibrium. You get the same equilibrium with once the policy is introduced. So this is equal to X star with P max, and this is equal to P star with P max. Why? Because the market forces are going to lead you to this price, which is below the price ceiling, so there is no problem. That should be obvious. Now, the case that is more interesting is what happens if the price ceiling is something like this. So in this case, P max is less or equal, than P star. Okay? So in this particular case, because of the policy, what we're going to have is that this becomes the new equilibrium price, because the price cannot go above that. But here comes the problem. At that price, suppliers want to supply this much, and consumers want to consume this much. So there is excess demand. The price is too low for the market to clear, and that means that not everybody that wants to buy at that price is going to be able to get. And this implies we need a rationing rule. which specifies who gets the units that are produced that is less than the total demand. And a typical, the typical one that is used is something called an efficient rationing rule. Which says that the units are allocated to highest value users, highest value consumers. The idea is that if there are only that many units, you allocate the first one to the consumer with the highest value, the second one to the consumer with the highest value given that, etc. So nobody with a higher marginal benefit for the unit than the ones that have it get it. Now, that assumption, this efficient rationing rule, makes a lot of sense if you believe that the effort that people will make, let's say by standing online or finding other consumers, finding clever ways to find the scarce units, is proportional to the marginal benefit that they derive from their units, which is not a crazy assumption. So what is the equilibrium in this particular case? In this particular case, we have that this is the total amount produced and consumed, and that the units are given basically to these subjects, to these consumers. These are the units with the highest marginal value. This is from the efficient rationing rule. So let's analyze the welfare effects of the binding price ceiling. Suppose we have the demand looks like this, the supply looks like this. This was the initial equilibrium price and quantity. Oops. And we introduce a price ceiling like this that is binding, and this becomes a new equilibrium. And this becomes a new quantity produced. And of course, we're going to assume the efficient rationing rule. Let me label these areas as follows: A, B, C, and D, E, and F. And I'm going to make a table here of what's the consumer surplus, the producer surplus, and the social surplus at the free market, at the price ceiling, and the change, the difference. Okay? So let's start with the free market. It should be obvious to see that the consumer surplus is A plus B plus E, that the producer surplus is C plus D plus F, and the social surplus is the entire triangle, which is A plus blah, 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 plus F. Okay? Now what's more interesting is what happens after the policies introduced. Notice now that the producers can only sell this many units at that price, so the producer surplus now becomes that. So the producer surplus becomes D. Now the consumers get this many units with these marginal benefits because of the efficient rationing rule, and they only pay this much. So the surplus for the consumers is all of this. Is A plus B plus C. So what is the social surplus? Is A plus B plus C plus D. Okay. Now we can compute what is the difference between these areas, which means that is this minus this, so it's C minus E. So consumer surplus can go up or down. Consumers as a whole can be benefited depending on whether this area is greater than this or not. It's going to depend on the details of the problem. Now, what happens to producer surplus? It goes down by minus C plus F. sorry, minus C plus F, like this. And what happens to the difference in social surplus is minus E plus F. And that is, of course, the deadweight loss introduced by the policy. So it's going to be this area. Now, let me make a couple of remarks. Clearly, when the policy is binding, it is inefficient because it produces this much loss in social surplus. Plus, please notice that there are cases in which the policy can have redistributive effects. So imagine, as we have been describing in previous models, that the people who own the firms are not the consumers. So there is a group of people who are firm owners and a group of people that are consumers. This policy entails a welfare loss, but also a sizable potentially transfer of producer surplus to consumer surplus. This C gets transferred to there. So potentially the consumers could be better off for the policy and could be highly in favor of it. And that may explain some of the politics about rent control that you see in many cities, New York City being the most prominent of them. Now consider the introduction of a complex price floor, P mean, that has the following properties. The policy says that P has to be greater or equal than P mean. And the government buys excess supply at whatever the equilibrium price happens to be. And that is done so that the market clears. Notice that once this is done, one needs to worry about two things. One is, where does the revenue for the policy comes from? And we're going to assume an equal lump sum tax. So whatever the revenue that is necessary to pay for that is raised for consumers using an equal per head lump sum tax. Now, why lump sum taxes? Is we know that most taxes are distortionary, because we want to isolate in our study the efficiency cost of the price floor from the efficiency cost of taxation. And if we were to use a non-lump sum tax, we would not know where the source of the inefficiency comes from. That's why we focus on that form of revenue. The other thing that we have to worry about is, once the government is buying its excess units, what happens to the units? To the units bought by government? We are going to assume that they are destroyed. Now, you may think that this is a ridiculous, wasteful, immoral policy. I would agree personally with you. Unfortunately, it's very common, especially in the agricultural realm. So it's not completely unrealistic. So let's see what is the effect of the policy on equilibrium. We have that the market without looks like this. X demand, X supply. And then, of course, this is the P star without the policy, the quantity in equilibrium. Now, a binding price floor gets introduced. It's going to be something like this. Pi mean. It's going to be binding because the prices cannot go down to their natural equilibrium price. And what we're going to have is that then this becomes the equilibrium price with P mean. And then there are going to be two quantities that are relevant in this complex policy. One is the X star consume. This is the amount that the consumers get to consume. And this is the amount produced. Notice that these two are not the same because the government buys all of these units. So these are bought by government, but destroyed. Now let's look at the effects of this complex policy, complex price floor policy on social surplus. Now, this one is going to be a little bit more complicated than before, so it's important that you follow every step and rewind if necessary. This is the demand, this is the supply, this is going to be the price floor, the binding price floor, and I'm going to define several areas for you. I'm going to call this A, B, C, D, E, F. This weird looking thing is G, triangle H, triangle I. And as before, I'm going to do a table about what is the consumer surplus, the producer surplus, and the social surplus under three conditions: the market, the binding price floor, and the difference between them. Okay, so let's do it together. The market is just as before. It's going to be A plus B plus E, C plus D plus F, and the sum from A to F. What now becomes more complicated here is what happens with the policy. And remember that this is the amount consumed in equilibrium with the policy, and this is the amount produced. And these are the units bought by the government and destroyed. Okay, so what is consumer surplus? Well, clearly they get to buy all of these units with the efficient ration rule. The consumer surplus is A. But we are not done, because the consumers also need to pay a lump sum tax to finance the purchase of all of these units at the binding price. So we also need to take out minus E plus F plus G plus H plus I. These are the taxes that have to be paid. Okay, now what about the producers? The producers get to sell all of these units to the consumer at a price B plus C plus D. Sorry, at the price P mean. They only incur this cost, so they get all of the surplus B plus C plus D. But they also get to sell to the government all of these units at the same price. So they also get the surplus E, producer surplus E plus F plus I, which is the total revenue from those units minus the total cost. So plus E plus F plus I. If you do the sum, you get A plus B plus C plus D minus H plus G. Okay? And if you do the difference for the deadweight loss, you're going to get minus E plus F plus H plus G. So this is the deadweight loss of this policy. Notice that it's bigger than the one we had before, and I'm going to talk about the intuition in a second. What about the producers? Well, the producers are better off by B plus E plus F plus I, and the consumers are worse off by minus B minus B plus F plus G plus H plus I. So this policy is particularly bad for consumers. I hope that you can see that. And it also entails quite a bit of transfer of consumer surplus to producer surplus. Now, what's the intuition for why the deadweight loss is larger in this case than in the previous one? Well, in the previous case, with the deadweight loss was due to the fact that these units from here to the X star were not being produced, and it was socially efficient to do so, so that led to that deadweight loss. But here, in addition of not producing those units, we are producing extra units and throwing them apart. And not only that, the extra units that we are producing, all of these are being thrown away. So that has a cost, which is the cost of not consuming these units and having to pay the cost. And that extra cost is what is showing up there. So this policy is particularly inefficient. Congratulations, you've made it to the end of Unit 7. You are this close to completing the course, so I urge you to keep pushing. I hope that you feel that you have learned several important lessons at a very high level, at a big picture level in this unit. Number one is that the market generating outcomes with perfect competition are fundamentally different from the outcomes generated in markets with monopolies. First, the first welfare theorem breaks. And second, because the monopolist is no longer a price taker, a very interesting set of features that we observe in the marketplace, like price discrimination, like quantity discounts, arise. However, having said this, I want to bring you back to Unit 1, in which we saw that the fundamental problem that any company is trying to solve is maximize profits, and that leads them to equate marginal revenue and marginal cost. Please notice how that fundamental lesson has not disappeared in this unit. Even though things look different, the problem definitely looks more complicated, that fundamental force is still there. Let me summarize some of the key ideas that are worth committing to memory from this unit. We have looked at different types of the monopoly problem based on what is the extent to which the monopolies can discriminate. So first we look at monopolies without price discrimination. And in that case, what we saw is that the monopolist sets marginal revenue equals to marginal cost, and that the first Welfare theorem fails, so we have an inefficiency. The deadweight loss is greater than 0. Then we look at the monopolist with perfect price discrimination. And we saw that in that particular case, there is no deadweight loss, but that the monopolist basically ends up charging this unit and individual specific prices that allow us to extract all of the social surplus. In other words, the producer surplus is equal to the social surplus. We finally look at those set of circumstances that perhaps are more realistic, in which the monopolies have imperfect price discrimination abilities. And for example, we look at the multi-market. In particular, I want to highlight that, the multi-market price discrimination. And we saw in that case what the monopolist does is sets the marginal revenue in every market I equals to the marginal cost, and that still generates a deadweight loss. Okay. Second, we also look at what are the policy tools that the government has to deal with monopoly in the case of full information. And let me highlight that all of these results really depend on this assumption of full information that is not particularly realistic, but we cannot attack the full case in this course. What we saw is that the government can do regulation, or it can engage in a subsidy policy. With regulation, basically what it does is induces the firm to choose Q monopoly equals to the optimal quantity, either through a price or a quantity regulation. And if it's in a price regulation, what it says is the price of the monopoly is equal to the aggregate marginal benefit at this Q optimal quantity. Now, with a subsidy, what the government does, it lets the monopoly do whatever it wants, but it sets a subsidy which is equal to the aggregate marginal benefit at the optimal quantity minus the marginal revenue at the optimal quantity, and this is greater than 0. In both cases, the deadweight loss is equal to 0. So far we have seen that monopolies often generate allocations that are not particularly desirable, either because they are inefficient or because they entail a large transfer of surplus to the producers from the consumers. That obviously raises the question of whether there are things that the government can do to improve the outcomes in monopolistic markets. And we're going to discuss some of the instruments at its disposal. The first instrument that is widely discussed is to promote competition. And the problem with this instrument is that it has limitations. Okay? It works sometimes, but not others. So where does it work? So a typical example will be eliminate patronage or eliminate government-created monopolies, especially when they don't have monopolies, when they don't have a particularly economic justification for existing. Now, another example here that sometimes could be useful is R&D, research and development in new technologies that can increase competition. So let me give you a favorite example of mine. Right now, a typical example of a monopoly are utilities. For example, the companies that bring broadband to you, or the companies that bring power to your house. Now, imagine the development of very small cost-efficient reactors that could serve a city block or a small city. That will introduce, the development of such reactors will introduce enormous competition in the electricity utility market and will naturally break the monopolistic nature of this market. And there are many other examples out there that one can think of. Now, but there are also cases in which it doesn't hold. For example, if there are true market economies or network economies, it's hard to promote competition because the monopolistic nature of the market is inherent to the characteristics of the market. Another very common policy to try to address monopolistic competition and the problems that they generate is regulation. And this is, for example, extremely common in the utility market. And the idea is the following. Suppose that the government has full information, okay, about the market. So in particular, it knows the cost function of the monopolies and the demand function. Then it can compute the optimal price and the optimal quantity. And don't be confused, the optimal quantity is obvious. By what I mean by the optimal price is what's the marginal benefit of the last unit or the optimal unit. Okay, then the government can get the Pareto optimal allocation using either what is called quantity regulation or price regulation. And let me describe each one of them. In price regulation, what the government says is that the price has to be this optimal price, and again this is equal to the aggregate marginal benefit of the optimal unit. And then monopolies is free to sell at this price. It chooses how much to sell at this price. And in quantity regulation, what the government says is that the monopolist has to sell Q equals to Q optimal and is free to charge any price. Any, let's be specific, single price. There's no price discrimination. Now, it's very easy to see that in both cases the government replicates the equilibrium of the market economy. Let's look at the case of the quantity regulation, for example. Suppose that the government tells the monopolist that this has to be the outcome, this has to be what it has to produce. What is the monopolist going to do? It faces this inverse demand function. Well, it's going to want to charge exactly this price. This is the price at which it maximizes its profits, and that price is going to be the price of the monopolist with regulation. And it's going to be equal to this optimal price. Now, in contrast, consider what happens with price regulation. The government tells the monopolist it can sell whatever it wants at this price. And then the monopoly chooses quantity, but what does the monopoly have? It has its marginal cost function, and what is it going to choose? It's going to choose this quantity with a regulation that is equal to the optimal quantity by design. Why do we know that it's there? Because we know that at the optimal quantity, marginal benefit has to be equal to marginal cost. Let me make two remarks about this policy that are important. The first one, it replicates the outcome of the competitive market equilibrium. So if the firm had, to be precise, it replicates the outcome that would have happened if the monopolist had acted exactly as a competitive firm, and it doesn't involve any taxes or transfer or anything like that, so it's relatively simple. But the second, it depends, or it requires full information to be able to compute P optimal and Q optimal. And this is very important, okay? One of the great advantages of the market that we saw before, it was able to generate these Pareto optimal allocations without anybody having to know this information. If we have a monopolist, the government can fix it, but it needs that information. And that information is not always available. That's what was one of the reasons we use markets in the first place. So in order to really study the effects of regulation in a realistic setting, one needs to model the uncertainty that the government has when it's choosing these policies and the amount of information that it really has, and things look significantly more complicated. That's well beyond the scope of this course, but if you're interested, I urge you to take more economics, in particularly either industrial organization or an area known as public economics. The government can also use tax policy to try to incentivize the monopolies to produce the optimal amount, and in particular it can use a subsidy, sigma, of size A aggregate marginal benefit at the optimal amount minus the marginal revenue of the monopolies at the optimal amount or the optimal quantity. If it gives it this subsidy, then you get the first best level, or the Pareto optimal level of production, And this is the way to see that. Look at this diagram of the problem of the monopolies. You have the inverse aggregate demand function, you have the marginal revenue function, and you have the marginal cost of the monopoly, say something like this. The government would like the monopolies to produce at this level, which is the optimal amount, but it notes that the monopoly is always going to set its net marginal cost equals to marginal revenue. Now notice the following. Under a subsidy, the problem of the monopolies becomes to maximize over Q greater or equal than 0 its revenue. This is revenue, total revenue, and we can write this as minus C of Q minus sigma Q. We can write the costs like this. I understand that we could have put the subsidies here, but I want to write them like here. I want to put them in the cost to pass you some intuition. From this perspective, the problem of the monopolies becomes to set, just as before, marginal revenue from here equals to marginal cost in quotation marks. Now, what does that do to this, our graph of the problem we have been looking, is as if the marginal cost curve has shifted down by sigma. And then, if it has shifted down by exactly that amount, the monopolies is going to want to set its quantity of the monopolies given the subsidy equals to the optimal quantity. Notice that the market equilibrium price in that case is this. Which is going to be equal to basically the aggregate marginal benefit at the optimal quantity. Okay? Now, some important remarks. First, Pareto optimality is possible only if the cost of the subsidy can be paid with lump sum taxes. Okay, there's going to be a transfer of money to the producer. That transfer needs to be financed with some revenue. That revenue is to raise with taxes. If those taxes are lump sum, then they don't introduce an inefficiency. But if they have to be raised with some sort of distortionary tax, then full restoration of Pareto optimal is not possible, and the efficiency cost of raising the money has to be deducted. The second point that is important is that in general, or typically, this policy has bad distributional properties. And the intuition is very simple. What the policy does is it taxes the consumers and it gives the cash as an incentive to the producer. But in equilibrium, the producers end up getting a transfer, the monopolies in particular, equal to that amount. Now, if the ownership of the monopolies is concentrated in a small fraction of consumers, or even in someone beyond the market, that entails a huge redistribution from consumers to producers. And finally, I want to highlight again, for very similar reasons to before, that Pareto optimality requires full information by the government. And in particular, enough information to be able to compute what the optimal subsidy is, what is the marginal benefit for society at the optimum, and what is the marginal revenue for the producer. that requires a lot of information that the government often doesn't have. Hi, welcome to Unit 7. In this unit, we're going to take a radical departure from what we have been doing for the last few units. In particular, we're going to abandon the world of competitive markets in which there are many firms, many consumers, and everybody's a price taker, and we're going to enter the world of imperfect competition. In this unit, we're going to look at markets that are characterized by monopolists, in which a single firm is basically servicing the entire market and no longer takes prices as given. In fact, as you're going to see, it has a lot of power to set prices, and that's going to change things in quite interesting ways. Next unit, we're going to look at another set of markets in which there is still imperfect competition, but instead of a monopolist, there is a small number of firms competing for servicing the consumers. The structure of the analysis and the tools that we're going to use are going to be very similar. There's going to be firms making decisions to maximize profits. We're going to look at the kind of equilibrium outcomes that they generate, and also their desirability properties, whether the outcomes are efficient and what are the distributional properties. Finally, we're also going to consider whether there is a role for government policy to improve the outcomes generated by the monopolist. Let me highlight one thing that is extremely important, and I don't want you to lose sight of this point. It sometimes confuses some students. We are looking at different models of markets because different markets have different characteristics, and therefore the same model of market doesn't apply to all markets in the economy. So, for example, the model of competitive markets applies really well to competition across restaurants for the restaurant market, where there are literally dozens, if not hundreds, of restaurants in every locality competing for service. But it doesn't apply very well to the market for operating systems and software, when a very, very small number of companies are servicing the market. Or if you're like me, you are a devotee of Apple, and in which case your life is in the hands of one company. So we need to expand our model of markets to really be able to answer the fundamental questions of economics: what was produced, how and for whom, and what are the desirable properties of the decisions created of the outcome generated by markets in all of the different types of markets. Besides learning how to extend our theories to analyze markets with imperfect competition and carry out government policy analysis in those markets, you're also going to get insights about the real world of the following sort. You may really understand for the first time why is it, really why is it, that movie theaters all over the world offer prices that are different to different people. For example, in Spain and in the United States, senior citizens pay a very small fraction of what people in middle age like myself paid. You're also going to get an insight into why airline companies price their goods the way they do, which for example, you may be aware of this. When you travel in an airplane, the price that you pay for your seat may be a fraction or several times what the person sitting next to you does. These models of monopolistic competition and imperfect competition with more than one firm that we are going to cover over this unit will give you insights into this real world phenomena. Let's begin our study of markets with monopolistic competition by looking at a model of a monopoly that does not engage in price discrimination. And I'm going to sketch first the basic model for you. So as before, the model has two parts. It has a model of the consumers, which is basically going to be just as before. There are going to be C consumers. Each consumer has a utility function over Q and M, which is quasi-linear, just as before. And we're going to assume that every consumer has a WI endowment of the M good. We're going to assume that they are price takers. And importantly, using all of the methods that we have developed for the case of perfect competition, all of that is going to allow us to derive the aggregate demand function as a function of the price for the market, just as before. What has changed now is the producer side. Now the number of firms is only one. There's only one firm, and who's not a price taker. And that is critical. In particular, this firm knows the aggregate demand function or equivalently, the inverse demand function for the market. It has cost, a cost function Q, with decreasing returns to scale of some form, and it picks quantity, the quantity it's going to produce, taking into account the impact in market prices. Let me emphasize already how different this is. Before, the firms were price takers. Now, there's only one firm, and it's going to have the power to change market prices. And in particular, because it's not the demand, it's going to fully internalize the effect that changing the quantity that it wants to sell has on the market price that its product commands. Now let's look at the problem of the monopolist. It's going to want to maximize over quantity greater or equal than 0 its profits, just as before. The key thing is, what are the profits now? It's going to be PD of Q times Q minus the cost of producing Q. Notice that this is, as before, revenue minus cost. Those are profits. What has changed is what is the definition of revenue. And it's important that we understand why it has changed and how. Before, this was just P, the market price, times Q. Now is this inverse demand function divided by Q times Q. Let's understand why. So I'm going to do a diagram here. The monopolist knows that it's facing a demand function with an inverse demand curve PD of Q. And basically, you can think of PD of Q as the market price that the monopolist can charge for any quantity and still sell all of these units. So therefore, what the monopolist asks is, what quantity should I produce given that I'm going to be able to charge PD of Q? So it's fully taking into account how, as it increases the quantity, for example, the price goes down. Now, what are the first order conditions for this problem? Well, it's going to be as before. First, let's do it for an interior case. Marginal revenue at Q equals marginal cost at Q. Now, the key question is, what is marginal revenue? Before, it was just P, the market price. Now it's going to be given by Q times dP of dQ, and this is of the inverse demand function, plus PD, and this is just C primer. So notice that the marginal revenue has changed. Notice that this is negative, since the demand function is downward sloping. And basically, it has a different shape as before, and we're going to explore the consequences of that in 1 second. Notice also that for a corner solution, this just look as the marginal revenue at 0. So this term evaluated at 0 has to be less than the marginal cost, less or equal the marginal cost at 0. And also notice that the second order conditions are satisfied if the marginal revenue is less than 0. And this should be very intuitive to you from previous work that we have done, especially in Unit 1. If the marginal revenue is negative, the problem of the monopolist can be plotted like this. You have a marginal revenue curve that is decreasing in Q. Sorry, what I should have said here is if the marginal, I apologize, if the marginal revenue decreases with Q. So you have a marginal revenue curve that looks like this. Let's say you have a marginal cost function that is flat or not or increasing, and then it's clearly that there is a unique solution for the monopolist, which has this value. This is QM, by the way. Now, the intuition should be obvious. If you start at 0, you should produce the first unit because the marginal revenue exceeds the marginal cost. You should produce the second unit because it's the same, and you should keep going up to the point with marginal revenue equals marginal cost. So basically, the same ideas about optimization that we have been seeing all along still apply for the monopolist, except that the marginal revenue looks different. Let me describe graphically what the equilibrium looks like. You have quantity, you have price, you have the inverse demand function that looks like this, and as we will see in the examples, and also as you can infer from the definition of marginal revenue, the marginal revenue curve basically looks something like this. It starts at the same point and goes below it, decreasing. So this is going to be the marginal revenue curve as a function of Q. Then let's say you have the marginal cost curve, is something like this. And if the monopoly is producing an interior allocation, producing a positive amount, and by the way, when the QM as the quantity produced by the monopolist, what we have is the following. The monopolist picks this quantity, but please notice that this is not the equilibrium price. The equilibrium price is this, the price that the market would bear, the maximum price that can be charged, and still get that amount produced. So this is the amount that is the price in equilibrium. Now, it's illustrated to compare how is this different from the case in which the monopolist had acted as a perfectly competitive firm. In that particular case, we know that this would have been the supply curve of the firm. So this would have been the quantity in equilibrium if the firm had been competitive, and this would have been the price on equilibrium if the firm had acted as a price taker. So, in other words, the monopoly introduction of the switch from the competitive behavior with this, other things being equal, the same firm, the same cost function, increases the quantity produced and increases the equilibrium price. Let me give you some intuition for why marginal revenue tends to decrease with Q. So let's look at our diagram of the inverse demand function. And let's do the following. Suppose that you start at quantity Q, and we know that we are at that price, P. And now consider increasing the quantity to Q plus DQ by a tiny amount. We know that total revenue is gonna change. Before it was this area, now it's gonna become the area of this rectangle, because the price is gonna decrease to this. Okay. Now let's see what is the impact in total revenue. Well, the increase in the quantity increases revenue approximately by plus P, whatever the price P was there, DQ. Now let's look at the size of this area. Is approximately Q, P prima, which is a decrease in price, DQ. Notice that P prima DQ is the approximately change in price. So this is DP basically. And notice that DP is less than 0. So this is a positive term, this is a negative term. Now what is the change in marginal revenue? Is going to be P times DQ minus Q prima, all of this, sorry, plus Q prima, all of this by DQ, where this is negative and this is positive. Now look at the following to understand why marginal revenue goes down. This term dominates when Q is small. So let's say when it's approximately 0. Why is that the case? When it's very small, the price is very high, so this term is very positive, and this term is approximately 0, so Q is 0. Now this term dominates when Q is large. Let's see why. When Q is very large, the price is approximately 0, so this term goes to 0, it goes down, and as Q increases, this term becomes more and more negative. So that pulls the marginal revenue down. Now, let me emphasize, this suggests there's a very robust phenomena that marginal revenue will go down, but let me highlight that it's not always the case. So it cannot be guaranteed that marginal revenue tends to decrease with Q. And you can basically construct cases in which that is not the case. And if you want an intuition for why it is the case, one particular simple way of constructing is remember that when you look at the aggregate demand function, sometimes you have kinks like this, in which different individuals start coming in at different points, and that can very easily produce marginal revenue that is locally increasing. So far, the analysis have ignored the issue of fixed costs or semi-fixed costs. How do this change the problem of the monopolist? It's very easy. What you do is do 2 steps. Step 1, is compute the profit of the monopolist, the best it can do conditional on entry. Step 2, you compute the profits conditional on not entry. And then you choose the solution with the highest profits. In other words, even if there are fixed costs, if conditional on entry you do better than non-entry, you entry and you pay either the fixed cost or the semi-fixed cost, otherwise you don't. And we're going to explore this in more detail in the practice problem. We have seen from the first welfare theorem that competitive markets generate Pareto optimal allocations. Let's see what happens when we have a monopolist without price discrimination. Let's look at our equilibrium diagram. We have the inverse demand function. We have the marginal revenue curve. We have the marginal cost curve. We know that the optimal quantity is this. And we also know that the quantity produced by the monopolist is this. Now, it should be easy to see that the deadweight loss in this case is this area. Why? Because the quantity produced by the monopolist is below the optimal quantity, and basically by increasing production by all of these units, we can obtain social benefits, marginal benefits that exceed the marginal cost of production up to this point. Now, the exact formula for this area is equal to the integral from the quantity of the monopolist to the optimal quantity under the inverse, between the inverse demand function and the marginal cost curve, dq. Let's get some intuition to try to understand why the first welfare theorem works for competitive markets, but not in the case of the price of the monopolies without price discrimination. So let's compare the case of the competitive market and monopolist that we are studying here. So in the competitive case, what we had is that every individual, by the way, this is just for intuition, look at interior solutions, because this is just, it's not a rigorous analysis, I'm just trying to pass you an intuition. Every individual equated their marginal benefit with the market price, and this was driven by their utility maximization, and every firm equated the price with their marginal cost, and this was driven by price taken plus profit maximization. Now, together, this implies that marginal benefit is equal to marginal cost for all firms, and this implies Pareto optimality. In other words, the invisible hand of the market guided the equalization of marginal benefits and marginal cost, which is what is required by Pareto optimality, through the fact that everybody equates this marginal benefit with price and marginal cost with price in order to maximize their well-being. Now, what happens in the case of the monopolist? Well, the consumers do the same thing. They try to equate, or they equate marginal benefit to marginal cost, again, by utility maximization. And the firms still want to equate, wants to maximize profits. But the problem is that what they do is they equate, marginal revenue equals to marginal cost. This is what monopoly plus a profit maximization gives you in this case. And the problem is that the marginal revenue, as we have seen, is always less than the price. So this implies that in equilibrium, marginal benefit of the consumers is greater than marginal cost, which implies Q of the monopolist is inefficiently low. In other words, the invisible hand of the market, when individuals can influence prices, does not guide you towards the conditions required for Pareto optimality. Finally, let's do a distribution analysis of the equilibrium generated by the monopolist case in comparison with the behavior in the equivalent competitive case. So we have again our equilibrium diagram. we have the inverse demand function, the marginal revenue, the marginal cost, and I'm going to highlight several things. This is the quantity at the competitive case. This is the quantity of the monopolist. And I want to highlight, this is the price of the monopolist, remember. I want to highlight several areas here. Let me call them A. This is all of this triangle here. B is the rectangle. So basically ignore the marginal revenue curve when labeling this area. C, D, E, and F. And let's do our usual table, especially with a focus on producer surplus and consumer surplus at competitive case and at monopolies. Now let me emphasize that the competitive case assumes basically that there is one firm with exactly the same cost function is just behaving competitively. So in the competitive case, the producer surplus is C plus F plus D. That should be obvious. And the consumer surplus is A plus B plus E. Now what happens when we shift to the monopolist case? The consumer surplus just becomes that. So it goes to A, and the producer surplus becomes all of this. So B plus C plus D. Notice that if you do the difference, you get that consumer surplus is going down by minus B plus E. So the consumers are clearly worse off as a group if you only take into account their effect on them and consumers, not as firm owners. And you have that the producer surplus is going up by B minus F. Now we know that B minus F, this is very important, has to be greater than 0. How do we know that? Because the firm could have replicated the competitive outcome by just choosing Q star. Therefore, the fact that it didn't do that, that it chose a lower quantity, means that its profits went up, which means that B has to be greater than F. So basically, there is a redistribution of consumer, there is a deadweight loss, but there's also a redistribution of consumer surplus to producer surplus. Now, that redistribution effect is not important if the firms are owned, if the firm is owned equally by everybody, but that is not typically the case. What you have typically the case is that the firm ownership is concentrated, so you have redistribution of social surplus if there is concentrated firm ownership. The goal of this example is just to give you practice with how to compute the equilibrium of a basic monopoly case without price discrimination. So consider a simple economy or market in which the demand function as a function of the price for the aggregate market is just 1,000 minus P. Suppose that the cost function for the monopolist has decreasing returns to scale like this. Now what do we know? We know that the total revenue as a function of the quantity for the monopolist is just going to be the quantity that it chooses times the price that can be separated out this quantity, which is given by the inverse demand function of the aggregate demand function, which is denoted by this, and substituting, we get that this is Q times 1,000 minus Q. Now this implies that the marginal revenue for the monopolist as a function of the quantity that it chooses is just the derivative of this, which is 1,000 minus 2Q. And we also know, trivially, from looking at the cost function, that the marginal cost for the monopolist is equal to 2Q. We know that the solution for the monopolist is given by the intersection or by the point where the marginal revenue is equal to marginal cost, which implies solving these two equations that the Q of the monopolist is equal to 250. And if you go back and substitute in the demand function that the price at which the consumers buy in monopoly is equal to 750. Now we can do a quick drawing of this just to get a graphical intuition, and in this particular case we get a linear marginal cost function like this equals to 2q. We have that the demand function is linear, and it basically goes down like this. It crosses here at 1,000 and it crosses here at 1,000. This is the inverse demand function, so function of q. But we also know, and I'm going to draw it in red, that the marginal revenue curve has twice the slope. So basically it starts at the same point, but it crosses at 500. That's the marginal revenue curve. And what we have here is that the price of the monopolies, so this quantity at which it crosses is 250, and the equilibrium price at which the consumers buy is 750. And you have that. Let's just highlight some terms that may be of interest for future problem sets. Again, this is the deadweight loss, and the consumer surplus is going to be given by this area of this triangle. And finally, the producer surplus or the monopoly surplus is going to be given by all of that. We have just seen that monopolistic markets generate very different allocations and less desirable allocations than competitive markets. A very basic question follows, which is, what are the characteristics of markets that make them have monopolistic competition or just one firm servicing the market, as opposed to markets that have many firms and perfect competition? What I'm going to do in this video is go through several of the main reasons that lead markets to have monopolistic competition. And the first one is the presence of economies of scale in production. Let me elaborate. Now, we know that competitive market forces, the same competition that we have seen before, with one twist in which there is entry and exit of firms, which is something more complicated and we have not studied, but it's quite intuitive, the results that I'm going to use. So with entry and exit of firms generates the following, which implies that the number of firms in the long run is approximately equal to the amount produced in equilibrium in the market in the long run, after there has been competition and firms have had a chance of enter and exit, divided by what we call Q mean ATC. Just to remind you, if you have a firm that has this shape of the average total cost function that we saw when there were economies of scale in production, this quantity at which the average total cost is minimized is the Q mean ATC. And that is a very special point because it's the point at which the cost of production is minimized, which of course has to be the case that production takes place at that level and at optimal allocation generated by a market. So what are we going to say? From this is going to tell us how competition is going to push the number of firms to look like in the long run. In particular, if you look at this ratio, if one firm can serve the entire market at its cheapest minimal average total cost, then there will tend to be monopoly. Otherwise, there will tend to be many firms. So let me do this with an example, with a graphical example, just to elaborate. So suppose you have a market that looks like this. Let's say the demand function looks like this. Okay? And I'm going to draw two situations. One in which, in the long run, there is perfect competition. So suppose that the average total cost curve of the firm looks like this. This is the average total cost curve that minimizes that. And this is, let's say, the Q mean ATC in this case, let's say it's 100. And we will have something else that we didn't study, but in this case, let's say that the equilibrium price we can derive will be in the long run, will be that. So let's say that we know that the quantity demanded in the long run will have been, let's say, 1,000. Then we know that in this case, the number of firms in the long run is equal to 10. Now suppose, in contrast, that we were in a situation in which the same market forces would have led us to a situation in which one single firm had an average total cost curve, let's say like this, okay, in which one single firm at its minimum will service all of the demand? Well, in this case, what we have had is that the price in the long run will have been this. The quantity in the long run will have been this, let's say 2,000. And the number of firms in the long run will have been 1. And by the way, this is also equal to the equilibrium in the long run. Now, let me emphasize two things. First is, I'm putting the equilibrium prices here in the long run, and I haven't taught you how to derive them. You are not responsible for knowing this material. I'm just trying to pass you an intuition for how the economies of scale affect the number of firms, not teaching you how to solve long-run equilibria. We're not doing that in this course, so don't worry about those details. The second thing is that we are assuming in this explanation that the monopoly somehow is competitive. We are assuming what will be the price and the market forces in competition will lead to one firm. In this explanation, we have assumed that this firm will behave as a competitive firm. Of course, that will not be the case. As the number of firms goes down, when it becomes very small, they will behave as imperfect competitors. But the purpose of this diagram is not to show you what happens when there are very few firms. That's the purpose of all the material that we're developing in Unit 7 or 8, is just to show you that it's a counterfactual, to show you that market forces, even under perfect competition, as the technology changes and the average total cost function switches from this to something like that, will tend to kick firms out of the market and therefore lead us into the realm of imperfect competition and monopolist. Now, there are goods in which the benefit of consuming QI, of consuming Q, depends on what others consume. Let me call that on Q minus I, that is others' consumption. So in particular, not only depends, but it increases with Q minus I, okay? So in particular, there are goods, let's say like Facebook, software, and movies, things like HBO, in which the value of consumption for the individual depends or increases with how many others are consuming. Why? Because it makes usage easier, more pleasant, you can derive more value from it, etc. When that is the case, there will tend to be one monopolist, because one single firm will tend to dominate the market, because the intuition is there is a virtuous cycle for the firm. The more users it attracts, the more valuable it becomes from its customers, and that gives it a competitive advantage that allows it to attract more and more customers. So eventually you converge to monopolists in these cases. Now, there are some industries in which production of the good that is sold requires the usage of a good, of an input of production that is very rare. And if that input of production is owned by a single firm, that gives a monopolist, the monopoly power over the market. So let me give you two examples of this. One is the Suez Canal. Now, the service that is being sold there, or the good, is transportation through the sea of bulky products. But it happens to be the case that to really make the transportation efficient, you have to pass through the Suez Canal that is owned by a particular set of countries there that have a lot of the ability to veto passage through that canal. And if that canal is owned especially by one company, they have monopoly power on that transportation market, at least for routes that have to pass through this part of the world. Another example is rare minerals. So it turns out that in the modern production, for example, of electronic equipment, some rare minerals need to be used that are found in a very, very small number of countries, and that the public companies of those countries are given monopoly rights over the extraction and export of those minerals. That one or two companies have almost monopoly power in that market. Another reason why monopolies arise is not due to any underlying economic characteristic of the market, like the ones that we have seen so far, but simply because the government assigns those monopoly rights to a particular firm by passing a law that says nobody can sell in this market. Now, there are two reasons why this government creation of monopoly rights are done. One is patronage, which is basically trying to give a transfer of cash to your political supporters or your family, and that is done by assigning monopoly rights, because as we have seen, monopoly rights can be very profitable. The second reason why these monopoly rights arise through the government is as an incentive for firms to engage in costly infrastructure expenses, in costly infrastructure investments, for example, roads. So suppose that you are a country that is really cash-strapped. You cannot really, your government finances are not in very good shape, and it's hard for you to go and borrow to build the roads that your country needs. One of the things that you could do is tell a company, come to my country, build these roads, and I will give you monopoly power, let's say, for 25 years. That could be profitable for both sides, for the government because you will get the roads built and then it will have them in perpetuity, for the company because those monopoly rights for 25 years can be very lucrative. The final reason why monopolies are right have to do with patents and copyrights. So here is a story. In many markets, something called the innovator's dilemma arises. What is the innovator's dilemma? The innovator's dilemma is that in these markets, there is expensive, think of a large expense to design a good, but then the marginal cost of production is approximately zero. And not only that, the recipe is easy to copy. Okay? That means that you can have a firm invest billions of dollars producing a product, and then after it's on the market, any person can buy it and replicate the formula at basically very low marginal cost. Why is there an innovator's dilemma? Because the firm would like to produce the product. If it has high value for the consumers, it can make a profit, but the moment it produces without any extra protection, others will copy and they will not be able to recoup the investment. Okay? So examples of this are software, movies, medication. By the way, all of these goods that are heavily produced in the United States, and that's as a side note, since there are many international students, why the United States cares so much about this topic. Many of these goods have these production functions that looks like a semi-fixed cost plus mu of q, okay, that we have been looking at. Now, what is the solution, the best solution that economists have come with to fix this problem are patents and copyrights. And basically what this says is that give monopoly power to the innovator for N years to recoup the large expense. Then he will be able to recoup the large expense, and the incentive to innovate will not disappear. Of course, there is a fundamental tension here, fundamental trade-off, which, by the way, is being debated in the United States very extensively right now in the right circles, legal and economic circles. And there is one between innovation and efficiency exposed. We know that if we grant monopoly power to the innovator, there's going to be a deadweight loss exposed because he's going to extract monopoly profits. That's a loss for society. On the other one, if the products are never produced, there is also a gain from granting that monopoly power, so the products are granted. And the question is, the fundamental question that a good patent system needs to design is, which are the properties of the goods and of the market that make this trade-off pointing to the direction of granting patent of copyrights, and if so, for so long, and of what characteristics, versus goods in which those patents and copyrights should not be granted. The reason this is a very hot debate in the United States lately is because we are in the middle of what are called patent wars. Companies are suing each other for what seem like really frivolous lawsuits that really don't seem to have anything to do with a true innovator's dilemma. I urge you, if you find this interesting, and I know there are many students involved in the computer industry, to take more advanced economic courses. This is a course all on its own and incredibly, incredibly important and interesting. Consider a market with monopolistic competition without price discrimination that has the following characteristics. The aggregate demand function is given by 100 a squared divided by p squared, where a is a positive constant. The cost function of the monopolist is given by a semi-fixed cost plus mu q, where mu is a positive constant, remember the semi-fixed cost is a cost that has to be paid if the consumer wants to produce a positive amount but is zero otherwise, and then after that semi-fixed cost is paid, the monopolist can produce, in this example, at a constant marginal cost, mu. Question: what is the smallest value of the semi-fixed cost at which the monopolist produce zero? Now, I've written here the data of the problem just to simplify your memory load. Let's solve the problem. The key thing to notice in this problem is that the monopoly has two choices. So the monopolist can be produce zero, which implies that its profits are zero because it doesn't pay the fixed cost and it doesn't get any revenue or pays any cost of production, or it can set up the best that it can, conditional on entry. So that's a positive greater than zero, and that is going to do this only if and only if, so set Q mon price, if and only if the profits that it leads to are greater than zero. Okay? Which is can achieve by producing nothing. That's the key idea of the problem. Now let me solve it for you. Well, we know what it does if it produces zero. Let's look what is the best that it can do if it produces a positive amount. So we know that its total revenue as a function of Q is going to be equal to the inverse demand function of Q times Q. Substituting from this and doing the algebra, this gives us 10a square root of Q. And that implies that the marginal revenue of the monopolist is equal to 5a divided by square root of Q. Now we also know that the best that the monopolist can do, conditional on entry, is given by marginal revenue equals marginal cost. Now the marginal cost is constant and equal to mu, so this is equal to 5a square root of Q. This is equal to mu, and this implies that the quantity of the monopolist, conditional on entry, is equal to 25a squared and divided by mu squared. And also, if you go back and substitute in the inverse demand function, you're going to get that the price of the monopolist, conditional entry, is going to be equal to 2 mu. Now, given this, we get that the profit of the monopolist in the case of positive production is equal to the quantity that it produces times the price that it gets per unit minus the total cost of production, which are the semi-fixed cost, plus Q monopolist plus times mu. And if you do the algebra, you get that this is equal to 25a squared divided by mu minus the semi-fixed cost. Now, we know that the monopolist produces a positive amount if and only if the profits of the monopolist in that case are greater than zero, and this is greater than zero if and only if the semi-fixed costs are greater than that number. So this is the smallest semi-fixed cost with the quantity of the monopolist greater than zero. That's the answer. Here's a problem designed to put into practice what you have learned about the price discriminating monopolist. So suppose that you are a monopolist, you have monopolist rights over a popular band, rock and roll band, and you are deciding whether to put out a concert, and you have the following data. The band has 20,000 fans. Half of them are men and half of them are women. And the men are willing to pay $100 per concert. The women are only willing to pay $50 per concert. And suppose also that the gender is perfectly observable to you. Here comes a question. Would you do the, one more thing. The cost of the concert is 1.2 million. Question, would you do the concert if allowed to price discriminate? And would you do the concert if not allowed to price discriminate. Okay, so would you do it under either of those two circumstances? And let me give you two hints. Hint number one is use your common sense. If you use your common sense, this problem is very easy. And second, when applying what you just learned about the price discriminating monopolies, do it carefully by thinking, because in this case, the demand function are step functions, not discontinuous functions that we will use in the video lecture. This problem is actually easier than the theory that we developed on the video lecture. So let's solve the problem. First, let's look at the case of price discrimination. And here, let's look at the price of without price discrimination. Now, notice that with price discrimination, the best you can do is charge the men and the women each their full value. So you're going to charge the men $100 and the women $50. Now, at that price, you are indifferent between attending and not attending, but you can assume that they attend to the show. If that bothers you, assume that you charge them 99.999999 and 49.999999, and everything is an approximation. Now, this implies that the profits or the revenue, the total revenue, is equal to 1.5 million, which is greater than the 1.2 fixed cost or semi-fixed cost of the show. So this implies that you put the show and you have a profit, so with price discrimination, of 300K. How's easy? Now, what happens without price discrimination? This one is slightly more complicated, but not if you think carefully about one thing. I'm going to draw a line here that has the value per ticket at $100 for men and at $50 for women. And the question is, what's the best that you can do without price discrimination? Okay? Well, let's think about it. You're clearly not going to want to charge anything down here, because you can do better charging 50. You're also not going to want to charge anything in the middle, okay? Because if you charge, let's say 51, you lose all of these customers, but you could charge more for the ones that remain. And you're not going to charge anything above, because then you don't get any customers. So the only candidate prices are 150. So let's say what you get with 150. So if the price is 50, then everybody attends, and this implies that total revenue is equal to 50 times 20,000, which is equal to 1 million, and that implies no show, and profits with equal to 0. Why? Because the total revenue you can get exceeds the fixed cost. Now, what happens, or semi-fixed cost, sorry. What happens if the price is 100? When in that case, only these people attend, and you still get total revenue equals at 100 times 10,000, which is equal to 1 million. So implies, again, no show, and the profit is 0. In other words, we get a show with price discrimination, but we don't get a show without price discrimination. Besides, since showing you the solution to the example, let me emphasize that this provides an illustration of why price discrimination sometimes can be desirable from the point of view of social efficiency. The value of this concert is 1.5 million for the population as a whole, and it only takes place when the monopolist can engage in price discrimination, but not without it. The goal of this problem is to get you to think hard about the nature of the equilibrium with the imperfect price discrimination that we just saw in the case in which there are heterogeneous consumers. The general question is hard, so we're going to look at a simple case. There is a monopolist that uses imperfect price discrimination with a policy of the type that we have seen, which is P1, Q bar, P2. It's literally what you just saw in the previous video. Now, we're going to assume that there are two types of consumers. Okay? 100 of them have the following benefit function. For the first good is $20, sorry, So it's here. And for the second good, it's $15. And for any additional good, it's at 0. Notice that the goods are indivisible in this case. So if the consumer gets 0, he gets 0. If he gets one unit, he gets $20 of benefit. For the second unit, he gets an extra $15, and then for any additional units, he gets 0. The other 100 types have benefits that look the same but with different numbers. Basically, they are at 10 and at 5. So for the first unit, they are at 10. For the second unit, they are at 5. And all of the other ones are at 0. Now, the monopolist has a marginal cost of production equals to 0. Yes, 0. And the question that I have for you is, what is social surplus at the equilibrium outcome? Here is an easy way of thinking about this problem. Let's look first, or begin with the best that the monopolist can do, or the best solution for monopolist, given that only type 1 buys in equilibrium. So remember that type 1 looks like this. The first unit, the second unit has a value of 20. The second unit has a value of 15. And every additional unit has a value of 0. Okay? Now, I claim that in this particular case, the monopolist can get the full surplus, the full social surplus, with setting a P1, a price of 1 equals to 20, a price of 2 equals to 15, and a Q bar equals 1. And in this case, it gets a producer surplus equal to the social surplus equals to 100 times 35, which is $3,500. Now, it's easy to see why this is the case. This is a price schedule that says you have to buy like this, the first unit at this price, after that at the lower price. The consumer is indifferent between buying nothing and buying the 2 units, and the producer gets all of the surplus. Now, this is something that the consumer can do. Now, if there is a better solution, it has to be the case that it involves also extracting surplus from the other consumer and a higher profit than this. So now let's look at the best solution for monopolists given that that type 2 buys something. And there are 2 cases that we want to look at. So in case 1, the other person just buy 1 unit, type 2. And in the other case, type 2 buys both units. Okay? Now, let's see what happens if the consumer, in the best solution for the monopolist, in which the other consumer only buys 1 unit. And to remind you, this was type 2. The prices, the benefits for type 1 were at 10 and at 5, 1, 2, and then 0, 0, 0, 0. Okay, now clearly the goal of the monopolist is to keep this price P1 as high as possible to extract also as much revenue from type 1, sorry, this is type 1 and this is type 2, as possible. The best they can do then is set P1 equals 10. That leads type 2 to buy 1 unit, but not the second unit, and it still extracts some revenue from the first type who buy both units. In this case, the producer surplus is equal to 100 times 10 plus 100 times 20. Let's see why is that. 100 times 10 is the revenue that it gets from this consumer which only buys 1 unit, so this is from type 2. And 100 times 20 is the fact that it sells at $10 2 units to types 1, and that gives you a total producer surplus of $3,000, which is less than the $3,500, so this cannot be a solution. Now let's look at case 2. Now again, in case 2, the best solution for the monopolies involves having the price 1 as high as possible while having the constraint that this guy buys 2 units. I hope it's easy for you to see that that looks like charging 15 and 0. Setting a price 1 of 15 and a price 2 of 0. That makes this consumer indifferent between buying nothing and buying the 2 units, and keeps price 1 as high as possible so that the other consumer, so that the type 1 buys, you can get as much surplus as possible from type 1. Now, so this is pi 1 equals 15, price 2 equals 0. What is the producer surplus in this case? It's going to be equal to 100 times 15. This is from type 2. Remember, they get nothing from the second unit because it's at 0, plus 100 times 15 from type 1, because they sell still both units, but they only get a revenue for the first one. And again, this is equal to $3,000, which is not as good as the solution in which only the first consumer buys. So what we get is only the first consumer buys, is recruited to buy at the best possible solution, and the monopolies extract all of the social surplus from that consumer, but none of the social surplus from the second consumer. And although this is not part of the question, notice that the solution is not Pareto optimal. Why is that the case? Because with a zero marginal cost, both consumers should be consuming both of their units, and that is not the case. The goal of this practice problem is to get you to understand the differential impact on consumer well-being that regulation and optimal subsidies can have. So look at a market that has the following properties. Aggregate demand is given by 1,000 minus P. There is a monopolist that cannot engage price discrimination, any form of it. And has a cost function, C of Q equals to Q squared divided by 2. And importantly, the monopolist is owned by individuals who are not consumers. So by someone else, perhaps a foreigner or something like that. Now the question I want you to answer is, compute the difference in consumer well-being at the optimal subsidy, and by that I mean the subsidy that restores the Pareto optimal level of Q and is financed with lump sum transfers, minus consumer well-being at the optimal regulation policy that we also have just studied. Compute this. The solution to the problem is straightforward if we think about it in just the right way. So here I'm going to look at the optimal regulation policy, and here I'm going to look at the optimal subsidy policy. We know that both of them restore the Pareto optimal level of production in good Q, but have different properties. Let's look at the regulation first. We know that the inverse demand function is given by 1,000 minus Q, that the marginal cost curve is going to be given by Q, and we know that the optimal policy, for example, the optimal regulation is going to involve a price that leads to the Pareto optimal. So let's say a price to the monopolist equals to 500, at which point the monopolist produces the optimal amount. Now, that policy doesn't entail any taxes or transfers. The consumers buy at that price, so therefore the well-being of the consumers is proportional. The well-being, consumer well-being is proportional to that area, which is equal to a half of 500 times 500, which is equal to $125,000. Now let's look at the optimal subsidy. We're going to do a similar diagram. We have exactly the same inverse demand function. Now the marginal revenue curve is going to be like this, and it's going to cross at a 500 there. This is 1,000 where the cross is there. And we have that the marginal cost curve as before. Let me redraw it to make it look better. You know that the marginal cost curve is just Q, it's just the same data as there. Now, and we know that the government wants to lead again to the quantity optimal, which is just equal to 500. To do that, it needs to give a subsidy equals to this distance. And what is that distance? Is 500. Because remember, marginal cost and marginal benefit equals 500. We just saw it there at the optimum. Now, what is going to be consumer well-being here? Well, we know that this is going to be the quantity the monopoly chooses. That's going to generate this market price. So consumer well-being is going to be equal again to that triangle, which is 125,000. But we also need to subtract the amount of taxes that are raised from the consumers and given to the monopolies, which is given by this area. And that area has an area of 500 square. So we get that the total consumer well-being there is minus $125,000. Therefore, the difference is minus $250,000. Consumers are much worse off here than there because of the tax that they need to transfer, the tax revenue need to transfer to the monopolist. In the model of the monopolist that we have developed so far, the monopolist takes into account the effect of its actions on the price and therefore affects the prices, but is restricted to charge the same price to everyone for every unit that they purchase. In this unit, we're going to study circumstances or markets in which the consumer can do even better by engaging in what is called price discrimination. And what is price discrimination? So a definition is a situation in which you can charge different prices to different consumers despite identical production costs. So it's a situation in which you discriminate on the charges, on the price to consumers, but it's not because it costs you differently to service them. And to understand this better, let's look at two examples. So one example are senior discounts at the movies, which are very common in Europe and in the United States. Is this price discrimination? The answer is definitely yes. Projecting the movie to a senior citizen or projecting it to a 15-year-old costs the same. So as you will see, the monopolist engages in these kinds of pricing rules because it enhances its profits. Now, what about charging extra to deliver a pizza up the mountain? So suppose you live in a city that has a valley and then it has all of these houses in the mountain, and Pizza Hut charges extra to deliver the pizza up the mountain. Is that an example of price discrimination? The answer is no, because it's tied to an excess production cost of servicing those customers. Now let's look at the basic assumptions of this model of price discrimination. It's going to be a simple one, not the most general one, to keep it tractable. So we're going to assume that there are two types of consumers. There are NR, this is a number, red consumers, and we will denote the inverse demand function by this. And this is, by the way, the inverse demand function for each red consumer. And then there are NB blue consumers, and we will denote their demand function by this. We assume that there are no resales, and you will see why that is important in a second. And this can be because the good that is served is a service, like watching a movie, so you cannot resell it, or because there are laws against it, or because the monopolies can prevent it. For example, you may be able to prevent the sale of goods in which they really require a warranty or service from you by simply denying warranty or service to goods that have been resold. Now, we assume that the monopolist can perfectly observe type. And what it does is it charges, or it offers, a price schedule. This is a new concept. Pi C of Q to each consumer Q. To each consumer C, sorry. So the idea is that if you're a consumer, you're offered this price schedule, and then your problem becomes to maximize, so this is a consumer problem, over Q, the benefit that you get over Q minus the P of C of Q. In other words, this Pi C of Q tells you how much you have to pay if you buy Q units. And the key thing is that this function is indexed by C, so it may be different to different consumers. Now, the monopolist has a cost function that has decreasing returns to scale with no fixed cost or semi-fixed cost. And the key thing is that what is the monopoly problem? The monopolist problem becomes to choose the function that it offers to red consumers, or the price schedule, and to blue consumers to maximize its profits. Of course, given that the consumers are going to react by solving this problem. Notice that this problem looks extremely hard at first sight because you need to maximize over the functions that you're going to offer to the consumers so that they themselves can react and do the best in order to maximize profits. But if you use a little bit of economic logic, as you will see in the next slide, this actually becomes very easy. This is the key for how to solve the problem, so it's important that you understand it well. The key remark is that the monopolist can extract all consumer benefit at any quantity produced or sold to the consumer Q. And let's see why that is the case. So take any consumer, this is consumer C, and suppose that his or her inverse demand function, let's say, looks like this. And remember, this is equal to the marginal benefit of the consumer. We've developed this in great detail before. Now, suppose that the monopolist wants to target this quantity. It wants the consumer to buy this quantity. So this is desired purchase by the monopolist. What can the monopolist do? So it can do many things, but suppose, for example, that it offers the following schedule to the consumer. The function pi looks like this, then it jumps here to the same level there. So suppose that it offers to consumer C this price schedule. What is the best thing that the consumer can do? This is the best that the consumer can do is exactly to do this. This is the best response by the consumer given the price schedule. Why? Well, notice that at any quantity up to this, the consumer gets zero net benefit. It's because it's paying a total price equal to its total benefit. But if it goes above it, it has to pay a price that exceeds that, so it's never going to be above it. It's indifferent between all of this, so it can pick that one. If this particular approximation bothers you, assume that all of this red line is epsilon below, and we get the same answer. But in economics, to avoid those epsilons, we normally assume that whenever there is an indifferent, we can resolve it in the favor of the modeler. Now, notice that this generates a class of potential pricing rules, each one with a different Q. So here is one, another one could go a little bit lower and then jump all the way up to that intersection and keep going. So we can index this class of price schedules by Q. And the idea is that any of them goes down along the inverse demand function up to Q, and then they jump like this. Now, in the previous board, we have seen that the monopolist can get any consumer to consume any amount that he wants while extracting all of his benefits. This implies that we can rewrite the monopolist problem as follows. Maximize not over functions but over the quantity that indexes those functions for both red and blue consumers of what? The total revenue that he gets from selling to those consumers, but he's extracting all of the surplus that is equal to this, i.e. the surplus that the consumers get from those sales, minus the total cost of production, which is equal to C of NRQR plus MBQB. Clearly, this is identical to the Pareto optimization problem. In other words, because the consumer can extract all of the surplus, its profit maximization problem becomes the Pareto optimization problem. And not surprisingly, it has the same first order conditions for Pareto optimality, which are NR B prima of R equals to NR C prima, are N B B prima of B equals to NB C prima. That is very, very remarkable. And what is going to be the solution is going to be that the QR that the monopolist is going to choose is just a function of the type that we have seen that has the every consuming R consuming at the optimum, and the same thing for every blue consumer. So both functions are going to look like this. If this is the inverse demand function of type I, the function is, and this is the quantity optimum for type I, the function is going to look like this at the solution. Now, several properties of the solution are worth emphasizing. First, the allocation is Pareto optimal. You have a monopolist, he couldn't care less in principle about generating Pareto optimal allocations, but because the best he can do is extract all of the surplus, and that leads him to internalize the full well-being of the consumers, he ends up indirectly maximizing efficiency. Second, producer surplus is equal to social surplus, and consumer surplus is equal to 0. Because the producer, the monopolist, extract all of the benefit from the consumers, they get no surplus. Third, the distributional properties of the equilibrium depend on the distribution of firm ownership. So, is in particular, if everybody owns an equal share, then you get a Pareto optimal allocation with very nice distributional allocations. But if the distributional of the shares of the monopolies are really concentrated, then you get very poor distributional properties. And the fourth thing is that the price schedule is not uniquely defined at the optimum. The quantities that the consumers consume are, but not the exact price schedule. Let's see why. So suppose that you have, for example, for the reds, you have that this is a demand function for a typical red consumer, that this is the optimal quantity. We have seen that this function that looks like this maximizes the quantity of the producer, But so does a function that looks like this, and one that looks like this, etc. So the price schedule, especially after the Q star, is not uniquely defined. Now, the model that we have developed up to this point in this lecture is an idealization, because if you think about your experience in the real world, you are not offered price schedules by firms, even by monopolists. You are offered prices and quantity discounts and things like that. So a very natural question is, how is this type of price discrimination implemented in practice? And the big idea that I want you to get out of this is that the perfect price discrimination is not possible, because it requires a lot of information, and it's also approximately illegal. There are many ways in which it breaks laws in many countries, but there are good approximations in practice. And let me give you just one example of many that I could give you. So in the United States, and I think in most over the world these days, when you buy a product in the store, it gets scanned. And in most supermarkets, you get these cards. They track who you are either with these loyalty cards, discount cards, or with your credit card. And basically, the supermarkets build a model of you, of what type of consumer you are. They put you in categories, and then they sell you discounts. They send you these coupons, and they give you Antonio-specific discounts. If you buy this many extra units, by, for example, a can of this size will give you this discount. If you buy this extra unit, we'll give you a discount of this amount. All of those efforts by consumers, by firms, to target, to offer specific discounts to specific consumers are one of the many ways in which the firms spend a lot of computing power and a lot of data collection trying to approximate this theory of price discrimination that we have seen. An open question that I don't know has been settled yet empirically is, how close do they get? I tell you I don't know the answer today, but I can tell you this, that as more and more data gets collected, unless more and more legal restrictions get imposed, it's natural to expect that the firms will be able to approximate this solution more and more. Now, sometimes monopolists would like to engage in full or perfect price discrimination, but it's not possible for them, because what it would require to accomplish it is illegal, or it would require information that they don't have. In such cases, they engage in more limited forms of price discrimination. And what I'm going to study with you in this video is a simple form of imperfect price discrimination. Let's call it a simple policy or price schedule. Simple price schedule for imperfect price discrimination. And those schedules have the following form. They are characterized by three numbers: P1, P2, and Q bar. And the idea is like this. This is Q bar, this is quantity, and this is the marginal cost for consumer per unit. And the idea of this is that the consumer can buy as many as he wants at price P1 up to Q bar, and then any additional units are bought at a lower price P2. This is a simple class of price schedules that the producer could use, and if you think about them intuitively, they look like a quantity discount. After you have bought Q bar, I'd like you to buy how many you want at a cheaper price. Now note, if price 1 equals to price 2, this looks like regular monopoly without price discrimination. So it nests the basic first model of monopoly that we studied without price discrimination as one special case. And we're going to assume two other things in the simple model. One is that the cost function is just constant returns to scale without fixed cost or semi-fixed cost. And the next thing is, just to make it simpler, is that there are C identical consumers, each with an inverse demand function given by PD of Q. This is going to be the demand function per consumer. As before, the solution to the problem is going to entail finding the best constraint price schedule that the monopolist can use to maximize its profits. But in order to characterize this, it's useful to start looking at the consumer problem. And in particular, I'm going to describe to you what the solution to the consumer problem looks like in 4 separate cases. In all of them, we're going to assume we're going to look at exactly the same inverse demand function for a typical consumer. Okay, these are the same. And now let's ask, how does the solution changes? So in one particular case, maybe that the price schedule looks like this. The kink is below the inverse demand function. In this particular case, the best that the consumer can do is pick this. Now, why is that the case? Well, think about it. Every unit up to here has a marginal cost of purchase, which is this, and then this, lower than the marginal benefit, which is given by the inverse demand function. So the consumer should keep producing all the way to here. Now, what if you have something that looks like this and never crosses? It should be obvious to you by now that the optimal is 0 because the marginal cost of purchasing exceeds the marginal benefit at any quantity. So these are the trivial cases. The more interesting cases are these two. Suppose that you have something like this that crosses the inverse demand function like this. Let me label these areas A, B, and C, and these quantities Q lower bar star and Q upper bar star. Then I claim that the consumer chooses Q lower bar star if this area B is greater or equal than C, and in contrast it chooses Q upper bar star if the area B is less or equal than C. Let's see why. Now, what happens if the consumer jumps from this point to this point to this point? Well, the jump from this point to this point entails a loss because every unit between here and here has a cost that is higher than the marginal benefit that it generates. However, if the consumer reaches this point and then keeps buying, let's say to reach that point, it can buy units, these many extra units from here to there at a marginal cost that are lower than the marginal benefit. So the key question is, what is the impact on the total benefit or surplus of the consumer from jumping from this point to this point? If the area B exceeds the area C, then that jump is not worth it and the consumer should stay there. If the area C exceeds the area B, the opposite is true. Now, the final case that is interesting is what happens if we have something like this. And let me call these areas B and C. Well, the case of interest here is this, Q star, and I claim that the solution here is 0 if the area B is greater or equal than Z, and Q star if the area C is greater or equal than B. And the reasons are identical, so I'm not going to repeat them. Now, given what we have just learned, it's easy to characterize the solution to the monopolist problem and the equilibrium allocation. So result with identical consumers, the monopolist gets all of the social surplus and the allocation is Pareto optimal. So let's see why that is the case. Look at the diagram of a typical consumer. It looks like this. Inverse demand function. We also have the marginal cost equals mu. We know that the Pareto optimal allocation, this is the amount that should be produced and given to that consumer or per consumer. Now, suppose that the producer, the monopolist, chooses a schedule that looks like this. Where this kink is at a Q bar equals to Q optimal divided by 2. Then, and the prices here is P1 equals PD of 0 and P2 equals mu. Let me call this A and B. Then, what do we know? We know that with this linear demand function, area A is equal to area B. We know that all of the producer surplus, all the social surplus, which is equal to this triangle, goes to the producer. We know that the individual is indifferent between consuming zero and consuming the optimal amount, so might as well consume the optimal amount. So we know that the allocation is also Pareto optimal. Now notice the key intuition of the quantity discount here. I charge an excess amount to the consumers for the first Q optimal over 2 units, and he loses all of this, but he keeps buying because he can make that up by buying these extra units at a discount. And that's enough for me to know that he's going to end up choosing this march in equilibrium, the optimal amount, and to be able, as a monopolist, to extract all of the surplus. Now, important, result doesn't extend, this doesn't generally hold with heterogeneous consumers. And solving this problem in general is difficult, but the next practice problem is going to allow you to understand why, to get an important intuition in a simpler case. Now we're going to look at another form of imperfect price discrimination that is very common in the world. Suppose that you have a firm, let's say, that has a centralized production facility that sells to multiple markets. Let's say market 1, market 2, market 3, etc. Okay? And what this firm is allowed to do legally is to charge a price PI for market I. It doesn't engage in other more sophisticated forms of price discrimination, but it charges this price for market I, and C of Q is its cost function. Now, what is the problem of a firm? It becomes to maximize over all of the quantities. Let's say there are M markets. The revenue in each market, which is this is the inverse aggregate demand function for market I. So it adds the revenue I get from all the markets, given how the quantity chosen in every market is affecting each price, minus the total cost of production. And if you think about it for 2 seconds, what you get is that at the solution, what you get is that the marginal revenue for each market I has to be equal to the common marginal cost. In other words, the firm is treating each market intuitively as a single market, taken as given the total marginal cost, and then picking the level at which marginal revenue equals that marginal cost. It's doing this market by market in some sense. It's a simple graphical illustration for the case in which the marginal cost is constant. So suppose there are 2 markets. Let's say on one, this is market 1, and this is market 2. And let's say that the demand function looks like this in one case, and let's say it looks like this in the other case. And let's say that the marginal cost is here. Then what we do is, as before, the monopolist is going to compute the marginal revenue in each market. Which, remember, we've seen before, for the linear case, it's just something with twice the slope, linear 2. And what it does, it picks this quantity in market 1 and this quantity in market 2. And that entails charging different prices. This price in market 2 and this price in market 1. Now this is very intuitive. Let me emphasize that this type of price discrimination is very, very common, and there are many goods that are produced at one location and sold all over the world at different prices, and it's difficult to attribute the price differences to shipping costs. This is evidence of this type of price discrimination. Congratulations, you've made it through Unit 8, and we are almost done with the course. Now, I want to summarize the key lessons from this unit because they are very, very important to advance our understanding of the outcomes generated by markets. Now, here we look at the case in which there are F greater than 2 but less than many firms, okay? And we look at two different models of what happens in markets in that case. One is the oligopoly model. And the key feature of this oligopoly model is that the firms sell identical goods. And then we saw the monopolistic competition model, in which the key feature is that there are differentiated goods through branding. Now, importantly, remember, these goods are differentiated in the perception of the consumer, but not in their experience utility. So they are actually the same good. It's just that the firms are able to convince the consumers that they are different. And what we saw in the case is that the comparison of these two models led to very stark different results. In this case, we get convergence to competitive case and full efficiency quickly with F. So as F increases very quickly, we saw, for example, by the time we have 10 firms, you're almost in the full efficient case. And we've seen that this is a very important result because it really shows that the competitive market is a good approximation even with small numbers of firms. In the monopolistic competition, that is not the case. No convergence. Okay? And there are also large inefficiencies. So this is an important result in my view for two reasons. First, it shows you that the competitive model again is a good approximation for markets in which basically the consumers perceive the goods as substitutable, but that is not for markets in which marketing and branding is very powerful. Are we talking perhaps about sodas or sneakers or fashion or things like that? In that particular case, the competitive model is not even close to being a good approximation. Hi, welcome to Unit 8. In this unit, we're going to continue our study of what happens in markets with imperfect competition. In the previous unit, we studied the case of monopoly, in which there is only one firm, and we saw what happens in those markets. In this case, we're going to look at the case in which there are more than one firm, two or more, but not a lot of firms, so perfect competition doesn't apply. And we're going to do this by studying two different models. One is a model called oligopoly, in which the firms sell identical products and have some market power, but not full market power. This characterizes many markets, for example, the computer manufacturing market or the oil petroleum production market. Then we're also going to look at another model called monopolistic competition, in which there are also a small number of firms competing with each other, but in this particular case, they can make branding or marketing experiments to try to convince the consumers that their goods are not equal to the goods of the other, that the brand is better, and that they should buy it. And we'll see what happens in that case. Now, one very important question that we're going to be doing in this section is asking ourselves how many firms are enough to approximate perfect competition. We know that there is never an infinite number of firms in the economy. Is 10 enough? Is 5 enough? Is 20 enough? We'll ask those convergence questions to the competitive case very, very carefully. Now, the unit is also going to give you a new insight about the role of marketing and branding in the economy that I hope you will enjoy. So without further preamble, let's look more at oligopoly and monopolistic competition. Now we're going to extend our model of imperfect competition to address a very basic question and a very interesting one, which is why are there brands in the market and what are the effects in competition? So consider the market for cola type sodas. Companies like Coke and Pepsi invest enormous amounts of money in marketing to try to get you to convince you that the two products are different, even though they're basically both caffeinated sugary water. Does this matter? How does it affect consumer well-being? How does it affect the outcome generated by the market? These are the questions that this model of monopolistic competition that we're going to study addresses. So here is the idea, a simple, there are various versions of the model. I'm going to show you the simplest one, and here is the idea in a nutshell. Suppose that there are at least two firms, that the aggregate inverse demand function has this linear form that we have been using, and that the firm's technology looks like this. They produce Q, the good, every unit of good, at constant marginal cost of mu dollars per unit. However, they have two choices. They can either, in addition to how much to produce, they can either pay a fixed cost, a semi-fixed cost of F dollars to create a brand. And what this fixed cost is, it gets consumers to think that these units that they produce are of this special brand of type firm, of the type that this firm produces, or they can not pay it and they don't have a brand, and then they can set Q equal to 0. So this model of monopolistic competition, the simple version, is a model in which only branded goods are sold. Now, the key assumption of the model is that brands split the demand equally and are monopolists within their share. Now, I will derive the math for you in a second, but let's think about the key idea. The basic idea is that if there are two brands, let's say, each of them gets half of the consumers and half of their demand, and somehow the branding expenditures, this semi-fixed cost, convinces the consumer that these are unique goods, that these are the only goods that the consumer can possibly buy. And since that brand is unique to that firm, and that firm is the only one who sells that brand, they are a monopolist within that market. Now let's solve the model. So since the firms split the demand equally, we need to characterize what is the demand that they face. But before, I have to define this variable, which is called in, which is equal to the number of firms that create a brand and therefore produce a positive amount. Then if this is the number of firms in, then what we're going to have is that each firm faces demand P max minus in times MQ. Let me denote this by I to simplify the notation. And one way of thinking about it is that if this is the demand for the full market, basically every one of the brands in gets an equal share. So these are equal shares, and there are I of them. I equal shares. Now, we know that each firm faces the demand and acts as a monopolist, so that implies that each firm sets marginal revenue equals marginal cost within its demand. Now we know that the marginal revenue for something like that looks like P max minus 2IMQ, I've seen that many times, equals mu, which implies that the quantity produced by each monopolistic competition firm that is in the market is going to be equal to P max minus mu divided by 2IM. Now, this also implies that the total quantity that is produced, which is just I times QMC, is equal to P max minus mu divided by 2M, which notice that is equal to the quantity that would be produced if one single firm would be a monopolist in this market. And this also implies substituting back into the aggregate demand function that the total price, so the price in monopolistic competition is going to be equal to the price in monopoly, and this is equal to P max divided by 2 plus Q max divided by 2. Now, let's compute what is the profit for a monopolistic competition firm that is in, which is basically going to give you equal to the profit of the monopolist, since we know that the total quantity is equal to the monopolist, divided by the number of firms, minus the that are in, minus the fixed cost that you need to pay. And if you do the algebra, this gives you P max minus mu square divided by 4mi minus f. Now, a basic question is what's the number of brands that get created? We're going to denote by IMC. And I hope it's easy for you to see that as the number of firms increases, the price per firm in goes down. And eventually there are enough brands inside that becomes negative. So the number of firms of brands that get created is the maximum number, the maximum integer, such that let me write it differently in case you're not familiar with this set notation, such that P max minus mu square over 4mi is greater than f. So brands are going to keep entering as long as the profits are positive. Remember, for a firm that doesn't enter, they get zero profits in this model. So brands are going to keep entering until that condition is violated, and that's going to give you the equilibrium number of brands. Notice one thing, so remark. The first is that there are multiple equilibria. Why? The model pins uniquely the number of brands, but not which specific firms are the brand, the ones that create brands. So basically, for example, if there are 3 firms and the number of firms that brands get created are 2, you could have the brands by firm 1 and firm 2, firm 1 and firm 3, or firm 2 and firm 3. The other remark that I wanted to do relates to the logic of equilibria. Notice why not all of the firms may create a brand is because they take as given that some of the other firms have already created a brand, and given that it's not profitable to do so. This really relies on equilibrium having this property that we have been using throughout this unit of taking as given the actions of the other people, anticipating correctly, and maximizing with respect to that. What's the deadweight loss from monopolistic competition? We know that the quantity total in monopolistic competition is equal to the quantity total in monopoly. So this implies, it should be obvious to you at this point in the course, that the deadweight loss in monopolistic competition is going to be equal to the deadweight loss in monopoly, with one twist, which is that the firms have to spend this semi-fixed cost money to create their brands, and that has no social value whatsoever. So in addition, there is this loss of I monopolistic competition times F. And if you do the math, this is equal to P max minus mu square divided by 8m plus I MCF. Now let me make several remarks about this. The first is, in oligopoly, the deadweight loss goes to 0 as the number of firms increases. In monopolistic competition, deadweight loss increases with number of firms in, with number of brands. So it's very, very different. The second is, let me highlight again, the semi-fixed costs of brand creation are social waste. Why are they social waste? Because they don't really add to the consumption utility of the individuals. They fool them into thinking that if they eat that brand or that other brand, they will get better utility, because otherwise they assume they get 0. But but they don't really exchange experience utility. And the third one is that there is a relationship, or before we saw this idea of decision utility versus experience utility, and that there were situations in which this could be different. This is the case in monopolistic competition. In particular, what the branding does is get the consumer to think that their decision utility is equal to B of Q if consume brand, and 0 otherwise. But this is not true. The true experience utility is the same in either way. So this basically, in the monopolistic competition, there is simply an assumption that there is a gap between decision utility and experience utility. Now we're ready to continue our exploration of imperfect competition markets for the case of an oligopoly. There are many markets in the world that have more than one firm, so they are not monopolies, but only a handful of them, so they are not perfect competition. That intermediate case is this case of monopoly that is of great practical interest. And it's of great practical interest because the firms will have some market power, but not as much market power as they have a monopoly. And that's what we want to understand with this basic model of the monopoly that we are about to understand. So let's assume that there are two firms, to look at the simplest case of the monopoly model, then we will complicate it. And let Q1 and Q2 denote the amount produced by each firm. And let Ci of Qi be the cost functions, and assume that there are no fixed costs or semi-fixed costs, to keep it simple. Now, the key assumption of the model is that firms profit maximize, as always, taking into account or given the actions of the other firm, which, by the way, they anticipate correctly. And let me make a comment about this. This notion that they anticipate correctly is sometimes called rational expectations, or is an instance of rational expectations, which means that in equilibrium people know, the actors know correctly what others are going to do. One important aspect of the monopoly model that is good getting intuition, clear intuition from the beginning, is that the choice that every firm faces involves some important strategic considerations. And by strategic considerations, I mean that the best action for a firm is going to depend on what the other firm does. And the key reason why that is the case is because the demand faced by one of the firms, let's say by firm I, depends on the choice of the other firm, let's say firm J. And let's see why. In particular, suppose to see why that the demand, inverse demand function for the market as a function of Q, the total quantity, is linear and has this shape, P of the market minus M Q. Suppose that this is the aggregate demand function for the market, then look at what happens. We're going to plot first that demand function, which looks like this. PD of the market of Q1 plus Q2. This is a choice by the two firms. And now suppose that firm 2, let's say, chooses this quantity. Question is, what is the demand that firm 1 is going to face, given that it's going to be given by this? This is going to be the demand of, as a function of Q1 that firm 1 faces, given that the other firm produced Q2. And let's see why that is the case. Well, we know that total demand is given by this linear thing minus m times the sum. If the other thing already shows that, it's only this part of the demand function that firm 1 can fill. Basically, if it produces nothing, this will be the price. If it keeps producing, the price will drop lower and lower. That's why, from the point of view of firm 1, the demand function, how it affects the price as a function of what it produces, is shifted to the left just by this amount. Okay, given that, now let's look at what the problem of each of the firms look like. So let's look at a firm I, which can be either the two, which is going to want to maximize over Qi greater or equal than 0, its revenue, Qi, times the demand given by the amount that it chooses and the other one chooses, because both affect the price, minus Ci of Qi. And very important, this Qj is taken as given. The action of the other firm is taken as given by the equilibrium choice of the other firm. Let me emphasize what I mean by that. When firm I is solving its problem, it assumes that it knows exactly what firm J is going to do, and it takes it as a constant in the maximization problem. So what are the first order conditions for this problem? Which by the way are also going to be sufficient. It's going to be taking the derivatives Qi times the derivative of PD with respect to Qi plus PD equals to the marginal cost for firm I. And notice, recall that this shape you have seen before of this equation, this is the marginal revenue with respect to Qi given Qj. Now, depending on the details of the function, it's going to have a unique solution, and let's call the solution, let Qi star of Qj denote the solution. So this is going to tell you what the best response for firm I is to any choice by Qj. And let me plot for you what this looks like. So if I have the aggregate demand for the market, let's suppose as before that firm 2 choose here, let's say Q2, so that the demand function for firm 1 becomes this. Notice that from this intuitively, then what remains is a problem that looks like the monopoly problem, just given with the shifted demand. So what we do is we plot the marginal revenue curve as a function. Sorry, this is Qi and Qj. I made a typo here. Of Qi as a function of Qj. And if the cost function of Qj is here, of Qi, what the firm is going to do is going to pick this, the point at which marginal revenue equals marginal cost. So this is going to be Qi star, and this will be the price in the market that results. Okay. So the key idea that you need to remember is that it looks like the monopoly problem, but the demand has shifted because of the choice by the other firm. Okay, now we're ready to define what an equilibrium in this market is going to be, and I'm going to define it for the case of two firms, and we'll see how generalized in a second. So an oligopoly equilibrium is going to be given by a quantity for the first firm and a quantity for the second firm that has the following properties, such that Q1 OL is a best response, so we're going to write like this, Q star of what the other firm does, and Q2 OL is equal to Q2 star of Q1 OL. So the key idea is that both firms are best responding to each other. And let me make some remarks about this. First, again, the notion of rational expectations is key. Notice that each firm is best responding to each other's equilibrium action, and the equilibrium action of the other firms is anticipated correctly. Second, again, let me emphasize that firms are best responding to each other. Third, at equilibrium, there's no incentive to deviate. What I mean by that is that the two quantities that are being predicted by the equilibrium are an equilibrium because given what the other person is doing, no one wants to deviate because they are best responding to each other. And fourth is that this equilibrium concept generalizes to more than two firms. And the key idea of how it generalizes is that you best respond to the actions of all other firms. So for example, if there were three firms, the equilibrium level for firm 1 will be the best response to the choices of firms 2 and 3, etc. In order to derive better intuition for the properties of these oligopolistic markets, we're going to solve a concrete example, which is the case of linear aggregate demand and two identical firms. In particular, we're going to suppose again that there are two firms and that each one of them has a cost function, C of Qi, which is simply given by mu Q. It's constant returns to scale, and mu is the marginal cost, which is the same for both firms. Also assume that the inverse aggregate demand function for the sum of the two firms produced is equal to P max minus M of Q1 plus Q2. Okay? Now, what is the demand faced by firm I? Well, it's going to be this inverse demand function taking the quantity of the other firm as given, which is going to be P max minus M of Qj, and again, this is the behavior by the other firm, and then minus MQi. That is the demand function, or the inverse demand function, faced by firm I. And what is it going to do? It's going to maximize over Qi greater or equal than 0, that demand function times Qi, minus its margin minus its total cost, which is MQi. Now that's a problem that you know how to solve if you think of this as a constant, because it looks like the monopoly problem, except that the intercept of the demand function has shifted to that, and we know that that problem is going to have marginal revenue for I given Qj equals to marginal cost for I. And this is going to be equal to P max minus MQj, that's the intercept that firm I is facing, minus 2MQi equals to mu. Okay? Now, the key to solve the problem is to notice that since the two firms are identical, we're going to have a symmetric equilibrium. Identical firms imply a symmetric equilibrium in which Qi equals Qj, and let me call that Q oligopoly. So that implies that that equation has to hold with P max minus, substituting this there, 3M Q oligopoly equals mu, which implies that the equilibrium quantity of the oligopoly is equal to P max minus mu divided by 3M. Now let's look at the nature, the graphical nature of the solution, and use it to compute the amount of inefficiency or deadweight loss produced by having an oligopolistic market instead of perfect competition. So let's do our usual diagram first, in which we're going to draw the inverse aggregate demand function for the market. So this is for the market, and the marginal cost function for the firms, which is equals to mu. And we know that at a competitive equilibrium we're going to get this level of quantity which is optimal, and you should be able to compute this given what you have learned in previous lessons. This is P max minus mu, I'm not going to do it again, divided by M. That's the optimal total production in the market given the parameters of the market. Of course, that's not what the oligopolistic market is generating. What the oligopolistic market generates is something like this. Let's say that every firm is producing QL, and therefore for a typical firm I, the demand that I faces, given that the other firm is producing QL, looks something like this. That leads to a marginal revenue curve that kind of looks like this as a function of QI, given that the other firm is producing QL. The best response by this firm is, of course, to produce Q oligopoly by either of them. That leads to a total output in the market. So this is, so let me improve the writing here. 2QOL is total output in the market, and that leads to this equilibrium price that I'm going to denote by P oligopoly. Okay, and you can obtain the formula for that price oligopoly by substituting the value of, I keep writing this very poorly, 2QOL, the value of the total output in the inverse demand function, and what you get is 2/3 of mu plus 1/3 of P max. Notice something interesting. In a competitive equilibrium, the price would have been P star equals mu. Here the price is shifted a little bit towards this value, P max, and so it's therefore higher than what would have been in a competitive equilibrium. Now, what's the deadweight loss in this market? Well, we know this is the total amount produced, this is the optimal amount, so it's going to be this area. Is the area between the inverse aggregate demand function, which is also the aggregate marginal benefit curve, and the marginal cost curve, which is also the aggregate marginal cost curve, and the underproduction and the quantity produced. So this is the deadweight loss. Now let's compute what the deadweight loss is. That deadweight loss, I'm going to do it on the right hand side, is going to be equal to 1/2, because it's a triangle, the optimal quantity minus the 2QOL, which is the amount of the quantity generated by the oligopoly, and that's the base of the triangle times the height of the triangle, which is the price of the oligopoly minus this price in equilibrium. And this is basically going to be 1/2 of 2/3 M P max minus mu. I'm just substituting terms. And this other one is going to be 1/3 of P max minus mu, which is going to be equal to P max minus mu square divided by 9M. So there is a positive deadweight loss, and it tells you how it relates to the different parameters of the economy. Now let's do a distribution and analysis of the surplus generated by this market. What I have done here is I have redrawn for you the key features that we need for the analysis are the aggregate inverse demand function, the marginal cost function, the equilibrium price in the oligopoly, the total quantity produced by the oligopoly market, the equilibrium price in a competitive market, and the intercept of the aggregate demand function. And what we want to do is we want to compare what happens to producer surplus, consumer surplus, and social surplus in the perfect competitive case and the oligopoly case. And let's be precise about the experiment. What we're comparing here is what actually happens when there are two firms, these two identical firms in this example, and we run an oligopoly market. Well, what would have happened, so this is a counterfactual, if these firms had behaved competitively. So we know that if the firms had behaved competitively, this would have been the equilibrium price, this would have been the quantity produced, and the consumer surplus would have been A plus B plus C. with this constant returns to scale production function, we know that producer surplus is 0, there are no profits, and social surplus is A plus B plus C. With oligopoly, the consumer surplus, because they have to buy at this price and only buy this quantity, is going to be A. The producer surplus is going to be B. Social surplus is going to be A plus B, and there is going to be, let's do the difference here, a Z, which is the deadweight loss. And notice that producer surplus goes up by B, and consumer surplus goes down by minus B plus C. So not only do we have a transfer to producers, we have a loss of social surplus. Consider a fun example that resembles the kind of questions that the US antitrust authorities often have to consider. So suppose that there is a market with two firms, and let's assume that is the simple linear symmetric case in which the aggregate demand function is this linear one, and remember Q denotes the total amount produced, and the firms have marginal cost equals to mu for both firms. This simple case that we have been looking at to really get intuition for the oligopoly. Now, this is the initial state of the market, and then the question is, what happens to efficiency, to deadweight loss, if the firms merge? What happens to deadweight loss? This is very important for antitrust authorities because in more realistic and more complicated examples, in order to decide whether or not they approve a merger of two firms, they have to decide, they have to measure whether this is good or bad for consumers, and they're going to look at things like what is the change in social surplus, the change in efficiency, the change in consumer surplus. So let's play with this case. So we're going to do here what happens before, and here what happens after. And remember, this is going to be the case of when they act together as a monopolist. This is going to be the case in which they act together as an oligopoly. Not together, sorry, separately, competing in parallel as oligopolistic firms. Now, we know what happens in this case in oligopoly, that each firm ends up producing a quantity P max minus mu divided by 3m, that the price in the market ends up being 1/3 P max plus 2/3 mu. We solved that before. And that the deadweight loss ends up being P max minus mu squared over 9m. I'm just copying from our notes what we knew happened before. Now let's think about what happens in the monopoly case. The problem of the firms that when they merge together is to decide how much to produce together in total, given that they face this demand function. And since the marginal cost per unit is constant, we don't have to worry about how much is produced by the old factory of firm 1 or the old technology of firm 2. The constant cost per unit produced is mu is the same. So it's going to maximize over Q greater or equal than 0, Q times P max minus MQ minus mu Q. Total revenue minus total cost. We know that this is going to look at the marginal revenue of that equals marginal cost, and that this is going to be equal to P max minus 2MQ equals mu, which implies that the quantity in the monopoly case is going to be equal to P max minus mu divided by 2m. So we already get the first insight when we compare the total quantity of the oligopoly is going to be this, which is going to be 2/3 of this quantity divided by m, is going to be greater than the quantity of the monopoly. So notice that the quantity of the oligopoly is greater than the quantity of the monopolies. We can also easily compute the price by substituting back in the inverse demand function to be, in the case of the monopolist, so price of the monopolist is going to be equal to 1/2 of P max plus 1/2 of mu. So, not surprisingly, given that the quantity of the monopolies is less, we have that the price of the monopolies is greater than the price at the oligopoly case. And finally, we can compute the deadweight loss using this of the monopoly case, using the same tricks as we have used before. This is going to be equal to 1/2 the price of the monopolies minus the price at the competitive equilibrium allocation or the efficient allocation times the quantity of the monopolies minus the quantity that is optimal, or the quantity generated by the equivalent outcome if the firm has behaved competitively. And if you do the algebra, you get that this is 1 divided by 8m p max minus mu square. Okay. So what do we have? We have that if you move from oligopoly to monopoly, you increase the deadweight loss. Surprisingly, not by as much as you would expect in the case of two firms, an oligopoly with two firms versus monopolies, but it goes up nevertheless. So it's not good for efficiency. So far, we have focused on the case of an oligopoly with two firms in order to bring out a lot of the notions, concepts, and tools. But really, a very important question is what happens in an oligopoly equilibrium as the number of firms goes up. So what happens as F increases? Now, what we're going to do here is we're going to look at a case with more than two firms, F greater than 2, and we're going to keep it simple by assuming that we are in this linear symmetric case that we studied before, which basically says that the inverse aggregate demand function is just P max minus MQ when Q is the total quantity produced, and that every firm has a marginal cost that is constant and equals to mu. Now, let's characterize the equilibrium of this oligopoly market. Okay? It's actually very, very easy if we use the same key insight that we used before, which is that because all of the firms are identical, we're going to get a symmetric equilibrium in which Qi at the oligopoly is going to be equal to Qj at the oligopoly. This is the quantity produced in the oligopolistic equilibrium by firm I or by firm J, and I want to denote just the quantity produced in equilibrium by any firm by QOL. Now, how we would derive that property? We know that the demand faced by firm I is just going to be equals to P max minus F minus 1 M QOL, because that is in equilibrium the quantity produced by all of the other firms except firm I that we're looking at, given that they are producing at the equilibrium level, minus MQI. Now, given this, we know that the optimal behavior, optimal choice by I, which as before takes the behavior of the other firms as given, it sets marginal revenue for I equals marginal cost for I. The marginal revenue for I is going to be P max minus F minus 1 MQOL minus 2M QI equals the marginal cost, which is mu. And since this has to be the same for every firm, we can assume that this is QOL too. And that implies, just solving the equation, that QOL is equal to P max minus mu of F plus 1 M. Notice that this is the quantity per firm in equilibrium. It's not the total quantity. The total quantity is F times this. Now, we also can derive what is the price in equilibrium by substituting the total quantity here, and we're going to get that the price of the oligopoly in equilibrium is going to be equal to P max minus M times this quantity, which is just going to be equal minus P max minus mu f over f plus 1, and this is just equal to 1 over f plus 1 of p max plus f over f plus 1 of mu. Okay. Notice one interesting thing. We know that in a competitive equilibrium, we saw that before, the equilibrium price is mu, and here what we have is a weighted combination of this larger number p max and mu, but as f increases, the weight shifts more and more and more and more to mu, so it converges to the competitive equilibrium as f goes up. Now, given those results, we can easily compute what is the deadweight loss as a function of the number of firms f. Okay? What we're going to get is 1/2 of what is the price in oligopoly, we just derive as a function of f, minus the price in competitive equilibrium. And by the way, remember, we know that in competitive equilibrium, this is mu, which seen that repeatedly this unit. And the difference in the quality produced in the oligopoly minus the quantity produced in competitive equilibrium. And again, as we saw before, remember, this is equal to p max minus mu divided by m, or the optimal amount. If you do the algebra, this gives you 1/2 of p max minus mu divided of f plus 1, and p max minus mu divided by m times f plus 1, and this is equal to 1 over 2m p max minus mu square divided by f plus 1 square. And I want to emphasize this result. I think this is a very remarkable result because it's telling you something extremely beautiful and extremely important, which is that the deadweight loss goes to 0. In other words, you are converging to the efficient allocation, to the competitive equilibrium allocation with the square of the number of firms. Not linearly, but with the square. That means, for example, that by the time you have 10 firms in there, you are approximately within 1% of achieving all of the efficiency gains. It's noise. And that is very important because it's telling us that you don't need to have a very large number of firms, which they are not in most markets, to really have the competitive model be a good approximation of what happens. The goal of this problem is to ask you to apply the concept of oligopolistic equilibrium for a market in which the firm do not have the same cost structure, in a non-symmetric case, in other words. So we're going to assume that firm 1 has a cost function, C of Q1 equals to 100 Q1. Firm 2 has a cost function, C of Q2 equals to 200 Q2, and that the aggregate inverse demand function defined over the total amount demanded is, so the total amount sold is 1000 minus Q1 plus Q2, and the question is to compute the equilibrium level of Q1 and Q2 star, given that this is an oligopolistic market. Let's solve this problem. And I'm going to solve it in quite a bit of detail to reinforce the lessons from the lectures. So we have two firms, firm 1 and firm 2. The problem of firm 1 is to maximize 1000 minus Q2 plus Q1, that is the price that can be supported at those two quantities, times Q1. All of this together is the revenue that the firm gets, minus 100 Q1. And this, of course, over non-negative quantities. The problem of firm 2 is to maximize over non-negative quantities the same aggregate inverse demand function the marginal cost of this firm is 200. Now, as we've seen in the lectures, in the theory, the first order conditions for both firms are going to look like marginal revenue for one equals marginal cost for one, and marginal revenue for two equals to the marginal cost for two. Now, what's the marginal revenue for this first firm? If you take the derivative with respect to Q1, and the key is holding this as constant here and this as constant there, what you get is minus Q1 plus 1000 minus Q2 plus Q1 equals to 100, which is the marginal cost in this case. And here what you get is minus Q2 plus 1000 minus Q2 plus Q1. This is the marginal revenue in this case, equals 200, which is equal to the marginal cost in this case. Now, if you work with both equations, what you get is a system of two equations with two unknowns, which are 1000 minus 2Q1 minus Q2 equals 100, and 1000 minus Q1 minus 2Q2 equals to 200. And if you do the algebra, what you get is that Q1 is equal, or Q1 star in equilibrium, to 1000 over 3, and Q2 star is equal to 700 over 3. Let's check our economic intuition a little bit. It would make intuitive sense that the firm that has a lower marginal cost will end up producing more, and that is indeed the case. By the way, a small tip for this class of problems: if you want to check that your solution is correct, one thing that you can do is obtain the solutions, go back and plug them back in the marginal revenue equals marginal cost equation, and check that everything holds. That allows you to check your algebra, and this is the case here. The goal of this problem is to ask you to keep thinking about what happens to the equilibrium in the market and its properties as the number of firms increases. So let's look at our basic model of oligopoly, in which we have that the inverse aggregate demand function of Q is just P max minus MQ, and there are F identical firms with a constant marginal cost mu, and of course they engage in oligopolistic competition. And the question for you is to compute the equilibrium aggregate consumer surplus and producer surplus as a function of F. Let's solve the problem together. Let me start with this diagram, which is going to depict the aggregate demand function in inverse form. So the PD of the market as a function of quantity, and the marginal cost of the firms. And we know that in a competitive equilibrium, this is the total quantity produced, which is equal to P max minus mu divided by M, and we also know that this is the equilibrium price. So we know that the area of the triangle in equilibrium, in the competitive equilibrium, the consumer surplus is going to be equal to 1/2 times this height. Remember, this interception is P max, which is P max minus mu, times the quantity, which is P max divided by M, so square over 2M, and that the producer surplus is 0. That's what happens in equilibrium, in a competitive equilibrium, regardless of the number of firms. Now let's see what happens in the oligopoly case. I'm going to use a different color. We know that in the oligopoly case, the total quantity produced is going to be equal to F over F plus 1 of Q star. We've seen this before several times, so I'm not going to repeat the derivation. And we also know that the equilibrium price in this particular case is going to be equal to P max over F plus 1 plus F over F plus 1 mu. Now, consumer surplus is going to be given by this area. Oops. In the case of the oligopoly, and producer surplus is going to be given by this area. So let's compute what those numbers are. Consumer surplus as a function of F in the case of the oligopoly is going to be the rectangle, so 1/2 times that distance, so F times F plus 1 P max minus mu divided by M times that height, but that height is going to be this price minus mu, which is equal to P max I apologize. This height is P max minus this, which is equal to F over F plus 1 of P max minus mu without being divided. So the total consumer surplus is 1/2 F square over F plus 1 square P max minus mu square over M. Okay? And I will interpret this in a second. Now let's do the producer surplus. In the oligopoly is that rectangle, which is just going to be that distance, F over F plus 1 of P max minus mu square over M, plus that distance, which is 1 over F plus 1, sorry, there is no square there, P max minus mu, which give us P max minus mu divided by M square times F over F plus 1 square. So please notice a couple of things. Now let's interpret. This term, okay, you can write, by the way, this is equal to, sorry, this term is the optimal consumer surplus, and that term is going to 1 as F goes to infinity, and in particular it's going to 1 fairly quickly. It's going to 1 like this, okay? So by the time you have 10 firms, you are pretty well up there. This term is also going to 0 with the square, but one important thing to notice is that the deadweight loss was going before to 0 by 1 over F plus 1 square. In these particular cases, these terms are going to the optimal consumer surplus, so for the equilibrium or the competitive level of consumer surplus, a little bit slower because it has this F square term in the term, and the producer surplus is going to 0, also is lower than the deadweight loss is going to 0 because of this F term here. Here is a problem designed to ask you to think about the decision the firm face to whether to invest in creating a brand or not. So consider a market with 2 firms. Each of them can produce at a constant marginal cost of mu dollars per unit. And the key thing is that they can create a brand at a semi-fixed cost of F. If they create the brand, they get half of the demand. If not, they engage in oligopolistic competition. Okay? Now, suppose the government introduces a branding fee of $T. By a branding fee, I mean just that if the company wants to create a new brand, it has to send a tax of $T to the government. Question: what is the lowest T at which firms do not create a brand at a symmetric equilibrium. Okay, let's solve the problem together. We need to compare, to solve the problem, the profits when both firms engage in monopolistic competition, when both create brands, and when both do not create brands, so have both in oligopoly. Now, in oligopoly, the fixed tax, the fixed semi-fixed cost F and the branding fee doesn't apply, and we know what the solution is going to be because we have solved it several times before. So we're going to know that every firm produces a quantity QL, which is equal to P max minus mu divided by 3M. We know that the price of the oligopoly is going to be 1/3 P max plus 2/3 mu, and we know that the profits per firm at the oligopoly are going to be equal to QOL POL minus mu, which if you do the algebra gives you P max minus mu squared divided by 9M. We know, therefore, what every firm would get in equilibrium, in the symmetric equilibrium, in which they both do not create a brand. Let's see what happens in the equilibrium in which both of them decide to create a brand. Then, from the work that we have done before, we know that each gets demand P max minus 2MQ, and they act as a monopolist in there. I'm not going to solve that detail because we've done it many, many times. So that implies that each firm in the monopolistic competition gets to produce P max minus mu divided by 4M, that the price in this monopolistic competition market subset is P max divided by 2 plus mu divided by 2, and the profits for each monopolistic competition firm is going to be equal to the quantity that it produces, the price at which it sells minus the marginal cost, minus the semi-fixed cost plus the branding fee. And this is equal to, if you do the algebra, P max minus mu squared divided by 8M minus F minus T. So this implies that T has to be equal, for the firm to be indifferent between both cases, which is what is going to give you the lower branding fee at which they want to switch to oligopoly, is going to be equal to P max minus mu squared over 8M minus F minus P max minus mu squared over 9M, which is equal to P max minus mu squared over 72M minus F. Now, since a market with public bats generates excessive amounts of production, a very natural question is which class of corrective policies can restore efficiency in the market by reducing the amount of production. We're going to consider the two classic policies that are used in the real world to deal with this problem, which are corrective or Pigouvian taxation and permit markets. So in this video, we're going to look at this corrective taxation. The policy looks as follows. A tax is imposed on every consumer or firm generating an externality on others. The tax is equal to the total marginal damage or total marginal externality at the optimum. And finally, the revenue is returned lump sum to consumers. Notice an important thing is that, for example, if a consumer is imposing an externality on both other consumers and firms, the size of the tax has to reflect that total marginal externality to both groups. Now, key result, this Pigouvian tax system leads to an efficient allocation. So if the government imposes such a corrective tax system, an optimal allocation would follow. Before I explore how this works, notice that these things are called Pigouvian taxes because Pigou was the economist that first figured this result out. Now, this beautiful result holds under very general circumstances, under very general assumptions, and certainly for all of the examples that we're going to look at in this course. But a general proof requires a lot of notation and gets too cumbersome. So to maximize the intuition, I'm going to look at simple case or model in lecture 9.1. And remember that this is a case in which the externalities, just to remind you, there are externalities from consumers to consumers. The utility function of the individuals would depend on Q, M, and E, and was simply BQ plus M and minus this damage function gamma damage of E, where E was the total externality, and the marginal cost of production was equal to mu, was a fixed amount. Okay, and also assume there are n consumers. So let's look at this case. What the Pigouvian tax system says is that we're going to use a Pigouvian tax, let me denote it by tau star, equals to the total marginal externality that is caused by every unit of consumption. So this is going to be gamma n, because this is how many consumers are affected, d prima, evaluated at the optimal level of externality, Q optimum. Okay, and this is imposed on consumers, because those are the ones generated the externality in this case. Now, what's the consumer problem? They have to maximize over Q greater or equal than 0, B of Q minus PQ minus tau star of Q minus the damage of the externality, and this is taken as given during the problem. Now this is going to generate first order conditions which look like B prima, marginal benefit, equals to the price plus the size of the tax. Now notice that in equilibrium we know that the marginal cost is a constant, so we know that the equilibrium price is going to be mu. We have seen this in many examples throughout the course for the simple case in which the cost function has constant returns to scale. So this implies that in equilibrium, every consumer, the utility maximization implies B prima equals mu plus tau star. But notice what tau star is gamma n d prima of Q optimum. And notice also, just to be precise, that in equilibrium everybody consumes the same amount, so this is B prima of Q total divided by N. Now notice that this is exactly the optimality condition. In other words, when Q total is equal to Q optimal, we have that the total quantity is optimal. So by imposing the tax equals to the optimal amount, the utility maximization problem leads, plus the fact that in equilibrium the price is mu, lets the individual to satisfy the optimality condition. Let me show you the intuition of what is going on. Now, optimality requires that the marginal social benefit be equal to the marginal social cost. In this case, the marginal social cost is equal to the marginal private cost because there are no externalities on production, which is equal to mu. The marginal social benefit is going to be equal to the marginal private benefit minus gamma n d prima, and this is the total marginal externality or total marginal damage. Optimality requires that a quantity is chosen that this is equated to this. Now, utility maximization implies that the individuals are going to set b prima minus t star equals p, and this is by utility maximization, and that the firms are going to set this equals mu, and this is by profit maximization. Now, what happens is that this is the marginal private benefit, and if this is chosen to be gamma n d prima at the optimum, then the optimality condition is satisfied. In other words, the key insight of PIGU is that by introducing the tax and picking the right value, we could restore the fact that utility maximization and profit maximization will again lead to the equation of marginal social benefit and marginal social cost. Here's another way of seeing graphically what is happening here. We have the marginal private benefit, which is given by the demand in the market as a function of Q. Now we also have a curve, let's say something that looks like this, which is a true marginal social benefit, and this distance is the n gamma d prima, the marginal damage. Now we also have in this particular model that the marginal private cost is equal to the marginal social cost is equal to mu. So that leads us to have an optimal quantity here and an equilibrium quantity here. As always, equilibrium is at the intersection of the marginal private cost and marginal private benefit, whereas optimality is at the intersection of the marginal social cost and marginal social benefit curves. But this is the inside of PIGU. Now suppose that you introduce the tax so that the demand curve of the subjects switches by the size of the tax. So it's going to switch then by the size of the tax parallel. As we have seen many times before, individuals react. So this is pure the market with tax. If this tax happens to be equal to this distance, which is n gamma d prime at Q optimal, what is going to happen is that the new equilibrium is going to become the Q optimal. This is the Q equilibrium with T star, the optimal Picouvian tax. They pass through here. Notice that a smaller tax or a bigger tax won't do it. It has to be exactly the size of the marginal externality at the optimal quantity. Let me highlight several important remarks. The first one is that the optimal Pigouvian tax restores efficiency. But the government can only do this if it has or it requires sufficient information to calculate it. Compare this to the case of the first welfare theorem, in which the market by itself, without any help, without any information by the government or a centralized party, was able to accomplish efficiency. Here, the government needs to know enough to at least know who to assign these Pigouvian taxes to and what its size should be. The second is that the model assumes, and this is an important assumption, that everyone produces the same marginal damage. But if this is not the case, say for example, because there are clean consumers and dirty consumers, then individual specific taxes are needed. And that requires even more information. So to give you a concrete example, suppose that half of the consumers produce twice as many externalities as the other consumers. They're twice as dirty, in an example of pollution. Those people require a Pigouvian tax that is always twice as large, and the government needs to have these individual specific taxes. The third remark is that the system works if tax is imposed to firms or consumers. It doesn't really matter, and let me show you why. So here we have the example that we just did, but in general we have the marginal private benefit, the marginal private cost, and suppose that we are looking at a case in which the marginal damage is on the consumers. So let's say we have that the marginal social benefit is below. We have something like this. We can restore optimality by either imposing the tax on consumers, which basically shifts their demand curve like this. This is their demand curve for the market with the optimal tax. And remember, this is the optimal tax. Or we can achieve the same thing, exactly the same thing, by leaving the consumers alone, but imposing a tax on producers that shifts their demand curve in parallel, the supply curve in parallel up. So this will be the supply curve of the market with the tau star. This will be the supply curve in the market without tax. In both cases, we get that the equilibrium quantity is equal to the optimal amount. So it doesn't matter. Notice, however, that you cannot, it doesn't work if impose the full Pigouvian tax, tau star, on both. Why? Because in that case, you think about it, have the marginal private benefit, the marginal social benefit, you have the marginal private cost, the marginal social benefit. If you impose that tax on both of them, so you switch the demand here by this much and you shift the supply here by this much, you end up with an equilibrium that is here, which is less than the Q optimum. So intuitively, you only have to tax the transaction of every unit of Q that produces externality once. You can either by imposing the tax on the consumer or on the producer, but you cannot tax it twice. The other policy that is widely used to deal with negative externalities or public bads like pollution are permit markets. These policies look as follows. The government creates pi star equals quite optimal units of permits. Each permit allows the owner to produce or consume, depending on whether it are permits on producers or consumers, 1 unit of Q, which is the good that generates externality. Individuals or firms who exceed allowed permits, in other words, will consume more Q than they have permits for, pay an infinite, a very large fine. So no cheating in equilibrium. We can ignore that part of the problem. And finally, individuals and firms are allowed to trade permits freely. An individual has a permit and he's not going to use it, he can sell it to someone else, and vice versa. Notice that there are two versions of this permit policy. In the version number 1, permits are sold by the government. In the second version, the permits are freely allocated. For example, everybody may get an equal number of permits, and then there is free trade. Well, actually, there is free trade in both cases. We have a parallel result to the case of the Pigouvian taxation here, which is the following. If the total number of permits is given by the optimal quantity, then the permit policy leads to an efficient allocation and in equilibrium the price of permits, let me use a different letter. The price of these permits in equilibrium is equal to the optimal Pigouvian tax. That is very nice because it leads to a very tight connection between the two systems that we have studied. Let's see why this result is true, and to derive parallel intuitions, we're going to focus on the simple case of only consumer externalities that we have been working with. This is the case of video 9.1. Also, let's develop first intuition for the case in which the permits are freely allocated, not sold by the government. So let's see how this works. Let's look at the consumer problem. Consumer has to maximize over two variables, Q and R, when R is the number of permits greater or equal than 0, and also Q less or equal than R to avoid the penalty, B of Q minus P of Q minus pi times R minus pi endowed of I. Notice that this is the number of permits needed to be just at compliance, to have this hold with equality, which is what the consumer wants if the prices are, if the permits are valuable. This is the amount endowed of permits that it receives. Now, this is equivalent to maximizing with respect to Q, as long as the permits have positive value, B of Q minus P plus pi Q, when pi is the price of permits. Okay? Let me actually, I realized that I changed notation before and I'm not being consistent, so let me fix that. This is going to be the price of the permits, and this is going to be the price of the permits. Okay. Now, what are the first order conditions? Now we are maximizing a single variable, but implies demands in two markets. B prima equals P plus this price of permits. Now, notice that in equilibrium, we know that P, the price of the good Q, is equal to mu by the constant returns to scale in the production function, in the cost function. Now, what's happening in equilibrium? Let's look at the two markets where the consumer is trading Q and permits R. Well, in this market, we know that the demand of the consumer would have been this. This is the inverse aggregate demand function without permits. And we know that with permits, this shifts down by pi. By the price of the permits. Okay. We also know that P star is equal to mu, and therefore, if the price of the permits happens to be equal to gamma n d prima at the optimum, which is the damage that the consumers experienced, then we know that this quantity has to be the optimal one. Because in that particular case, this demand function in the market with permits is equal to the marginal social benefit. And since this is equal to the marginal social cost, we have the optimal quantity. That's a way of looking at the Q market. Now let's look at the permits market. Well, without loss of generality, you can think of what's going on here as the consumers think of the endowment of permits as something that they can sell and consume the income, and then they just decide how much to rebuy. That's the way we have rewritten the problem here. So the endowment of the free allocation or endowment of the permits is kind of an income transfer to the consumers. How does the equilibrium of this market look like? Well, here we have the price P. Now here the market price is this P of pi, the price of permits. The total supply of permits is pi star equals to Q optimal by design of the policy. Now the question is how many permits are demanded. That's given by the same first order condition. So it's going to be given by start, like you can write like this, start with the price of the market without policy, but then you can bring it down not by the price of permits, but by the price of the Q good in equilibrium by the mu. So this shifts down by mu. Okay? And the question is, what's going to be the equilibrium price of permits? Well, since we know that at the optimum, I'm going to write it here, at the optimum, we have that the marginal private benefit has to be equal to mu plus the marginal externality. We derived this for this model. We know that this height has to be equal to gamma n d prima optimum. Why? Because that height plus mu has to be equal to the marginal private benefit. So that's how the two markets reach in equilibrium. And there is a very nice intuition that I hope you're seeing, which is you can look at what happens in the equilibrium market Q, in which basically the permits act like a tax, like an additional cost in the consumers, and the value of the tax is determined endogenously by the equilibrium in the market permit. Now the equilibrium in that market is going to be the one which, given the shift in the demand by mu, is going to make the market clear, and that has to be a price P pi star at which the total quantity demanded is the optimal quantity equal to the number of permits. The analysis of the case of the permit solved by the government is very simple with one small twitch, which is that in this particular case, no individual, or let me say differently, the endowment of permits is equal 0 for all I, and instead the government sells pi star permits in the permit market. Notice that that doesn't change the equilibrium in the market. If you go back and you look at all of the analysis that we have done, the endowment of permits was a transfer to the consumers, but has no effect in the equilibrium, which implies that same equilibrium as before, so same P pi star, P star, and Q star. The only difference is that now the policy raises revenue from selling the permits. Whereas before, it raised no revenue because all of the permits were given for free. There is a very nice equivalent result between Pigouvian taxes and permit markets, which is that the optimal Pigouvian tax system, and I'm going to put in parentheses to remind you, with revenue returned using lump sum transfers to consumers, is equivalent, it generates exactly the same outcome as the optimal permit market with permits sold, not freely allocated, and with the revenue, just as before, returned using the same lump sum transfers. Let me give you an intuition for why this is the case. It's actually, in my view, rather beautiful. What happens in a Pigouvian tax system is that the government sets the price, which is going to be tau star equals to this, in the case of the model we have been looking at, gamma n d prima at the optimum. And then the market finds Q optimum. In this particular case, the government does the opposite. The government sets quantity by fixing the number of permits and imposing the fines to pi star, the total number of permits equal to Q optimum. And then through the permit market, the market finds the price of the externality, which is going to be P pi star equals to gamma n d prima of Q optimum. But in both cases, the total revenue raised is equal to Q optimal times gamma n d prima Q optimal. And as long as the revenue is distributed in an equal fashion to consumers, the systems are completely equivalent. Let me conclude with several remarks. First, the system restores optimality. Permit markets can restore efficiency, just like Pigouvian taxes, but require information by the government. In particular, the government needs to know the optimal quantity, and that requires to have information that it may or may not have. The second comment is that you may be wondering why the government uses permit markets versus command and control. Just basically telling firms what to do. That's often called command and control. Direct regulation, sometimes it's called. The advantage is, again, information. Here, the government only need to know Q optimal. Here it needs to know what is the optimal for every individual and every firm. And that's a lot more information, or a much bigger information burden in the government. The third thing that I hope is obvious is that the system is optimal only if the number of permits is equal to Q optimal. In particular, if the number of permits is less than Q optimal, you get under provision, and if the number of permits is greater than Q optimal, you get overproduction or provision. So it's critical that the government know what the optimal number of permits is for this policy to generate or to restore efficiency. Congratulations are in order. Not only have you made it through Unit 9, but you have finished all of the work, all of the units for the entire course. I hope that at this point you feel that you have gained a deep understanding of the way economists think, how they model things, and how they use models to gain insights about various very basic economic questions. My hope is that you feel that now you have gained a significant mastery of how to set up those models and solve them to answer questions that may be of interest to you in different applications you may encounter. Throughout this course, in terms of conceptual knowledge, you should have gained a deep understanding of how we model behavior by consumers and firms, what are the outcomes generated in competitive markets and their properties, what are the impact that public policy, both desirable and undesirable, has in the outcomes generated by competitive markets, and what are the outcomes and public policy properties of imperfectly competitive markets and markets with externalities. Above all, I hope that you have enjoyed the course enough to be interested in taking further economics. In terms of this unit, these are the key ideas that you should remember. With externalities, the first welfare theorem fails, and it fails in two very different ways. Either with public bads, we have over-provision, so that the quantity generated by the market is greater than the optimal quantity, and with public goods, we have under-provision. The quantity in the market is less than the optimal quantity. In terms of corrective policy, you can use Pigouvian taxation for the case of public bads, with the optimal Pigouvian tax equals to the marginal damage at Q optimal, or you can use permit markets, and in that case the number of permits should be equal to the optimal quantity. In terms of corrective policy for public goods, you can either use Pigouvian subsidies, which are defined analogously, or direct government provision. Hi, welcome to Unit 9, our last unit of the course. In this unit, we're going to leave the world of imperfect competition, go back to the world of perfect competition, but add a feature to the markets that is extremely important in some domains like the environment or research and development. We're going to assume that there are what are called externalities. In other words, the actions of one consumer or firm can affect others directly, and that those externalities can be positive and negative. Then we're going to ask what are the outcomes generated by the market in this case, and what is the role for corrective policies. If you've ever wondered about what should the government do to subsidize research, or what do we know from economics about what is the best way to deal with problems like global warming or acid rain, this is the unit for you. One other goal of this unit that I hope you realize is that it will put into practice as a big application all that we have learned throughout the course. So I hope you get this deep sense of how much understanding you can really have at a sophisticated level of these types of economic questions because of all the work you have done so far. Here is a problem designed to ask you to put all that we have learned so far together. So consider a market in which production creates negative externalities on both consumers and firms. Okay? And in particular, for the consumer side, to assume the following: the inverse aggregate demand function for the market is just 1,000 minus Q, and the total damage for consumers is 2Q squared, where Q is total production. Okay. Now suppose for the producers, suppose there are 10 identical firms, and each firm has a cost function CQ of J equals to 5QJ squared plus 2EQ. Question: what is the deadweight loss in the market or in equilibrium? So let's solve the problem. We're going to begin by computing the equilibrium. And to do that, first we're going to look at the problem of the firm. So each firm does the following. Maximize over Q greater or equal than 0, PQ minus, let me take the parentheses out here, the total cost, which is 5Q plus 2EQ. And notice that E is taken as given. This is going to lead a solution using the standard methods, which is the quantity supplied by firm J is going to be equal by P minus 2E divided by 10. Adding over the 10 firms, we get the quantity supplied by the market, which is P minus 2E. Okay? Notice, by the way, that in equilibrium, as a side note, in equilibrium, the inverse demand function is Q plus 2E star. The inverse supply function, sorry. And this is a marginal private benefit that the firms are going to use to make the marginal private cost that the firms are going to use to make their decisions. Now, let's look at the equilibrium conditions. We know that in equilibrium, E star has to be equal to the quantity supplied. So this implies that the quantity supply in the market has to be equal to P minus 2, the quantity supply in the market, which implies that in equilibrium, the quantity supply in the market is equal to P divided by 3. Also, we know that in equilibrium, it has to be the case that the quantity supply in the market is equal to the quantity demand in the market, but this is equal to 1000 minus P. This is equal to P divided by 3, and together this implies that P star is equal to $750 per unit, and Q star is equal to 250 units. Let's continue with the solution. Now we're going to compute the optimality. And to do that, we need to start by looking at the marginal social benefit. But we know that that is going to be equal to the marginal private benefit plus the marginal damage. So this is going to be 1,000 minus Q. This is equal to the marginal private benefit plus 4Q, which is equal to the marginal total damage. Remember that the total damage was 2Q squared, so this is just the derivative. Sorry, this is minus because it's a damage. So the total marginal social benefit is equal to 1,000 minus 5Q. Now, what about the marginal social cost? We're going to start by looking at the total social cost, and we're going to do it by before. If we want to produce Q units, we're going to produce them by allocating them equally across all firms, given the nonlinearity on cost. So the total social cost is going to be 10 firms times the cost per firm, which is 5 Q over 10 square plus 2Q times Q over 10. And notice that this Q is just equal to the value of the externality. We are substituting, because when we're computing the total social cost, we have to take that into account. And if you do the algebra, this is just equal to 5/2 of Q squared. This implies, taking the derivative, that the marginal social cost as a function of Q is just 5Q. And it follows that Q optimum solves marginal social benefit equals to marginal social cost, which implies that 1,000 minus 5Q is equals to 5Q, which implies that Q optimal equals 100. So let's conclude by computing the deadweight loss. Now we know that marginal social cost is equal to 5Q. We know that marginal social benefit is equal to 1,000 minus 5Q. We know that the optimal amount is at 100, but that the market generates an outcome of 250. So what is the deadweight loss? It's going to be this area here. And let's compute it. That deadweight loss is going to be equal to the integral from 100 to 250 of the area between these two curves, which is 5q minus 1000 minus 5q dq, and this is just equal, if you solve the integral, to 5q squared minus 1000q evaluated between 250 and 100, and this is equal to 112,500. This problem is designed to ask you to put into practice what you have just learned about Pigouvian taxation as a corrective policy. So consider a market in which there are 10 firms, and each one has a production function CQ of j equals QJ. And there are 10 identical consumers, all of whom have a utility function given by 100 square root of Q minus PQ minus 0.9 E. The externality has the following features: is consumer to consumer. There are no externalities in production, and in particular 1 unit of Q consumed leads to 1 unit of E, as we saw in the basic lecture in 6.1. Question: what is the level of the optimal Pigouvian tax and what is Q star in equilibrium given the Pigouvian tax? This problem is quite easy and intuitive if you focus on the right things. Recall or note that the utility function of a typical consumer is 100 square root of Q plus M minus 0.9 Q. Now, what does this imply? That the marginal damage, total marginal damage of each unit of consumption is equal to 10 times, because there are 10 people, times 0.9, which is the marginal damage per person, equals 9. So this implies that the Pigouvian tax, the optimal Pigouvian tax, tau star, has to be equal to the total marginal damage at the optimum, but since the total marginal damage is a constant, it will be that value at the optimum, so this equals 9. So in this simple case, we can calculate what the optimal Pigouvian tax is without having to worry about what the optimal quantity is. Now, what is the problem of the consumer in the market? Is to maximize over Q greater than 0, 100 square root of Q minus PQ, that's the market price, minus tau star Q, that is the tax, and they of course have the externality, but this is ignored or taken as given in problem, and since this is an additive constant, it is ignored, and this implies that the consumer says marginal benefit, which is going to be equal to 50 over square root of Q equals P plus 9, which is equal the marginal cost. And here, remember, this is the value of the optimal Pigouvian tax. But this implies that the demand for every consumer is, doing the algebra, 50 square divided over P plus 9 square. Now, we know that in equilibrium, P star has to be equals to 1 since the firms have constant returns to scale. And we also know that the market demand is going to be 10 times this, which is 10 times 50 square over P plus 9 square. But given that the equilibrium price is this implies that the total quantity in the market has to be this value evaluated at 1, which is going to be equal to 10 over 50 square over 10 square, which is equal to 250. And by the way, if you really want to triple check your intuition about the Pigouvian, you can tag section result, you could check that this 250 is also the optimal quantity for this market. The purpose of this problem is to ask you to put into practice what you have learned about permit markets and to develop some intuition about the difference between permit markets and Pigouvian taxes. So we're going to use the same setting as in practice problem 9.2. And I will remind you what it is. There are 10 firms, and all of them have marginal cost equals 1. There are 10 consumers. All of them have preferences given by 100 square root of Q plus M minus 0.9 E. And remember, the externality is E is equal to the sum of QI when we're assuming over all consumers. So basically, every unit of consumption generates 1 unit of externality. Question: what is the equilibrium price of permits if the government creates A, 250 permits, or B, 500 permits? So solve for the equilibrium price of permits in both cases. To solve the problem, we need to begin with the consumer problem, to understand the consumer that each problem faces, in other words. They're going to want to maximize over Q greater or equal than 0, 100 square root of Q, that's the benefit from consumption, minus PQ, that's the cost of buying the good Q, minus P pi Q. Notice that this is the cost of permits necessary to consume Q units, given that when the price of permits is positive, the consumer is not going to want to buy extra permits, so the number of permits that he's going to buy is exactly Q. The first order conditions for this problem are going to be 50 divided by Q equal to P plus price of permits. And our interior solution, we're going to have that the Q, which is going to be interior in this case, that the demand in the market for both quantity Q and permits is going to be equal to 10 times 50 squared, this is just pure algebra, divided by P plus price of permits squared. Now we also know that producers or firms have constant returns to scale cost function in production of Q, which implies, and by the way, the marginal cost is equal to mu, so this implies an equilibrium. We've seen this 1,000 times in this course. The equilibrium price of Q is going to be equal to mu. Now what we're going to do is look at the permit market. Oops. Look at the permit market. We're going to have that in equilibrium, the number of permits, this is the number of permits, has to be equal to the quantity demanded, which is equal to 10 50 square P plus P pi divided the square. Now let's look at case A. When pi is equal to 50, this implies that 25 is equal to 2500 divided by P plus P pi square, which implies that P pi is equal to 9. And when the number of permits is 500, this implies that 50 is equal to 2500 divided over p plus p pi squared, which implies doing the algebra that p pi is equal to square root of 50 minus 1. Notice one interesting feature. This is not part of the problem, but for your intuition, in this case, the number of permits is equal to the optimal quantity. You can compare that with what we discussed before, and therefore the price of the permits is equal to the optimal Pigouvian tax. In this unit, we're going to continue our systematic study of markets by looking at markets that are competitive but have something called externalities. And here I'm giving you the definition of an externality. An externality arises when the actions of one economic actor, it can be a consumer or it can be a firm, affect directly, and directly is the key word, the utility or production function of another economic actor. And by directly we mean something very precise, which is not through a market transaction. When I buy a car from you, you affect my economic well-being, but that is through a market transaction. Externalities occur directly, not through trading. The concept of externality is subtle, so it's important to look at various examples to really understand it. And I'm going to do it with a table. So here I'm going to put the example, and then we're going to check two tests. Is there an effect on others, and is it direct or through market? Okay, so let's do the first example, which is roommate. Your roommate, your flatmate, plays loud rock music. Is his action of playing a loud music going to have an effect on others, in this particular case on you? Yes. Is it going to be directly or through the market? Well, the moment he starts playing the music, that is going to affect you even if you never decide to purchase that from him. So the answer is direct. So this is an externality. Now let's do another example. What about the fact that the consumption of pharmaceuticals any medicine contaminates or pollutes fish stocks? So a lot of fish, for example, these days are being found to contain a lot of psychotropic medicines. They are really not depressed, for example. Now, question, is that act of consuming a pharmaceutical, buying and consuming a pharmaceutical, creating an effect on others? Yes, it's affecting the fish stock, which is affecting the fisheries. So it's affecting the quality of the product that other fishermen can produce. Is it direct or through the market? No, it is direct. The moment you consume the pharmaceutical and you put the materials, let's say when you go to the bathroom, in the water, they end up in the sea and they end up in the fish. So it is direct, it's not through the market. This is an example of an externality. Okay, now what about, let's do another example. Microsoft hires 10,000 new software engineers, and let's suppose that you are one of them. Does that have effect on the well-being of others? It definitely does. Those engineers are going to have a higher income and they're going to have a much better lifestyle. So the answer is yes. Is it direct or is it through the market? It's through the market. The engineers have to agree to work for Microsoft for those transactions to take place. So this is not an externality. Let me give you another example that is a little bit trickier. What about if a company invents a drug that makes people 10 times smarter? Would that produce an externality? Well, it clearly will have an effect on others that consume it, and perhaps even in those that don't consume it through competition and things like that. But the key thing is that as long as the economy works through the market and as long as nobody can be forced to take the medicine, this is going to work through a market exchange, through an agreement to take the medication. So this also is going to be an example of market, and it's not going to be an externality. Externalities come in many different shapes and flavors and in different degrees of complexity and subtlety, and it's important to do that in order to have good intuition, to start with simple cases. So I'm going to first spend a lot of time working on what we're going to call public bats. It's a particular type of externality that has the following features. They are negative. In other words, they harm others. And they are non-targeted. And by that I mean that they tend to affect everybody in a side of the economy. For example, all consumers, or all firms, or everybody. Let me give you examples of public bats are CO2 emissions and global warming. If we end up experiencing global warming, and that's caused by emissions of CO2, every time you drive your car, you're hurting all other consumers and all other firms. Noise pollution, this is very common, for example, in Spanish cities. This tends to affect all consumers living in the neighborhood. And the fact that one person is affected doesn't decrease the ability or the extent to which others are affected. And another one is something that we actually saw before, which is poverty. If you have a situation in which people have social preferences, and for example, they feel bad from knowing that there are other people in their economy, in their country, that are poor, the fact that there are poor people, somebody not being able to reach a living wage and sufficient income will cause a negative externality, a public bat for everyone. Now we're going to start our study of the public bats with a very, very simple model that is going to allow us to develop in a very clear way some key results and intuitions. And then we will complicate it or look at different, more complex versions of the model in applications in the practice problems and in the problem set. So again, this model is very simple, but it's simple by design to really clarify some ideas. So we're going to look at a market with three goods. There's going to be the goods Q and M that we have always been looking at. And in addition, there's going to be this good E. And you can think of this as the externality. And if you want to keep a concrete example in your mind, for example, think of pollution, some sort of pollution. And another important thing is the technology of the externality. What is the production function of the externality? And the idea is that every time one unit of Q consumed, every time a consumer consumes a unit of Q, it generates 1 unit of E. Notice that this doesn't have to be integers. If they consume 0.1, it leads to 0.1 of E. Now we're going to assume that there are n identical consumers and that they have the following utility function, and now depends on Q, M, and E. It's like before, a benefit function of Q plus M minus gamma D of E. And this D of E has the property that is positive and potentially increasing at either constant rates or increasing rates. So in other words, if you have E, D will be like this or like this. Now a couple of comments. You can think of this as the damage as a function of E, which is the total level of the externality in the market. And you can think of gamma as a parameter greater or equal than 0 that tells you how big is the damage, how important it is. And we can turn on and off the level of the externality by turning on and off gamma. In this simple model, there are also going to be F identical firms. And these firms are going to have a constant returns to scale production function, so their C of Q is an identical mu of Q. So you have a lot of experience computing the equilibrium of markets in which look like this. They are competitive but there is no externality. I'm going to add here as a reminder in your note that the market is competitive. Okay, now the only thing that has changed here is that now every time a unit of Q is consumed, it creates a unit of externality that affects everyone. Everyone, that is key. To be able to characterize the outcome of the market, we need to define a notion of market equilibrium. As you will see, the notion of market equilibrium is very similar to the one for a purely competitive equilibrium. And that shouldn't be totally surprising given that it's a competitive market. So in the market equilibrium, two things are going to be true. First, every consumer is utility maximizing, so there is utility maximization and profit maximization by all firms and consumers. Importantly, taking as given the total level of the externality. So the idea here is that there are many players in the market, all of which affect the externality, and therefore when they are choosing their actions, they don't think that they can affect the total level of externality. Much in the same way, when you drive your car, you probably don't think by yourself you really are going to change during that decision global warming. And the second is that prices adjust so that market clears, just as before. So what does this mean in practice? Let's look at the problem of the consumer. The consumer is going to maximize how much to buy, so over Q greater than or equal than 0, how much to buy in the market. It gives him this much benefit, minus direct benefit, minus it has to pay this much. It also gets this externality that depends on E, but importantly, this is a constant, since it's taken as given. And what does this imply? This implies that the demand function for the consumer and the demand function for the market is just as without externalities. Nothing has changed in this particular case. Notice that this is true in particular because the externality, if you're thinking carefully about this, is additively separable. There are cases in which the demand function can change, and we will see in examples later. But in this particular simple model, nothing has changed. What about the problem of the firm? Well, the firms, as before, are going to maximize over Q greater or equal than 0 their revenue minus their costs, which we have assumed as CRS. So we're going to have, again, the same supply function and the same supply function for the market, which is 0 if price is less than mu, anything if price is equal than mu, and infinity if price is greater than mu. So this is a market equilibrium that you have solved in homeworks many times and should be very obvious. Now that we know the market allocation, let's study whether or not it's efficient. And to do that, first we need to look what do optimal allocations look like in this simple market with public bats. So we know that an optimal allocation has to maximize total utility in society, the sum of the utilities, and we know from a lot of previous work that we can write this as maximizing over positive consumption of Q, the sum of the utilities for the individuals, where we can write like this, the sum of the BQI minus, and this is for every I, the damage from the externality, which is Q total, or the sum of the QIs. Remember, this is the externality, minus the cost of producing this level of QI, because that has to be discounted out of what they get to consume on M. And what you get, since the B functions and the D functions are identical, is that every one gets to consume at a point in which B prima Q total divided by N minus gamma N D prima at Q total is equal to mu. everybody is a symmetric allocation because individuals are identical, characterized by this formula. So notice that we can write this formula like this, or we can pass it on to the other side. But basically, one important intuition here is that this is the marginal cost of producing Q, and that this is the marginal benefit. Let me be precise. This is the marginal social, I'm going to do it by MSB, the marginal social benefit of giving additional units of Q, an additional unit of Q to anyone. Okay, let's get some intuition for this. Suppose that gamma was 0. If gamma was 0, if this was not there, the marginal social benefit would just be the marginal benefit for that person, and the optimum has to be equal to the marginal cost of production. The problem here is that we have here the marginal externality. Every time you give a unit of Q to someone, you increase their marginal benefit of consumption by B prima of this, but you also create damage on everyone. How much damage? All of this much. And therefore, the marginal social benefit in this case is less than the marginal private benefit, which is just equal to the B prima of Q total divided by N. Notice that in this simple example, the marginal social cost is equal to this marginal cost of production. There is no externality on the production side, therefore the two things are the same. In this simple case, the optimal allocation has a very nice graphical representation. So again, let be Q, let be these dollars per unit. We have mu, which is equal to the marginal private cost, and is equal to this marginal social cost of producing Q. And then we have the inverse demand function for the market. And notice that this function can be written as B prima Q total divided by N. Why is that? Because we knew that this was the aggregate marginal benefit of consumption. What is the increase to the group of giving it an additional unit when it's distributed optimally? But because everybody is identical, that unit gets distributed identical to everyone, so everybody gets 1/n of the extra unit. Okay? Now, what else do we know? We know that this is not the marginal social benefit. This is what is often called the marginal private benefit. The marginal social benefit is going to have to subtract this marginal damage. So it may be a subtraction, let's say like this. So that curve is going to be the marginal social benefit, and this gap at any point is going to be gamma n d prima of Q. Now, what do we find out? We find out from this graph that the optimal amount is with the marginal social cost is equal to the marginal social benefit, which is here. This is the optimal amount of Q. Now we can characterize the deadweight loss, which is the size of the inefficiency in this market, graphically. We know that the market is going to produce at a point in which the inverse demand function, which remember measures the marginal private benefits, is equal to the marginal private cost, which is equal to the marginal social cost in this example, which is equal to mu. And that is going to give us this equilibrium of the market allocation. Now we also know that the marginal social benefit is going to be shifted left, and this marginal social benefit curve is going to be equal to the marginal private benefit minus gamma n d prime of Q. This is the marginal damage, the marginal externality that gets produced. So we know that the optimal amount is when these two curves intersect, and is here. So this is the optimal amount. Now, of course, the question is, what is the deadweight loss? And the deadweight loss is going to be equal to this triangle. It's going to be the difference, the excess social cost over the marginal social benefits, which is going to be equal to this area. That's going to be the deadweight loss of excess production. Why am I calling this excess production? Because the Q of the market is greater than the optimal. Now let's remember why this is a deadweight loss. This is the optimal amount. Every additional unit that gets produced has a marginal social cost of production that exceeds the marginal social benefit. Intuitively, why does the market produce it? Because when the individuals make their decisions, they only take into account the marginal private benefit, and that marginal private benefit exceeds the marginal private cost, which is the equilibrium price mu, all the way to the market equilibrium. But from a social point of view, this is the amount that we would have wanted to be produced, and this is the loss in total utility for the market that happens. I want to conclude this section of the video lectures with two remarks. First is we have looked at a very special model, a very simple model of public bats to derive some intuition in which all of the damage happens from consumers to consumers. But I want to emphasize that the finding that there is inefficient overproduction of a good Q when it induces negative externalities is a robust finding. You can extend the model in many other ways, as you will see in the problem says, and you will always have that Q star, the Q of the market, is greater than the optimal amount. The second is that when you solve the problems, you're going to have to decide whether the externality is lowering the marginal social benefit or is increasing the marginal social cost. And in examples like the one I just gave you, this is a natural way of doing it, but in other examples it can get complicated. So I want to propose to you a normalization, a recipe, an accounting recipe for externalities, which is that damages or externalities that affect utility go into the marginal social benefit part, and externalities that affect cost or production go into the marginal social cost part. Let me emphasize, don't over worry about this, because as long as you're keeping your accounting correct, it doesn't really matter where you put it in terms of characterizing the optimal amount, the optimal policy, and all of that. But this, I have found over the years that this recipe really helps students keep things clear. If you have an externality like pollution that is produced by consumers that affect the utility damage to consumers will go into the marginal social benefit part, whereas the part of the pollution that increases the cost of firms will go into the marginal social cost part. I hope that you find that recipe useful in solving problems. Consider another example that is also quite representative of externalities, but that is more complicated to solve. Now we have a market in which all externalities are firm to firm. And in particular, the story that we have in mind is that each unit of production, each unit of Q that is produced creates 1 unit of pollution E. So notice that this implies that the externality, the total level of the externality, is equal to total production. The J's are firms. Okay? Now, we're going to assume that the demand function is given for the market by 1000 minus P, that there are 10 identical firms, just for the purpose of this example, and they have each a cost function C of Q of J equals to 5 Q squared of J plus E Q J. Again, when E is the total level of the externality, or total level of the pollution in the market. So think of an example in which, as the firms produce, they create pollution, but that makes it harder and harder to produce. They impose cost, or they increase the marginal cost of production for other firms. Notice that the marginal cost increases because here the marginal cost of Qj given E is 10 Qj plus E. So every unit produced by any firm increases the total level of the total marginal cost for every firm by 1 unit. Now let's derive the supply function by looking at the problem of a typical firm. So each firm is going to have the following problem. Maximize over Q greater or equal than 0 is revenue PQ minus its costs, which are 5Q squared plus EQ. Critical, as before, this level of externality is taken as given when solving the problem. Why? Because there are many players that the firm assumes that it cannot affect the total level of pollution. This is of course not literally true, but it's a good approximation, and when there are enough players, it's a very, very good approximation of how the firms behave. Now, this implies this is going to have a solution in which the marginal revenue is equal to P, the marginal cost is going to 10Q plus E, and this implies that the supply of any firm J is going to be P minus E divided by 10, and the supply of the market, which is just 10 times that, is just P minus E. Okay? Now, important, in equilibrium, that E is going to be equals to Q star. But when we have derived the problem of the firm, we have assumed that the firms were taking that as given. We have not, the firms were not really worrying about how their own actions were affecting this. Notice that this problem, the reason that this problem is more complicated than the previous one, is that now the behavior of the consumer or of the firm, in this particular case the firm, depends on the level of the externality. Before, it was independent. Now, what's the market equilibrium? We know as before that in equilibrium it's going to have to be the case that the quantity demanded in the market is equal to the quantity supplied in the market, and that prices are going to adjust so that that happens. But there is another thing here that we have to worry, which is that the total level of the externality is going to be equal to the total level that is sold by the firms. So both equations are going to be true in equilibrium. Okay? Now let's work with the second equation first. We know that in equilibrium, so we have derived before that the market supply as a function of P is equal to P minus E. But that implies that since in equilibrium E has to be equals to the Q of the market, this implies, doing the algebra, you just substitute and do the algebra, that the quantity supplied by the market is just P divided by 2. Now, substituting in 1, this implies that the demand in the market, which is 1,000 minus P, has to be equal to the supply in the market, taking into account the effect of the externality in the demand. It gives you P over 2, and this implies, doing the algebra, that P star is equal to 2,000 over 3, and that Q star is equal to 1,000 over 3 units. Okay? Notice the key thing was here that we had to take into account to really pin down the supply function that whatever quantity was done in equilibrium, that was going to affect the amount supply through the externality. Now, we know that the optimal quantity is going to be given by the intersection of the marginal social benefit equals to the marginal social cost. We saw that in different ways over the previous units, and especially on the previous video lecture. The key thing in any externalities problem is to characterize properly what the marginal social benefit and the marginal social cost curve are. So let's do that. The marginal social benefit in this particular example is just the marginal private benefit because the consumers are not being affected by the externality. And we know that the marginal private benefit is just what we have been calling the aggregate marginal benefit function before, which is just the equal also to the inverse demand for the market, which is going to be therefore equal to just 1,000 minus Q. Okay? The only new change of reasoning here, chain of reasoning, has been this, that because there are no externalities, the marginal social benefit equal to the marginal private benefit. What about the marginal social cost? See, when it's a little bit more complicated in this problem, but if you use a little bit of economic intuition and logic that I hope you have started to really internalize, it's actually not that hard. Now, what is going to be the marginal social cost? Is the cost of increasing production by a tiny amount. Now, notice that the individual production functions, cost functions for the firms are C of Qj equals 5Q squared plus EQ. This increases non-linearly, therefore, with Q. And this implies that it is optimal to split production equally across firms. In other words, you want to give every firm an equal share to really minimize the cost of production by avoiding the quadratic term to kick in. That implies that total social cost times 1 by TSC is equal to 10, because there are 10 firms, of producing Q units, times the cost for each firm of producing, let me rewrite this to improve the notation, times the cost of producing 10 units in a typical firm, and this is equal to 10 times 5 Q squared over 100 plus the externality is going to be the total level produced, so Q times Q over 10. Notice again, don't be confused here, this terms is equal to the externality. This is equal to 3/2 of Q squared. And therefore, if you take the derivative with respect to Q, we get that the marginal social cost is just 3Q. What you should learn from this is that if you are not sure how to compute the marginal social cost, in the case in which there are externalities in production, what you can do is compute what is the optimal way of setting up production, set up the total social cost, and take the derivative. So what is the optimal quantity, therefore? We have marginal social benefit equals marginal social cost, which implies 1,000 minus Q equals 3Q, which implies that Q optimal has to be equal to 250. To gain more intuition, it's useful to look at the difference between marginal private cost and marginal social cost in further detail, and these are different. Now, we have seen that marginal social cost is 3Q. We just derived that. The question is, what's marginal private cost? Well, we know that marginal private cost is going to be equal to what we have been calling the aggregate marginal cost function, which is just equal to the inverse supply function as a function of Q for the market. And we know that this is just P minus E. Now, importantly, this is not just any, which we have seen was P plus E, but that's just not any E, is the E at equilibrium. So I'm going to add star there. And of course, we know that E star is going to be equal to Q star because of the assumptions of the technology for the externality, which is the sum of the quantity produced. Now, we know, therefore, that in equilibrium, this is going to be equal to P plus 1,000 divided by 3, which is the quantity produced. So I'm going to plot for you what these animals look like. Marginal social cost is equal to 3Q. Okay? A function that looks like a marginal private cost, let me say it differently, the inverse supply function of the market when there are no externalities is just Q. Okay? Apologize, there's a typo here. It should be a Q. It's the inverse. Okay. And finally, we have what's the marginal private cost, which is the cost that the firms are using to base the supply function on. It's just the one without externalities plus this external effect that they internalize, which is just a shift up by E star equals to 1000 over 3. That is their marginal private cost in equilibrium. Okay. Now, why do I call it an equilibrium? Because the value depends on what they anticipate E to be, and they are assuming that E is fixed at the value in equilibrium. Notice how this is different from the marginal social cost, and it's also shifted from the case of no externalities. Also know that in this example, again, it depends on the equilibrium value of the externality. Now let's put all together in a diagram that is going to allow us to compute the size of the inefficiency. So these are dollars per unit as always. It's a quantity in the market. First, we're going to have this curve, which crosses here at 1000, has an expression of, is the inverse market demand function, which is 1000 minus Q. And we know that because all of the externalities are within the production sector, this is equal to the marginal private benefit and the marginal social benefit. We also know that the supply curve in this particular case is going to take the form, this is a supply curve in the market against in inverse form, to Q plus E star, which is Q plus 1000 divided by 3. The equilibrium is going to be given by the intersection of these two curves and is at a quantity of 1000 divided by 3. Notice also that this is equal to the marginal private cost, the cost that the firms are internalizing when they are making the decision about how much to supply. Finally, we have this curve, which is 3Q, which is equal to the marginal social cost. And that gives us this point, which is Q optimum, equals to 250. Now, as before, we find that the optimal level of production is less than the amount generated with the market, which again is a general feature of these markets with public bats. Now, the question, of course, is what is the deadweight loss? Well, it's going to be given by the area between the optimal quantity and the quantity produced between the marginal social cost and the marginal social benefit curve. So by now you should be used to that. It's going to be given by this area. That is the deadweight loss in the market. I want to give you an intuition for why does the first Welfare theorem fail in the presence of public bats that span both of the examples that we have looked at in detail. What do we know? We know that the market, the invisible hand of the market, induces consumers to set their marginal private benefit, their marginal benefit equal to the price, by utility maximization. We've been seeing that throughout the course, and that's what utility maximization does. And also that it induces firms to equate price equals to their marginal private cost by profit maximization. That's what competitive firms do. Now, we also know that optimality requires that the marginal social benefit be equal to the marginal social cost. That's what optimality requires. Now, in the case of no externalities and competitive firms, marginal private benefit is equal to marginal social benefit, marginal private cost is equal to marginal social cost, and therefore the invisible hand of the market, through utility maximization and profit maximization, generates the required optimality condition. But what happens in the case in which there are externalities? With externalities, the marginal private benefit is going to exceed the marginal social benefit, and the marginal private cost is going to be less than the marginal social cost. Every unit produced costs more than the producer internalizing and generates less benefit because it creates damages that the consumers are internalizing. But since the market induces this, it also implies that the market induces that the marginal social benefit is going to be less than the marginal social cost at equilibrium. And therefore, this also implies that the Q of the market is going to be greater than the optimal amount. Here is another way of seeing that. Let me do it in black. That may provide even better intuition for some of you. We know that the market equilibrium is going to happen when the marginal private cost is equal to the marginal private benefit, or the inverse supply curve is equal to the marginal private cost, or the inverse, demand and supply curves. That's going to generate the quantity of the market. But what are the externalities going to do? Are going to shift the marginal social benefit below the marginal private and the marginal private social cost above the marginal private cost. So both of them are going to push the optimal quantity below the quantity of the market. Now, the details of where these curves are depend a lot on the details of the problem, but this insight is completely general. So far, we have considered the case of negative externalities, and in particular the case of public bads. Now we're going to look at the reverse case, which is the case of positive externalities, and in particular at something called public goods. Now, public goods are going to be positive externalities, an instance in which there are positive externalities to other consumers or firms, or both. And there is what is called non-rivalry in consumption. And what this basically means is that every actor can benefit from the positive externality. Let me give you an idea to define that more carefully. For example, a typical externality, positive externalities, is basic R&D. If a company invests in R&D and comes up with a new idea that other firms can use, every firm, every consumer in the economy can use it, and the usage of one person doesn't diminish the fact that it can benefit others. In that case, it's non-rivalry in consumption. In contrasting what happens when somebody produces an apple, if somebody eats it, consumes it, nobody else can. So public goods have this feature of positive externalities and non-rivalry in consumption. What are other examples? Very famous example that I like a lot, if in the United States, is something called the LoJack anti-theft system. So in the United States, they sell this system that you can install in your car that basically is like a beeper, a locator for cars. And if your car gets stolen, it allows the police to track the car to the thieves. Now, this is very useful because it turns out that thieves steal many cars and they bring them to a common place. And therefore, when through the LoJack they locate your car, they actually arrest the entire band of thieves, and that decreases the probability that everybody gets the car stolen. That is a direct positive externality that looks like a public good. Another one that we have mentioned before is what I call network externalities in consumption. For example, HBO or Facebook. These are activities that your marginal benefit from consuming may increase on how many other people are consuming or engaging in them. So, as before, there are many different detailed models of public goods that depend on the specifics of the problem, and here we're going to talk about a general one that captures the essence, and it's a very simple one. So the idea is that there are end consumers, each of whom has a utility for Q, M, and the externality given by B of Q plus M plus gamma G of the externality. And now G is greater than 0, G prima, and G double prima is less or equal than 0. This is a parameter greater or equal than 0, measuring measuring strength of the externality of the public good. And as before, we're going to assume that E is just the sum of the Q's, to keep it simple. The other aspect of the model is that Q is produced at constant marginal cost mu. So it's a very, very simple model that parallels the one that we saw for public bads, but now the externalities are positive. What does the equilibrium and the deadweight loss look like in this case? Let's think about it. We have dollars per unit, we have Q, we have mu equals to the marginal private benefit, sorry, the marginal private cost and the marginal social cost of production. And we have this curve, which is going to be the demand function in the market that the individuals have, which is the marginal private benefit. But we also have this other curve, which is going to be the marginal social benefit, and this gap is going to be given by gamma and G prime. Okay. In this case, the marginal social benefit is above the marginal private benefit because there is a positive externality. What do we have? The market is where marginal private benefit is equal to marginal private cost, so it generates this quantity. But the optimal quantity is where the marginal social benefit and marginal social cost intersect, which is this. So there is underproduction. We derive this graphically for this very specific model, but as before, this is a very robust result for public goods. What's the deadweight loss in this case is going to be this triangle for analogous reasons to everything that we have been seeing. Now, it shouldn't be surprising to you that the opposite case of Pigouvian taxes can be used as a corrective policy for the case of public goods. With public goods, there is a problem of under-provision, so we have to subsidize instead of tax the behavior that is not being supplied sufficiently to encourage it. So what is the policy here? You're going to subsidize the sale or consumption or purchase, depending on whether you put it in the consumer or in the firm, of good Q with a subsidy sigma star equals to the marginal externality social at the optimum. And it's going to be financed, the cost of the subsidy is going to be financed with lump sum taxes. And the result is that this policy, Pigouvian policy, restores efficiency, just as before. Now, in some cases, another good corrective policy is government provision. Look at an example or an extreme case in which the utility function of the consumers has 0 plus m plus gamma g of e. So in other words, there is no direct, no consumption benefit of qi, but there is a positive externality. In this particular case, we're going to have that the Q of the market is equal to 0. Nobody's going to provide anything. And we're going to have that the optimal policy, the government can restore optimality let me say it differently. The policy first buy a Q optimal and finance with lump sum taxes restores optimality. This is basically a case in which the government just goes directly and purchases the optimal amount. And as before, as we have been emphasizing, notice that this requires extra information on the part of the government. One remark is that policy not optimal if lump sum taxes are not possible. In other words, if the government needs to finance its purchases with a tax that creates a deadweight loss, it's never going to be able to restore the first best, because every time it raises revenue, it creates an inefficiency. And the benefit from the public good and the cost of taxation needs to be balanced in that case.